Very good morning, good afternoon, good evening to all our audiences, all our guests who've taken time out and joined us here. First and foremost, thank you for your time. Well, we do know this is the IEEE Data and Storage Symposium 2022. Hearty welcome to all of you who've joined us here today. We do know organizations are facing unprecedented challenges storing and managing data. Not only must they have handled greater amounts of data, but they must also work with different types of data. Much of it is unstructured. At the same time, modern workloads have become more complex and pose high demand for reduced access latency and better space efficiency. Some of the major technological driving factors like reduced cost of media, ever increasing cores or processor die have raised the bar for innovation on traditional storage systems. These are the exciting times. And to listen more on what's next on storage, IEEE Bangalore section presents its fourth edition of DSS. DSS had been an industry flagship event connecting technology leaders across various segments of the data management and storage world. Like previous editions, today as well, we do have technology leaders, innovators, entrepreneurs, and thought provokers who are passionate about addressing impactful problems by turning ideas into solutions. Industry stalwarts and technology practitioners together will share their vision on the challenges the storage industry is facing today and the researchers' ideas to address them. As the pandemic is majorly over, but yet the risks of it is reoccurrence and it remains. Keeping this in mind, we are here joining virtually today. And your in-person interaction will certainly be missed. But however, we are excited that we have participants from academia and industry across the world. Once again, hearty gratitude to IEEE Data and Storage Symposium 2022. Before we begin and tell you what else is in store, I'd like to invite our Chair IEEE to join us, Dr. Deepa Shenoy, and she is the IEEE Bangalore Chair section and the professor at University Visvesvaraya College of Engineering, Bangalore. And most importantly, ladies and gentlemen, she is the first woman chair of IEEE Bangalore section. Over to you, ma'am. The virtual stage is all yours.
Yeah. Good morning. Can you all hear me?
You're audible, ma'am.
Yes. Okay. Warm welcome to the fourth edition of Data and Storage Symposium, jointly conducted by IEEE Bangalore section, IEEE Computer Society, and Huawei. So data is growing in an unprecedented way, and currently and in future, it will be everything, and we have to have various platforms, servers, and algorithms, memory to handle this unstructured and variety of data. Okay, today I just want to share for a few minutes my interaction with data. So my interaction with data started somewhere in the year 2000 when I started doing my research in the area of data mining. I started working with simple transaction data. We generated data ourselves using various distributions, random numbers, and tried to find out patterns using various algorithms. And it is very, very hard with limited resources and limited knowledge what we had. And especially we tried to find out the buying patterns of various customers in a shopping mall or so on. Now things have changed. Now the data has grown tremendously. We have various tools, but now the problem for my students who are pursuing research in various areas of medical field or agriculture or waste management or finding out opinion minding, they find it very hard to get the data itself. From where to get the data, because it is hard to generate primary data ourselves. Medical data we cannot generate ourselves. We want the ready data from an authenticated source. Sometimes it is small. What we get is very small. Then what we do, we use synthetic data generators to enhance the data. Sometimes we get a huge data, we cannot manage it. What we do, we cut down the data, make it small, cut down the dimensions, reduce the number of records, and make it small and try to run the algorithms. So with the machine learning algorithms and deep learning algorithms, which want more and more and more data to give accurate patterns and outcomes or output with greater efficiency and accuracy, we need systems to manage, handle, store, and retrieve data. So today's symposium is all about this with highly eminent speakers and very expert and good audience. I wish this symposium a great success, and thank you for inviting me. Thank you so much. All the best. We can't hear you. You are on mute.
Thank you. Thank you. Thank you so much, Dr. Deepa Shenoy. It was lovely having you with us this morning. And without further ado, ladies and gentlemen, we would like to take you through what else is in store this morning. We have 6 sessions. We'd like to start this event with our keynote speaker who's taken time out and joined us here. And that is Dian Milojcic, who is the Distinguished Technologist and Director at Hewlett-Packard Labs and the past president of IEEE Computer Society 2014. And the virtual stage is all yours, Dian. We've been waiting for this moment. Over to you.
Thank you very much, Rina. And before I start, I'd like to join in hearty congratulations to Professor Dr. Deepa Shenoy. Bangalore section is one of the most important ones. I think we are very close to each other with Santa Clara Valley section, which is really Silicon Valley and Bangalore. Can I please be enabled to share? Okay, now I can. Can you see my just a second.
Yes, your screen is visible.
Thank you. I really like how Professor Dr. Deepa Shenoy spoke about data, because it's really all about the data. Storage is the place where we store the data. So today, when thinking about what I will be talking about, I chose to tell you a little bit about how in Hewlett-Packard Labs, we look at this problem, which is a little bit broader, not just data and storage, because you need to process this data. And then I'll focus on a program that I have started a few months ago, which is called Heterogeneous Serverless Architecture. So in labs, we are focusing around 6 areas. Silicon design, where we develop chips that really enable you to access data, to transfer data. We look at photonics and fabrics, which connect both storage and computing entities in small computers or larger computers. Then we look at networking and distributed systems that run middleware and other things. We have security lab that makes everything secure, because if your data is not secure, you can't trust it ultimately. As Dr. Deepa Shenoy was mentioning, AI and accelerators with machine learning are now really helping us analyze this data. And finally, my own lab is system architectures, which enables you to put it all together and run everything. So this is not marketing slide about labs. It's more explaining how one labs is organized in order to address this large problem. And we look at all these problems because we are labs, we go from 5 years and sometimes even 20 years out. That's how long it takes to come up with new materials, new technologies. For example, for memristor, it took over 20 years, and for silicon photonics, similar. But we really like to be somewhere in between 2 and 5 years to be able to transfer technologies to advanced development teams who really live between today and the next few quarters. And I'm sure Chengapa and other people in the industry can really tell you about it much more. This is the slide that Professor Dr. Deepa Shenoy was talking about, this really tremendous growth of data. And we have been using this slide really for maybe last 7, 8 years, but it became richer and richer. Originally, we were emphasizing that the growth of data has outgrown the growth of compute. So compute was not able anymore to manage that data, to analyze it. And then came various accelerators like GPUs and as of recently many others. But then the models that analyze this data started growing. So one or the other way, there's always a lot of growth of data or in support of data. And now what is really important is once you analyze this data, how you take action on it. So there's this combination of exponentially increasing data, exploding data sources, and shrinking time to action, which really means that this computing power, including these accelerators that are really close by to the sources of data, have to enable you to address this growth. To be able to have one unified architecture all the way from edge towards exascale system. So we have just recently announced the first exascale system, Frontier, that was developed and deployed. But you can't really afford to have all kinds of different architectures because it's hard to develop them, to produce them, to maintain them. Our ultimate and ideal goal is to have all these components of memory, compute, and then storage and accelerators and interconnect that could be transparently used from all the way edges through cloud infrastructure, through large memory systems, to exascale systems, and then ultimately to the next generation architectures, which we still don't know how they look like, that support quantum computing and neuromorphic and other architectures. What we've seen recently is that world has been turned upside down. The new accelerators like Cerebras, which used to be in the past really slaves to computers, so you would have a computer and then you have these slave accelerators that will do tasks only for that, really are so much powerful that they require superdome computers to feed the data in them. So in order to feed them data to conduct this very powerful processing, there's 12 times 100 gigabit Ethernet, over 100 gigabit Ethernet switches. And we have these huge computers that over using NVMe devices are now feeding data into these accelerators and enable scientists, because ultimately what we care about is scientists to solve the problems. Nobody cares about, what kind of computer did you run on it. It's just us geeks who need to develop them and support them. But ultimately, we need scientists to get hold of these and to advance the science. There are different deployment models for these accelerators that are now addressing this growth of data. So you can have these accelerators cards like you have with GPUs or FPGAs. Then there are these larger accelerators like Cerebras. And then you even have systems like racks that are full of these accelerators. And then there are also analog accelerators and neuromorphic and other more exotic forms or fashions thereof. So there's a pretty rich landscape in terms of deployment factors. What is happening with this growth of acceleration and heterogeneity is that we are transforming performance with this novel programming. So on one hand, we have variety of CPUs and variety of accelerators, but then we also have different types of memory. We have DRAM traditionally, which have high bandwidth memory, storage class memory. We have fabric attached memory. So we have different models, and we're introducing different programming like OpenFAM for fabric attached memory, or new types of frameworks that can program these accelerators. But ultimately, it's how you program and access them that's probably really most important. And because there are so many of these new accelerators, they're almost becoming siloed. There's a little bit of commonality between GPUs and CPUs, but other types of accelerators, FPGAs, they're really siloed. And it's not only about different source code. You spend even much more time in compilation and most time on optimizing these kernels that run on these accelerators. We would like to go from this siloed approach towards innovation where you can have as much as possible common source code, then commonly optimize high-level synthesized code, and then optimize low-level code. And only then do you go and, in an automated fashion, go and deploy and run on these different accelerators or different types of compute. Eventually, we will hopefully have unified hardware, but we're still far, far away from there. This is pretty straightforward picture, and the reason I included it is that in labs in Hewlett Packard Enterprise, we discussed it with memory vendors and compute vendors. And when you think about storage, you think only about storage, but there's a number of deployed accelerators throughout this whole architecture. So in a memory lake, which would be closest probably to what you consider storage today, you have MPUs. In Fabric, you may have SmartNICs. In both DRAM, down the line, they're talking about MPUs, and in HBM as well, memory processing units. And so all of them are really helping to do some optimizations very close to the data. Now, we really need to be mindful, where is this data coming from? And usually it's coming from the edges. These edges could be heavy edges, like this large hadron collider that produces tons of data, or it could be light edges, like information from satellites, from fire alarms, and things like that. One needs to pass this data from edges to the place where you will manipulate that data, process it, could be either on-premise or in cloud. But then in order to hedge your bets, or do the risk management, you really want to federate things. So you can federate at the IoT level, you can federate at the clusters or federated clouds in order not to put all your bets on Amazon or Azure or Google. And then there's also what we call vertical federation, horizontal federation, probably diagonal if you want to go from one federated entity to another federated entity at the higher level. What I was saying earlier about unified hardware, this is not the first time when we have a number of different processors or processing power. Some of you, I'm not sure about Professor Deepa Shenoy and some of my colleagues, but those who started working in early 80s, they may remember Motorola, Zilog, MIPS, HP has their own processor, Digital, many others. Over the time, industry and market demanded unification. So for a while, there was only Intel, AMD, and then ARM came. So we have a similar situation where first you have this specialization, which brings innovation, but then you have generalization. We anticipate the same thing will happen. We'll again have, after these thousand flower blooming specialization, we'll have a generalization in order to make it easier on the market. One downside of having so many accelerators is that all these companies are trying to innovate on their own. And they are innovating even where innovation is not really required. And these things are at various buses because they want to put them together, package them in racks. We came up, and there's associated report here. You can download it. There's even video, YouTube video of this. We are advocating that as a system integrator company, that there's a need for industry standards to be used. Industry standard here, but also for system integrators, some of these other points like NICs, like runtimes, network stitches, they should also be standardized. These are the points: local I/O, APU, local fabric, various plugins, etc. So I'll skip this slide in the interest of time, and this one as well. So I spent about half of my time talking about generic landscape and how we address these things as a lab broadly, and then as our company. The remaining half of my time, I will tell you a little bit about the program that I have been leading. We just started. It's called Heterogeneous Serverless Architecture. And there's a number of people, some of them are not even listed here. The intuition that drove formulation of this program was that Um, there's a lot of heterogeneity as we witnessed in previous slides, but then there's also evolution of virtualization techniques. We started with clusters, then came virtual machines, which were abstracting hardware. They still retained the operating system, but abstracted it from the hardware ISA. And then containers came that abstracted the operating system and made it much easier and quicker to start them. And then most recently, there are functions as a service, also called serverless. These functions are abstracting away even DevOps. So you just have to think about the functionality, the functions, and the system takes care of everything else. It can scale it out, scale down, and all kinds of things. Our intuition was that the level of abstraction of these virtualized functions matches the kernels that are run on these accelerators, both in the size of the abstraction and the amount of time. Usually, when you deploy clusters, it goes for 5 years. You deploy VMs, they can stay for a number of months. Containers, you can fire them off and run them for a few minutes. Functions, you can run them for a few milliseconds, and then they are over. And the similar is true with all these accelerators because you fire off these kernels on them and then you're done. So the bottom line is we felt that there's a good match between the two. We chose serverless as one point in virtualization. We could have also chosen others. We could have chosen containers. We could have chosen bare metal as a service. But we felt that serverless are the right both from the time horizon, as I mentioned, it follow our intuition. When we developed this serverless, heterogeneous serverless architecture, we had three goals on our mind. The first one is seamless scalability and fluidity. And we started from the really high performance computing where the things are ran on a supercomputers and very rarely do they go out of them. They can usually partition them. Since they started using AI, as Professor Deepa Shenoy mentioned, there's also need to switch and invoke some kernels on these accelerators, but in reality, it's really hard for them to go to another supercomputer or other cluster or anywhere else. So this is our first goal, to enable this seamless scalability and fluidity of these programs that can go and run elsewhere. The second one is increased programmer productivity, and I'll explain in detail what it means to me. And then finally, it's performance efficiency. When we think about as a system integrator and as a provider, we think how efficiently, and also cloud providers do the same thing, how efficiently are these programs run, because they take a lot of energy and you sell these CPUs and memories and all of that. So you want very efficiently to put these together to run. So what is this heterogeneous serverless architecture? For us, it's a secure, scalable architecture that allows users to access heterogeneous resources where they're available through workflows. So workflows is really important, that can be easily composed and remotely invoked through serverless interfaces. So that's what it is. So if you think about these workflows today, scientific workflows, they are running in these tightly coupled loops here on these supercomputers. We believe that tomorrow there'll be these workflows that are distributed throughout, not just on these supercomputers, but also on other supercomputers in the cloud, managed services, colos. So programmer productivity will be much easier because they can simply invoke these workflows that are already running somewhere, possibly close to the data, possibly close to the accelerators that are available only on that site. So through that, we would enable much better programmer productivity. Because it has to be invoked remotely, we also enable seamless scalability and fluidity of these programs. And then finally, if you think about performance efficiency, earlier these programs, workflows were taking over the whole supercomputer. Today, as you have many more smaller workflows that are invoking on these kernels, you can really package them much easily and you can taking the analogy of, a jar where you can put the stones, you can put pebbles, you can put sand, you can fill this jar much more efficiently than only if you put the stones in it. You can maybe put 2 stones, but here you can put, I don't know what, 6 pebbles and a lot of sand. I'd like to read this. This is a really important statement for us, that we're striving to enable this workflow optimized heterogeneous serverless architecture, which is inclusive of, compatible with the public cloud for a set of workloads that is broader than what the public cloud can support. Today, public cloud is usually exporting these VMs, or they export also some sort of bare metal where you can get dedicated cluster, but they don't necessarily export the high performance computing yet. And that is what we are aiming at. And we would like to deliver it as a service, as a colo, or as supercomputing centers, whatever our customers want. So what are the types of use cases that our customers have? So one example is cross-site medical data sharing. And I think this resonates very much with what Rina was talking in the introduction, and then also Professor Dr. Deepa Shenoy. There are data lakes that store all these data, but then there are many sources of data, like genomic data, clinical data, laboratory data, imaging data. And these sources of data are really going through workflows. So you first collect either genomic data or clinical data, lab data, imaging data, then you do some sort of local processing because you want to reduce that amount of data. Then you do genome processing, you do local storage of these, you do visualization, then you do data integration, data cleanup, data analysis, visualization. Some of these are very specific to individual type of data, but others could be generic. If you, for example, do cleanup, it could be almost applied to any, or data integration. Now, what we do is to enable programmer productivity, we can dynamically create these workflows and connect these functions that are exposed here. We can also seamlessly scale these. Sorry, let me go back. We can seamlessly scale them because we can just replicate these data integration functions or data cleanup or data analysis, etc. And in order to gain better performance efficiency, we can conveniently combine complementary functions together. So, for example, those that don't pound on data caches, or they're very active in terms of CPU. So you can put them together and combine these patterns. So we believe that we can offer a number of benefits to customer, like remote invocation, distribution, federation, utilize heterogeneous. We can address stay latency, security with hardware authentication. We can do billing optimized for finer granularity operations, which are all the pain points that they do have today, whether they execute on supercomputer or in the cloud. There are other examples of use cases. I don't really have too much time to address them all. Additive manufacturing is an example of heavy edge. We have similar workflows that could be built, and we have many users there. We have from materials designers to artifact designers, manufacturing engineers, and even digital twins that can interact with all these functions. Another interesting use case is another light edge is wildfires prevention, where you can similarly have, very similar to the first use case, different sources of data like sensor data, satellite data, airplane data, phone data, etc. And then we can follow the similar models that we discussed earlier. So what do we actually do? I was talking about motivation, really, not about what we actually do. The actual work that we do is comprised of a number of technical areas. So we first start with use cases and applications. I showed you some. We are addressing programming models for heterogeneous accelerators in order to make it easier for developers. We are using existing frameworks. There's a few of those that are already working for high performance computing. Examples are FunkX or RFAS. One is from University of Chicago, the other from ETH. We've been exploring both. Then we're doing billing and metering and performance application prediction, which is really important for delivering on these functions. We are partitioning network to enable quality of service. We do all kinds of optimizations of the hardware architecture where we are deploying in SmartNIC all kinds of near memory compute accelerators for various data operators. And then we do security instrumentation control applied to these, and finally resource scheduling. And there's a bunch of other important areas, but these are our major 8 areas. So what kind of critical research questions do we need to address? And I think this is one of my last slides to motivate both developers and researchers. So for us, probably the most important one is how to improve ease of use for programmers. How can they take these existing workflows and then compose them and make them more dynamic and complex? How to engage and empower developers is function as a service, the third missing programming model. Some people think that it's task programming, which is actually workflows, but we take it as a given. Or is it something else in addition to MPI and Pmem or PGAS? And then how to increase ease of system deployment and provisioning. For seamless scalability and fluidity, what are the billing algorithms that are optimal for the intersection of as a service and HPC for serverless? How to guarantee tenant application security, performance, isolation at scale. This is really important for all providers. And then how to extend common secure design across cloud and edge. Because either of them might be secured, but how do we extend them? How do we do end-to-end security? Because if we don't trust the data, we won't trust the outcomes. And finally, for performance efficiency, which is important for providers, be it in supercomputing centers or Green Lake, like in Hewlett-Packard Enterprise or cloud providers. Some of the key questions are how to provide performance guarantees. Are serverless really viable for high performance computing as a general tool, or are the costs too high to start them off, to switch them when you compose these complex workflows, etc.? How to improve efficiency or minimal resource allocation? And finally, can the techniques apply to high performance computing, data analytics, and AI be equally applied to general data centers to compute, storage, edge problems that you are dealing with every day? So this was my talk. I'd be delighted to answer questions if you have any.
Thanks a lot, Dejan, for the wonderful session. So what interesting was the reuse of this architecture on the serverless architecture on the general purpose systems now, which was one of the questions. So could you please throw some insights that would really help us?
Well, I think in the serverless is already being used in general purpose tools, but it is used on CPUs primarily. They are not as much used in serverless. We always thought that there's serverless, there's accelerators, but there was very little combination of the both. And we felt that there's intuitively there's a good match between the two. But it's tricky to accomplish it. And if we can apply it and do research in high performance computing and data analytics where accelerators are already used, then potentially we can also take these approaches and just use them for general purpose computing. Today, accelerators are used primarily for inference or for training. They are less so used for other types of applications. So I hope that answers your question.
Thank you.
And thanks for asking, Santosh.
Thanks a lot. It was my pleasure.
Rina, do we have any questions from other groups that are coming online?
Not as of now. We are still looking into it. Just give us a moment. If there's anyone who wants to ask question, you can leave your questions on the chat box and we'll take it through from there.
I think there is one on the chat.
Yeah, Dian. So I see one on uh, chat. Probably Amit, you want to go first, and then we can take the question on the chat.
Okay. Hey, great talk. Very excited to hear about this. So I personally also work in a lot of this multi-heterogeneous technology, and a question which is not directly relevant to the talk, but in your experience, do you believe that our undergrad computer science curriculum is well suited to kind of churn out engineers who understand this level of complexity and heterogeneity?
First of all, I think that our students are extremely capable. And when I say students, I think in India, America, Africa, South America, China, Australia, any country literally in the world. I've spent last year and a half conducting some panels in 10 regions of the world where I felt there was a growing marketplace. And I invited people from industry, academia, and government. And people over and over solicited answer to your question. They're saying that curricula is not sufficient in academia around the world. Perhaps in the United States it's closest, but in places like South America and even China for other reasons, in Africa, the curriculum was way behind. And that was very obvious because the professors haven't been trained. I cannot speak for India. We held the session in India as well. But I think that we can never over prepare students. They're extremely capable. The more we can teach them, the better. But in order to teach them, we need to teach the professors first. And it was very obvious to, and this is not criticism to professors, but it was very obvious that a lot of professors were unprepared for the COVID when they were supposed to teach remotely. And because especially those who are at the end of their career, it's not easy to, I mean, it's hard for me to understand all the concepts. I mean, I worked with India team in HP on development of a new processor, new dot product engine accelerator, and it took me a while to understand it. And you can't expect professors at the end of their career to just pick up like that the new AI concepts and all that. So what I'm trying to say is we need to invest. So this is not criticism of them. It is a solicitation. It's a call for governments and industry and academia to work together to be able to better educate young generations. Because I think your question was very important, Amit.
Thanks, Dian.
And we have a question from Dibakar. The question is your views on the challenges scheduling across heterogeneous processes, accelerators, and memories. And do you see any need for standardizing the programming models?
Yeah, that's one thing we've been working together with a couple of universities, especially UIUC, and then with University of California at Irvine. This is all generation of students, PhD students, and graduate students from Professor Wenmei Hu. I think that for me, and as I was pointing out, if you try to solve problems with scheduling, I think it's a little bit too late. It needs to be done even earlier, which I believe you are hinting at the programming model level, because if you can take care of optimization in an automated way, then it's much easier to do the scheduling at the runtime. And that's how we look at it. But then on the other hand, as you know, people are now more and more going towards Python and using it. So the things are getting abstracted at a higher and higher level. I think the frameworks and tools like TensorFlow and others are taking over. So the scheduling is usually done at the lower levels. But I think for me, ideally, things should be done at the programming model, and then because it's not just scheduling, it's optimization of the things that is hardest. thanks for the question, Deepak.
Thanks a lot.
So with that, we don't have any other questions on the chat box, but we still have 5 minutes. Santosh, do you have anything to ask?
Well, no, none from our side.
Okay, well, you
Well, on
can on
that.
to the next topic.
Actually, I will ask another question. Just from your own experience at HP Labs, how does HP Labs go through kind of training their own employees, because these technologies are evolving very fast, right? I mean, and there's a whole lot to learn.
Yeah, everyone takes ownership of herself or himself. You know, we just all learn on the seat of our pants, as they say. We also work with universities a lot. The most you can learn by doing. So that's how you learn. You go ahead and try technologies and then build upon it. We also do a lot of things cross topics. We make sure that we, for example, have not only software and hardware teams, but we have also device teams who produce devices, who produce materials. We work all together and then try to accomplish these end-to-end solutions.
Fantastic. Thank you. Thank you so much, Dian. It was lovely having you with us. Do we have any more questions from anyone? We'll give you a moment there. We still have 3 minutes.
Yeah, there
If
was
someone has
Deepakar's
a
question about Python seeming to consume a lot of power. Any thoughts on power consumption? I think power consumption is, or the general notion of sustainability seems to be one of the most intriguing topics as of now, and people are looking at it really holistically. I can't speak about Python. I haven't done those experiments, but I know that people are dissecting literally everything, and that includes they even call it cradle to cradle. So it's not only how you use the program, but how much energy has been used to produce that computer, to bring it, how much power it used, what kind of power was used, how you're going to dispose of that computer. So really holistically everything. And various companies are making statements of becoming energy neutral companies by certain years, 2030, 2040, 2050. I think IT is probably the easiest target because you can measure it most and easiest. As soon as you get into governance, regulatory compliance, it's much harder. It takes much more effort. So I think IT is leading. We do IT for sustainability, pursue these efforts. But we have been doing this for quite some time in labs. I remember 10 years ago, we have a cloud sustainability dashboard where we tried in the cloud to break down how much power is used for any service invocation. At that time, it wasn't as interesting, so that project came and went away. Now it's coming back. And we had also net zero data center, meaning we had we put that was 10 years ago. We put the batteries on the roof. We're in California, so there's a lot of sun, like in India, and whatever energy we created, we were using for data center. We were moving things around, doing all kinds of optimization. Now it's getting even much more advanced. By now, I also think I used up all my time, so I should probably stop.
Thank you. Thank you so much, Dian. And Dibakar is thanking you for taking time out and answering to all his question. And thank you for joining us here today. We had a splendid time listening to you. Thank you so much. We'd like to move ahead to our next session. Bye-bye. Thank you. We would now like to move ahead to our next session. The next session is on building storage systems for new applications and new hardware. And this is led by Professor Vijay Chidambaram, University of Texas, Austin, and VMware Research. We've been waiting for you, Vijay, and the virtual stage is all yours.
Thank you, Reena. So hi, folks. My name is Vijay. I'm from the University of Texas, Austin. I also work with VMware Research. And today I'm going to talk to you about my group's efforts over sort of like the last 5-6 years about how to build storage systems for emerging technologies and applications. So let me share my screen. Okay, I'm now the presenter, so I should be able to do that. Let's see. Right, are you folks able to see my screen? Okay. All right then. So let's get started. And please feel free to interrupt me at any point of time and ask questions. Right. I would like this to be as interactive as possible, and I can speed up and slow down based on like the question. So that should be fine. Okay. All right. So let's get started. So this I think is like a little like preaching to the choir here, but like storage services today really are like the bedrock of like all the different things that we do, right? Whether we are watching videos on Netflix or we're playing games on the mobile phones, using traditional key value stores, databases, storage services really are the foundation on which all of this is built. And designers of storage systems today face new challenges that they have not faced before, right? So one of them is new hardware. So we have persistent memory from Intel that came out in 2018. We'll be talking more about that today. There's DNA storage that's on the horizon. University of like Washington is working on this. University of Southampton is working on this with Microsoft Research. There's also Project Silica, which aims to actually write your data into small pieces of glass. This is again a Microsoft Research collaboration. So there's lots of like new and interesting sort of like media that's coming out. And if we look at sort of like the history of storage, right, for a very long time it was like tape, and then it was like like magnetic hard drives, and solid state drives were really the most exciting thing recently. But now if we look forward, there's so many different media that's coming out, and these all form challenges for storage system designers, right? How do you build good storage for like DNA? How do you build good storage for silica? So there's challenges there. There are also new applications that are coming out, which put new stresses on storage systems, right? The sort of like the ones I have here, two of them at least are like stereotypical, right? Like we all know machine learning, for example, is like putting stresses on a lot of different systems, including storage. And I'll briefly talk about this later today. Blockchain, for example, is putting a lot of stress on the storage system. New privacy regulations like GDPR from Europe is putting stress on the storage system. So these are all like new ways in which the storage system has to adapt to sort of meet these challenges. We're also having new metrics that we are concerned about, right? So for example, if you take solid state drives, after you write to them a certain amount of times, they get bricked and you can't use them anymore. So you have to buy new devices. And when you think about like tape and like magnetic hard drives, there isn't this factor, right? Most of the things that we are so the devices that we are manufacturing today do have limited lifetimes. So how do we get the best out of the device before it reaches its end of life is another question that we are concerned about. So my group at UT Austin tackles these challenges, and over the years we have worked on a number of related projects. We worked on like storage reliability, like how do you build like reliable storage systems. We worked on distributed storage systems, write optimized storage. So this is basically if you have an SSD, how do you minimize the IO write IO going down to the device so that it lasts longer. We have worked on storage for like persistent memory, and I'll talk more about that today, and for machine learning and for the new regulations. So this is like a lot of just giving a flavor of my group's work, and I'm happy to chat about any of this offline if you'd like to. But in today's talk, I'm going to be focusing more on like three projects: storage for persistent memory and storage for machine learning. Okay. All right, so let's sort of like get to it. So persistent memory is this new memory technology from Intel appeared in 2018. The interesting thing about this is that Intel has been saying it will release persistent memory for a really long time. Like when I was in grad school, I remember that the next year would be when like Intel would release, and it kept getting postponed until sort of finally in 2018 it sort of came out. So this is it's connected directly to the memory bus, so it's kind of like DRAM in that way, and accessed via processor instructions like loads and stores. Once again, similar to DRAM. And if you look at sort of like the performance profile, reads have slightly higher latency, writes have similar latency, but if you look at the bandwidth, read bandwidth is 1/3 and write bandwidth is 1/8. So one way to think about persistent memory is it's a very bandwidth constrained, slightly higher latency version of DRAM, right? Now, part of the reason why people are really excited about persistent memory is one, because it has durability. So even if you lose power after writing something to persistent memory, when you reboot, it's still there. So it gives you like very quick restarts. So that's there. And also it's very dense. Like you can put about 6 terabytes of persistent memory in a single laptop or a server class machine, and it consumes less power than DRAM. There's no periodic refresh cycle required. So all of these factors together make persistent memory a very exciting technology, and my group is working on how do you build effective software for this technology. Right? And so what there are two lines of work roughly here. So one of them is like, how do you build data structures for persistent memory? And this may be like a weird question because, like, when we think about storage, we think about like databases and key value store, not data structures, right? This aspect comes through for persistent memory because it's like DRAM. Like just how you build a hash table or a B tree in DRAM, you can build similar data structures in persistent memory. We want it to be concurrent, so depending on regardless of how many threads accessing the data structure, we wanted to give high performance. We wanted to be crash consistent because now persistent memory is durable. So if you lose power and you come back up, you want the data structure to be in a consistent state so that you can recover and use the data that's in there. There's been lots of work, like very good work along these lines. Another sort of like slightly orthogonal question we're tackling is how do you build file systems for persistent memory, right? The sort of like most common system software used to access storage devices is one is databases, one other is file systems, right? So how do you build highly concurrent, efficient file systems for persistent memory? And again, like there's been like somewhat recent lines of work, like from BPFS in 2009. But if you really go back, even like in the 1970s, people are thinking about like how do we build file systems for persistent memory. Only then, like you didn't really have a persistent memory at that point of time. So only now, with persistent memory actually commercially available, do we actually get to really build these things and see how they play with the unique characteristics of like persistent memory. So I'm going to first talk about the file system project, and then I'm going to talk about the data structures project. And again, like feel free to interrupt me and ask questions at any point of time. All right. So first, let's get into the file system project. So what we're doing here is we're taking the various open source file systems that are available for persistent memory, both research and industrial file systems, and we're doing a very simple operation. We have a file, and we're going to append 4 kilobytes to that file. Okay. So what this graph is showing you is on the x-axis, we have the different file systems that are used to do this operation. And on the y-axis, we have the time taken in nanoseconds. So the first thing we can see is that if you just write 4 kilobytes to the device, to the persistent memory device, that takes about 700 nanoseconds. Okay, so that's all it takes. But if you do the same operation via ext4 in the direct access mode, it takes 9,000 nanoseconds, about like 12 times higher, right? So this gap between what it takes for the device to do it versus what it takes for the file system to do it is what we call the software overhead. And really, if we have this high software overhead, you are wasting the low latency of the device, right? The device can actually do the 4 kilobyte append in like under a microsecond, but we're taking about like 9 microseconds to do it. So we're wasting the low latency of the device. If we look at different research file systems like Strata, Nova, and PMFS, they do better than ext4 DAX, as you would expect, because ext4 was not really designed for persistent memory, whereas these file systems were. But they still have like high software overhead. Like Strata, which is the best of the bunch, it takes about 2.5 times the base device latency to do this append. So the question is, can we do better, right? Current PM file systems have high software overhead. So how do we decrease the software overhead of file system operations? So that's a main question that we're tackling here. Okay. And the basic idea behind it is actually like a very old idea with a slightly new spin on it. And the idea is we're going to handle operations in user space. We're going to split our file system into two parts. We're going to have a user space part, and we're going to have a in-kernel part. We're going to handle the user data operations, like like reading a file, writing a file. We're going to do that in user space. We're not going to trap into the kernel to do that. And then for metadata operations, like file renames, file creates, stuff like that, we're going to trap into the kernel. And not only are we going to trap into the kernel, we are not actually going to build a custom software layer. We are going to just use ext4 to handle the metadata operations, right? So this is a very unique design, I would say. And this is also collaboration with a bunch of folks from Georgia Tech that we did it with, and Ashish, who used to be at like Penn State and now is at Google. Okay? So again, to reiterate the central idea, like we want to handle the user space operations from, handle the data operations from user space without trapping into the kernel. We're going to route the metadata operations into the kernel and use an existing file system to handle it. Why this particular design? So if you look at the storage operations, right, the data operations are relatively simple. So reading a file, writing a file, and by writing, I mean like updating a file in place. These are all like, fairly simple operations. Metadata operations are significantly more complex, right? So back when I was in grad school, we did a piece of work where we looked at like the POSIX metadata operations and how different file systems implemented them. Lots of corner cases, and it's very hard to get it completely right. So that's there. And also, like if we look at like most workloads, they are data intensive. Like if you think about something like RocksDB, for example, right? Most of its time is actually spent on data operations. So the bet that we're making here is we are going to speed up data operations because we're not dropping into the kernel, right? We will take a hit on the metadata operations because we're dropping into the kernel and we're using ext4, which is like slow and not really designed for persistent memory. So that's going to be slower. But because the data operations are so much more in the workload overall, we believe that in sum, this is still going to accelerate the workload without having a lot of implementation cost. So that's the bet that we're making. So if we look at the architecture of like SplitFS, right, and we look at like how persistent memory file systems have been designed over the years, there's really a spectrum. And at one end we have ext4, PMFS, and Nova, which are all entirely in the kernel. If you want to do data operations, if you want to do metadata operations, you always have to trap into the kernel. At the other end of the spectrum, we have things like Strata, where everything is in user space. It's a completely user space file system, so you never have to trap into the kernel, right? So this is great. And if you look at the trade-offs between these two things, right? So doing everything in user space gives you very high performance. You don't have to trap into the kernel and all the overheads that come associated with that, but you have high complexity. You end up basically re-implementing a lot of the stuff that's already in the kernel. Like for example, like the VFS layer, the implementation for all these sort of like many different like metadata system calls. You have to do it all yourself. If you look at the other end of the spectrum, where everything is in the kernel, you get to reuse VFS, you get to reuse a lot of stuff that's already in the kernel. So the complexity is lower, the implementation complexity is lower, but you also have low performance because all the time you're actually trapping into the kernel. There have been like interesting designs in the middle, like ARE, for example, from Wisconsin-Madison. And ARE's sort of like goal was to say that every application that is sort of like writing to persistent memory should have a different interface. Why should everyone have the same POSIX interface? And so it allowed different applications to use persistent memory via different interfaces. Because focus was not really on performance, so it has like low performance, and it has like sort of like medium complexity because you still have a software layer inside the kernel, which is responsible for giving out like big blocks of ranges of like persistent memory, right? And so this is where SplitFS sits in the spectrum, right? We have high performance because we're not trapping into the kernel for like every operation. We have low complexity because we're able to reuse ext4 for all the complex metadata operations. So this is roughly what like SplitFS looks like. I'm not going to spend a lot more time on it, but like just to give you a flavor for what it looks like, there's a user space component which we have creatively called usplit. There's a kernel component which we call ksplit, which is really just ext4 DAX. So whenever you're doing read and write system calls, the ksplit is not involved. Like it doesn't trap into the kernel. It just goes directly from the application to our library to persistent memory. Whenever you're doing metadata operations, it goes to our user space library, from there to the kernel, down to persistent memory. We also keep a log on persistent memory so that we can provide properties like atomicity of system calls. So in summary, right, SplitFS accelerates common case data operations by leveraging the maturity of ext4 DAX for metadata operations. It uses logging and out-of-space updates for providing strong properties like synchronous atomic system calls. So if you want to do that, like SplitFS can actually help you do that. And SmartNIC has different modes. So strict is the mode where all system calls are atomic and synchronous. So the minute, or like I guess like the nanosecond that the system call completes, then all the data that is associated with the system call is now durable and will survive a crash. So if we go back to our the experiment that we had before, we are once again appending 4 kilobytes to a file. And what we can see now is that SplitFS strict in its like strongest property mode, it takes about 1250 nanoseconds. So about like 80% overhead versus just writing to the device, but the cost is lower than writing another extra 4 kilobyte block, right? So the cost is like about 80% of like writing the same block twice. So we have reduced our overhead down to like less than 100%, which is sort of like like what we were aiming for when we started. We're still able to provide strong properties like atomic synchronous operations. So let me see. There was a question on chat. Let me see how I can get to chat. All right, so let's see. So the question was, is there any part of the metadata leveraging the persistent memory in SplitFS? So like the log that we are writing, for example, right, that can be considered, I guess, like part of the metadata. And that is really, it's only possible because like we are able to do direct operations to persistent memory, right? If we did the same log idea in like SSDs, it would be much slower. So we are using some of the unique properties of persistent memory to provide these properties. In terms of like, we are using ext4, right? That doesn't actually, it's not super tailored to persistent memory. And we're using ext4 because like, it's actively developed and like, like it's very mature, but you can replace ext4 with any file system that you want. Hopefully that answers your question. All right, cool. So let's continue. So I'm going to skip all of this. Like, so if you're interested, please see the paper where we have experiments like showcasing how SplitFS works in a number of like different scenarios. And SplitFS is open source. So most of the work in my group is open source. So you can check it out and you can build it. And like, if you have a use case where SplitFS would make sense, please reach out to me. We are very happy to help you set up SplitFS for your use case. All right, so with that, we are finishing up sort of like that part of it, and we're now going to talk about the concurrent data structures part. So I have about, I would say like, 10, 15 minutes left. So I'm going to be like, kind of quick in the other parts of the talk, but feel free to sort of like ping me. And I'm happy to chat offline about any of these words. Okay. All right, so let's very quickly look at this, right? So how do you build concurrent data structures for persistent memory? So that's the goal here. And by data structures, we mean things like hash tables, B trees, stuff like that. We want these data structures to be concurrent to allow access from multiple threads, multiple cores. You want it to be crash consistent. If you're doing an update and you crash, when you come back up, data structure must be in a recoverable, usable form. We also want it to be cache efficient, right? So the way persistent memory is accessed is that it's brought into the CPU caches and then the data is sent to the thread. So it goes through the caches. So we want it to be very cache efficient, right? So concurrency is a hard problem. Crash consistency is a hard problem. When you combine these two things, you get like bugs. So it's kind of inevitable. So if we looked at sort of like the state of the art data structures like fast and fast, CCEH, for example, we found bugs in both of them. Serious bugs that lead to data loss and corruption. So the question that we asked ourselves here is, we have done like decades of research, right, on DRAM data structures. Can we use that research somehow to build data structures for persistent memory? To make the question more specific, is there a way to convert existing finely tuned, mature DRAM data structures into persistent memory data structures? So that's what we're looking for. And the basic insight in doing this conversion is that if you look at isolation in DRAM data structures, so these are all like concurrent data structures, you can use the mechanism that they have for isolation to provide crash recovery. So this is sort of the basic high-level technical insight that powers this work, that isolation in concurrent DRAM data structures can be reused for crash recovery in persistent memory data structures. So you may be wondering, like, how, this doesn't make any sense. Now, we are not the first to provide this insight, right? The folks from Michigan, for example, have already done this, but this is how it works. So if you have isolation, right, in a data structure, like what is it actually ensuring? So it ensures that if you're doing writes and then a concurrent read is happening, the read still returns the correct value. Like it returns whatever is sort of like based on a consistency level, the latest data or the version before that or so on does not return some sort of like in updated partial version. Right? Crash consistency, on the other hand, ensures that even if you crash while in the middle of an update, when you do a read after you recover, you still get the correct version. So you can see how like these two things are slightly similar. So the memory persistency paper from Michigan made this connection back in 2014. And what we are doing is we're using these insights or like basically power our work, right? So we're reusing the isolation mechanisms in DRAM data structures for crash recovery. So let me give you a quick example so you know what I mean, right? So imagine there is a lock-free B tree, right? So we are not going to take a lock whenever we are performing reads. So in the leaf of this B tree, we have like 1, 2, and 5, and there's an empty slot. And one of the threads is updating, like this particular leaf. And so, like the way it's going to do this update is it's going to copy over what it currently exists. So, like it first transforms it into 1, 2, 2, 5, and then it transforms it into 1, 2, 3, and 5. So 3 is the value that's being inserted. Now, a reader, because it does not take a lock, right, may actually see this partial state. It may see 1, 2, 2, and 5. What happens then? The reader has smarts built inside it to return 1, 2, and 5 to the user. So it basically ignores the duplicate that is in this like leaf node, right? So it has some semantic knowledge of like what is contained within the node. It can ignore duplicates and return the correct data to the user. So basically, the reading thread, the reader detects and tolerates duplicates, right? So that's what is really going on here, right? Now, in the same way, if the writers also don't hold lots, another writer may see this, right? So it may see this partial state. Now, if the original writer had crashed for whatever reason, the second writer will restore the data structure back to its previous state. So it will basically remove these duplicates, right? So the writer is able to detect and fix inconsistencies. And it turns out that this is what you want in a crash recoverable data structure. You want readers to detect and tolerate inconsistencies. You want writers to detect and fix inconsistencies. And the inconsistencies in this particular case, they happen because the thread crash due to some reason. But really, if you have a power loss crash and the whole thing goes down, you end up in the same state. Right? So in the paper, we have talked about different kinds of data structures. We classify data structures based on like how they do reads and writes, and we show how to fix, how to convert them from the DRAM version to their persistent memory version. So let me issue just like one type, and then we'll quickly move on to the rest of the talk. So here's like a type 1 data structure, all right? And the way updates are done in this particular data structure is you make a copy of the leaf node, and then you do the update in the leaf node, and you atomically switch a pointer, right? So in the storage world, this is copy on write. So the data structure is using copy on write to atomically update its nodes, right? So if you have data structure like this, right, which is using copy on write to update its nodes, it turns out that the only thing we need to do when we take a DRAM data structure and we place it on persistent memory is that we have to ensure that after the pointer switch happens, that the data is properly flushed and fenced. Okay, so what do I mean by that? So it means that before the pointer switch happens, for example, we want to ensure that the data in 1, 2, 4, and 5, which is the new node, is flushed from the volatile CPU caches down to persistent memory. And then you update the persistent pointer and then you flush it. Using DRAM data structures for persistent memory would mean CPU utilization shoots up 4 to 5x. It does not actually, right? So if you look at like, it depends on like the data structures that you use to sort of like do this. So in our work, for example, we have taken like very finely tuned cache efficient data structures. It does not actually increase like, CPU utilization all that much. We are not, because we're not really doing a lot of extra work here, right? So there's really no basis for CPU utilization to increase. Right? All right, so I'm going to skip the type 2 stuff. Like, again, you can, if you're interested, we can see this in the paper. But to summarize, right? So we call this a recipe, a recipe to convert data structures. It's a principled approach to convert DRAM data structures to persistent memory data structures. And in our work, we converted 5 different data structures like hash tables, B trees, radix trees, adaptive radix trees, and so on. And what we found out was that in most of the cases, the conversion required less than 200 lines of code, right? So you take this big data structure, you only change 200 lines of code. This was like in all cases less than 9% of the total code. In some cases, it's like less than like 2%. And because the data structures were like very good DRAM data structures, and we retain properties like cache efficiency, the converted persistent memory data structures outperform handwritten persistent memory data structures like fast and fair, for example, up to 5x. So if we take very good DRAM data structures and we convert them in this way, we get very good persistent memory data structures. The really nice thing about this is that we don't have to write these things from scratch, right? Developing good DRAM data structures is like very hard and takes like many years. So people have already done this for us. So we are able to take all that work and just add on what we need to ensure that it works correctly for persistent memory. And recipe is again open source, and we have like 5 different data structures. And we talk about like how which data structure is good for like which case. So if you are looking for persistent memory data structures, please let us know. We'd be very happy to sort of help you do this. So let me sort of quickly talk about one of the themes of my work, right? Which is like we want to reuse existing code. So we want to use existing software artifacts to solve new research problems. And we saw this both in SplitFS, where we're using ext4, and in recipe, we're using existing DRAM data structures. So, and the reason that I really like this approach is that it makes it easier to deploy these things in practice, right? It helps to adopt these things, because if you're like, I have developed a completely from scratch persistent memory file system, people are like, hesitant to adopt it. But if you say, I have something in user space that sits on top of ext4 and helps you accelerate your persistent memory application, people are like much more willing to try that. And doing this requires a lot of careful innovation, right? You want to make sure that the thing that you're reusing, you don't lose the good properties of that. So when you transform the data structures from persistent memory, from DRAM to persistent memory, we wanted to keep things like their high concurrency, their cache efficiency, and so on. And doing this requires like very careful thought and innovation. So I just want to there's one more slide that I'm going to quickly go through, and I'll actually sort of end on that. So let me actually get here, right? Look, okay, this is what I want to head on. It's a very exciting time to be a storage systems researcher, right? This has not always been the case, but it is now. We have new storage devices, we have new applications, which make it very exciting. And my plea for people listening to this talk is to try and use existing software artifacts to solve these new research challenges. And doing this may require, collaboration with theory folks. For example, for recipe, we had to collaborate with theory folks. For other work as well. And if you do it right, it's actually very exciting and enjoyable. So with that, I'd be happy to take questions.
Thanks a lot, Vijay. Thanks a lot for the insightful thought. So the first question we have is from Rajesh. So this is on SplitFS. So the question is, with data and meta operations are being split between the U layer and the K layer, so what are the challenges, or what is the challenge we are facing with the atomic updates, like file M time changes or file property changes?
It's a very good question. So I think like broadly, right, the question is if we are going into the kernel for every sort of operation, we're able to update all of these metrics for every instance, right? But if for data operations we're not going to the kernel, like what can we do? So there's like 2 answers to this. So first, if the application requires these sort of up-to-date metrics, but like no other application actually requires it, it's like within the same process, we can maintain it in user space and return it to the application, right? So we have the log, so we do keep stats in user space, so we can keep stats like when was the last file last touched. So every time you do an fsync, for example, we propagate that information down into the kernel. Otherwise, it stays in user space. Now, this does not work, for example, when 2 different processes are trying to access the same file. Because like one process may have touched it, the other process does not know about it. So in this case, you do want to actually route everything down to the kernel, and SplitFS is not a good fit for such use cases.
Okay. We have another question from Shupratam. So this is regarding the DRAM data structures on the Pmem. So the question is, have you observed that usage of data structures on the Pmem increasing the CPU?
No, like, so let's see, right? So basically, like, I think the key point is that even though, like, like if one thread is doing some work and crashes, another thread is finishing this work, this is very rare. And the work that was originally going to be done by the original thread, we are now shifting it to the second thread. So overall, we're not increasing the total amount of CPU work that is being done, and this is why we don't have increased CPU utilization.
But in terms of fixing or the readers fixing the structure or the writers fixing the structure, don't you see that we would be involving more CPUs in it and eventually aging up the PMMs as well, much faster?
No, so because like it doesn't happen on every thread, right? So let's imagine that there was a one thread writing and then like three threads trying to read it, right? In some data structures, like readers threads don't actually fix anything. Like they're just going to tolerate this read. And if you look at like what they're reading, they're going to be reading the same cache line. It's just that they're going to be ignoring the duplicates in them, for example, right? So the writer thread is going to be fixing it. Let's say there are many other writers that want to do that. Only one writer will do the fix, not all of them. So original thread before it crashed was trying to do it. Now after the crash, like one other thread is going to complete that work. So not all the writers face that extra CPU work.
Okay. We have a question from Umesh Pelaru. So what's your take on dynamically tuning the selective use of the Pmem or the PM or the accelerator based on application need?
Yeah. We have a project in our group where we are working on this. So I think like more broadly, right? We now have a lot of like heterogeneity even in our storage stack. We have DRAM, we have persistent memory, we may have GPUs on the machine. And so the question of like, how do we use all these things together for the application at the current point of time is very interesting, right? And in my group, like for example, we are trying to build a distributed storage system that like works with this mix, but it's really very application dependent, right? Like there's no one sort of like answer for the whole range.
Okay. The next is from Ravi with Intel EADR feature. The fence and the fence and flush is still required.
Yeah, that's a good question. So EADR will make the persistent domain right up to the caches. So whatever you're writing into the caches will no longer actually require the flushing. We might still require fences if we want to control the order in which it's made visible to the other threads. So we'll still need fencing for that, but it will make persistent programming much simpler.
Great. Thank you. Well, one question from my side. So with the changes from DRAM to Pmem, we already see that the industry is having a lot of software changes that are coming up. And the new and upcoming features like the DNA storage or the silica or the quartz. So do you see again a sort of a revamp into the whole storage software, or are they also thought into the new architecture as we are coping ourselves with PMEMs?
So I believe there will be like phases, right? So like I think like one phase will be where we'll be using existing software and storage stacks and so on. And sort of like some of my research helps in this transition, right? So we have not yet developed like new architectures and so on for persistent memory in the stack, but we still have applications required to use this. So we have this sort of like intermediary phase. And after this is done, I do believe like 5 years down the line or 10 years down the line, we'll actually have like new architectures which are going to be like purpose built for persistent memory and our heterogeneous architectures that we'll be using.
Great. Thank you. Thanks for answering the question. So the last question we have from Ravi. The question is the small read writes, that is, which are less than 256 bytes on PM is not efficient. So directly using DRAM data structure will waste the bandwidth. So what is your thoughts on this?
Yeah, that's a great question, right? So you're right. Like, if you're doing very small writes, then it is going to actually waste your space. But most DRAM data structures, if you look at them, right, they have tunable node sizes. So you can basically do a config change to say, like, I want my nodes to be like, 256 bytes or like larger. So that is not really like a big change as far as like the data structure goes. And in our case, like like what the data structures that we are looking at, right? We are not actually it's more latency bound rather than bandwidth bound, right? So if you're like having like a high throughput, like like a highly concurrent metadata index, we are not hitting anywhere close to PM bandwidth, right? Because like you're all doing like very small operations. You're totally right in that because we're doing the small operations, we're not hitting the PM bandwidth. But metadata operations, by their very nature, are very hard to get the full bandwidth of the device because it's more about small operations which are like latency sensitive rather than like very large operations where we can actually get the full bandwidth of the device.
Great. Thanks a lot for taking the questions and answering them. Back to you, Rina.
Thank you, Santosh. And thank you, Professor Vijay, for taking time out and joining us here today. The session was knowledgeable, and I'm sure it has helped a lot of them out here. Thank you so much for your time. Thanks a lot.
Thank you. It's my pleasure.
On that note, we'd like to move ahead to our next session, and this is towards failure, recoverable, and secured persistent memory systems, which is led by Sihang Liu, research scholar, PhD, University of Virginia. Over to you.
Can you hear me?
Looks like you're, yeah. Yes, we can. We can.
Can you let me share the screen?
You will be given the presenter rights now.
Oh, perfect. Thanks. Seems like I don't have permission. Ah, now it works. So, get started. So, are you seeing my presenter? I mean, okay, perfect. So, hello everyone. Thanks so much for inviting me for DSS. I'm Sihang Liu, currently at the University of Virginia, and I'll be joining the University of Waterloo in next year as assistant professor. So today I'm happy to talk my research during my PhD work that is towards failure recoverable and secured persistent memory systems. So, in this theme of DSS, I guess everybody knows that we have huge demand for memory and storage, like all kinds of workloads running in the cloud, such as data analytics, databases, and in-memory caches. All those things have something in common, that is, they consume tremendous amount of memory and storage. For instance, a study at Google Cloud Workloads has shown that all those workloads are bounded by memory and storage. Like more than 56% of the time is due to pulling data from the backend of memory and storage devices. So for this reason, the next talk I'll be focusing on solving the bottleneck on the memory and storage side. So let's see what we have today for memory and storage technologies. On the memory world, we usually have DRAM. And on the storage, it is a volatile, low capacity, high cost, and fast type of memory device. And on the storage side, we have hard drives and SSDs, which have exactly the opposite properties. That's persistent, high capacity, low cost, but much slower. Because we have to play the trade-off between those features. It's very hard to get benefits from both worlds. And now, persistent memory is here. Thanks so much for the previous talk from VJ to introduce the persistent memory, so I don't have to introduce everything again. So persistent memory is coming with all those good features from both worlds. So persistent memory unifies memory and storage devices. For example, Intel has already delivered the Optane persistent memory like this. From the shape, you can tell it's installed to the memory bus and can actually be installed next to the DRAM devices so that the applications can directly utilize the high performance features and data persistence. Since persistent memory takes advantages from both tiers, from both the memory tier and storage tiers, the question now is, how can we build a system stack for persistent memory? How does that look like? We know in the conventional system stack, we have applications, the operating system, the processor, connected to the DRAM and SSD in the bottom storage and memory layer. To perform these normal accesses from the applications, they can just use load and store instructions to gain fast access to the DRAM. But for applications that deal with persistent data, they typically go through the file system indirections and then use I/O to access data stored on SSDs. This is actually making the data path to access the persistent storage much slower. And now we have persistent memory, right? It's unification of both tiers. Then how would system stack look like? It's actually allowing applications to perform load and store directly to the persistent memory medium, so that the data path to persistent data is much shorter. So in the rest of the talk, I'll be focusing on the newer system stack for persistent memory systems. And the goal of my research is to enable better performance using the direct management feature of persistent data. But things are not always ideal. To utilize the advantages of persistent memory, we are actually seeing a system stack redesign. To leverage all the benefits, we have to have applications tailored for persistent memory, like the previous talks have shown. And also on the hardware side, we also need to design new hardware features, like adding additional hardware support to enable direct access to the persistent memory storage medium. So in such a case, we are seeing a system stack redesign on both the software side and hardware side. And my research in my PhD is all about this. That is to enable a seamless integration of persistent memory by redesigning both the software side and hardware side. So both sides can work together seamlessly. So on the software part, my research focuses on program correctness. Like we have the program with direct access to persistent memory now, it's giving us all the performance and persistence benefits. But what if system fails and data in such a direct access mode can potentially be in a corrupted state, and we don't have file system to back up us? But we still need to fix the crushed data to enable program and resume the execution. So this is adding a lot of burden on the software side to design these robust software against failures. And the problem is, what if the software is buggy? Then we may fail in the recovery, and data can remain crushed, and we cannot resume the execution. So in this line of work, my research focuses on correct failure recovery for persistent memory programs. And on the hardware side, my research focuses on efficiency and security at the same time. We know that persistent memory now has a persistent feature and is installed to the memory bus. So all the persistent data suddenly gets exposed to the outside world. Then what if we have an attacker that can potentially, say, gain access to the data? Then we are exposing all this personal data to the outside. So that we need to secure our data to provide confidentiality guarantees and integrity guarantees through all sorts of supports, like data integrity verification and encryption. But at the same time, those operations all come as a cost. That is the performance overheads. Data needs to be processed first before they are stored into the persistent memory, so as by reading from the memory. And in this direction, my research guarantees both efficiency and security of the persistent memory hardware. So here, so I just gave a very brief view of my research, and this is an outline for the rest of the talk. On the software side, I've been working on testing frameworks for failure recovery issues to detect those problems that can cause data to be unrecoverable. At the same time, I also work on test case generators so that we can drive those testing tools more efficiently to figure out corner cases. And on the hardware side, I work on efficient and secure persistent memory hardware through software-hardware co-designs, and at the same time, looking into new security vulnerabilities in existing Intel's persistent memory devices. So there are several projects here I'm listing out, and I'll be focusing on primarily two projects. So feel free to send me questions through chat, and I'll be happy to answer them through the talk. I like to make it interactive. And next, I'm going to be focusing on the software part, which is Pmem test, a fast and flexible testing framework for persistent memory programs. So let's revisit the software stack for persistent memory systems. In the conventional system, we have the application going through the file system to access data stored on hard drives, which is through indirections and making the access slower. Now we have persistent memory giving us the direct access capabilities, so the accesses become faster now. And because of the capacity advantages plus the faster accesses, persistent memory is a good candidate for storage class applications like databases, key value stores, and other kind of customized storage logic. At the same time, we also have new challenges. That is, what do we have system failures? Then when a system fails, how can we recover data properly? In the conventional systems, we have the file system to recover data for us because everything goes through the file system. But now, since the burden of managing the accesses goes to the software, then all the recovery burden also goes to the software. As programmers, we have to make sure that the program can recover correctly because it's coming with all those data management logic inside the application without file systems. So I refer to the ability to recover as the crouch consistency guarantees. And of course, as programmers, our burden suddenly increases. So speaking of programming for persistent memory systems, let's see what we already have to support cross-consistency. I summarize the support into two fundamental guarantees. The first one is data persistence. That is, writes can become persistent on demand. Like we have such a memory hierarchy over here, with the processor being volatile and the memory being persistent. Through certain instructions such as cache and write back, the program can on demand flush data to the persistent memory. So that data is being persistent, then we can do anything we want on afterward. And the other guarantee is ordering. That is, one write becomes persistent before another. For instance, we have two cache lines we want to write back. Through a combination of cache and write back and a store fence instruction, we could have one cache line written back to persistent memory first, and then go for the next line, next cache line. And as a collection, I call this cache line write back and a store fence as persist barrier, just for simplicity. So I'm going to reuse this term later on. So since we have the tools in hand, let's see how we can design a piece of code that's satisfying these cross-consistency guarantees for data structures to build on top of persistent memory. So this is a linked list on persistent memory, and I'm implementing list append operation to add a new node to the head of the linked list. And the guarantee is we want to make sure that the linked list is recoverable if failure happens anytime in the middle. And starting from this piece of code, we are creating a new node first. So after creating a node, without being flushed into the memory, it stays in the cache. And then update the new node, and finally, update head pointer. So all those three steps are same as writing a volatile linked list. But the last step is to write back everything to the persistent memory, so that, for example, we have everything down, everything persistent in the memory before we move forward to the next stage. But the programmer overlooks the fact that writes can potentially reorder. Like we have the hierarchy still, we have two cache lines representing the, say, next pointer and the head pointer. If we don't really enforce the order of write back, actually the data can be written back in a reverse order. Like say, the head pointer becomes silently evicted from the cache and it becomes persistent in the memory. Under such circumstances, we need to enforce ordering so that we won't have cross-consistency issues. For example, given such a reordering, when the crash happens at line 3, line 4, before we issue the persist barrier, the new node can be lost after failure, and our head pointer is now pointing to some piece of data that is potentially garbage because we're not writing back the data that we're supposed to. So in such a case, the rest of the linked list will be not traversable because we can't even find out the beginning of the node. So to fix the problem, we have to enforce additional ordering between these two lines through another persist barrier. So that we will have a head pointer pointing to always persistent data, either the old node or the new node. But in other cases, we can still recover the linked list. Worst case scenario, we lose a new node, but we can still get back what we used to have. So we call it a recoverable linked list. From this example, you can probably see ensuring cross-consistency is hard. Although I'm just showing a very simple case here, adding another line, we get the code work. But in real scenarios, when programs are dealing with tens of thousands of lines of code, it's not simple to figure out where exactly they need to enforce this persistent ordering. Not along that algorithms may be redesigned for the persistent memory systems. So since persistent memory program is hard, we found that using this low-level primitives such as persist barrier is error-prone. Even Intel expert programmers can make such a mistake, or Lenovo programmers that we have also studied. They make mistakes when dealing with persist barrier or some similar equivalent write-back primitives. Then one solution that people have been thinking about is to use libraries. Like Intel's persist memory development kit is a very standard library for these persist memory data structures. But so we will think that the libraries will solve all the problems because it allows even application developers who don't have the system expertise to make the programming possible for persistent memory. But actually, it's not always the case because in our study, we find that even through Intel's library, developed by Intel themselves, there are issues in utilizing their own library interface. So we have a couple of interactions with Intel folks, and these are just a few of those. We are reporting issues when Intel deal with their own library interface to implement code examples. So a summary here is we actually need to test the persistent memory programs before we can let them go in the wild and utilize them in especially critical tasks. And when designing such a testing tool, I'm seeing several challenges. The first challenge is we need to really expose cross-consistency problems. Like here, we have the hierarchy that's doing the write back in certain order using the cache on write back and store fences, for instance. But all those things are not exposed to hardware, so exposed to the software. They're all happening underneath in the hardware, like in the processor and the memory systems. Like if we have a program that's buggy, say just like the linked list before, we are missing those instructions, it may appear to work if we don't have failure at all, because we can still we can still execute properly afterward. We don't have to deal with data recovery problems at all. But once failure actually happens, the program may not work even though it worked before, because data may corrupt due to the failure, and we are losing these guarantees of persist ordering and data persistence. So in such a case, the challenge is we really need to expose those cross-consistency problems to the upper-level software. And I call those bugs that are only appearing during a crash as cross-consistency bugs. The main question is, how can we expose cross-consistency bugs since they are hiding behind us? And the second challenge is we are seeing a variety in the persistent memory systems, both on the software side and hardware side. On the software side, there could be different types of persistent memory libraries or customization of persistent memory systems that use, say, low-level primitives themselves without even relying on libraries. And those access to persistent data are through a different interface. And on the hardware side, we are seeing different types of implementation, like Intel already has a persistent memory system on x86, and ARM is planning to build their own persistent memory system, so as many other academic proposals. For example, some may use RISC-V to build their own persistent memory hardware. And those also follow different instructions and also different persistent memory guarantees. The question is, how can we cover both the software and hardware as combinations? Fortunately, we have seen similarities across those software-hardware systems. On the software side, we could have customized program using, say, Intel's library to use those x86 instructions to overcome optane memory. And there could also be customized program using ARM instructions to overcome ARM's future persistent memory systems. Although the software interface and hardware instructions are looking different, there are common features. That is, if we look closely into how software interacts with hardware, we are seeing common operations for cross-consistency, that they both guarantee the ordering and persistence, which are the two fundamental guarantees we will need to implement a persistent memory data structure. And if we can somehow expose the persistent ordering features, we'll be able to reason about the guarantees and whether the software actually meets the guarantees. And this is how it works. So my approach is to construct persistent intervals from the instruction traces collected by the software, say using binary instrumentation tools, to figure out the time interval in which a write may become persistent, so that we can deduce whether the guarantees are met or not. I'm going to talk about details later. And here I'm showing an example of a trace with the, say, the instruction collected from the software, and then build up the persistent interval for the interval of where data becomes persistent. So first it comes the instruction of a write to location A, and now we are trying to write back location A using a cache on write back and a store fence. So that interval is already closed, starting from the write all the way to the fence. So as the second location B, we are also writing to B, and now we see those two intervals are completely separated. We don't have overlapping between the intervals, so that we can say A becomes persistent always before B. And now we have another trace with the same instructions but in different order. We have write to A, write to B, and then write back of A, write back B. In such a scenario, we can actually have A silently written back first before we issue B, or also B written back first before we write back A. So those two intervals are interleaving. And this interleaving tells us that A may not become persistent before B all the time. So in such circumstance, if we have a specification that enforces A becomes persistent before B, then the conclusion is it's not correct. For example, in the previous linked list example, we want to have the new node become persistent before we update the head pointer. But without this additional fence in the middle, we can't say A becomes the new node becomes persistent before the update to the head pointer. And therefore, we can use those specifications to figure out whether the program is buggy or not. And build up on the key idea, we have our tool called Pmem test, a persistent memory testing tool. Here's the workflow. During runtime, the program is binary instrumented, and we can able to track the traces that access the persistent memory, like the traces here. And then, based on the trace, the tool will deduce the persistent intervals to figure out the ordering persistent properties. And finally, the tool checks against the specifications. So in our tool, we have specifications either from programmers if they're dealing with lower primitives, or specification automatically generated if they use a commonly used library like Intel's PMDK. And based on specification, we can tell whether the cross consistency guarantees are met or not. So to summarize, Pmem test a testing tool that aims for figuring out cross consistency bugs during runtime to ensure correct ordering and persistence. And we have also other works towards higher efficiency and coverage, like another tool that we built as a follow-up work called cross-failure detector, that is to involve failures into the system testing so that we can trigger the recovery procedure and use the recovery itself as an oracle to detect whether there's failure recovery issues, not just based on these crafted specifications. So it ensures end-to-end correctness even after failure. And we also have a test case generator called PMFast that is to use the fuzzing technique to generate test cases efficiently, especially covering those hard-to-cover corner cases. And all those tools are open source. If you're interested, feel free to look it up, and you can find them on GitHub. So overall, we have detected 18 bugs in existing software produced by the industry for persistent memory systems. Although 18 may sound like a small number, but persistent memory research doesn't have a very long history. We are primarily focusing on industry-produced software systems. We have reported those bugs to the industry developers, and those are in these active repositories have already been addressed by those developers. So, so far I talked about the software part, and now I'd like to move on to the hardware part. Is any just very brief clarification question so far? Check in the chat.
I guess we can continue, Xiang.
Sure, yeah.
Thank you.
So on the hardware part, I'd like to talk about Janus, that is memory and storage system optimized for optimization for memory and storage system for persistent memory. So in the persistent memory hardware, we not only have the persistent memory directly exposed to the processor, but also come with all kinds of supports. For example, like I talked about in the beginning, we need to have security guarantees, that is to prevent attackers from stealing and tampering data. For example, we can use encryption to provide confidentiality guarantees and use integrity verification to ensure integrity of users' data. At the same time, persistent memory has other problems. That is the limited bandwidth. It has the bandwidth not as good as DRAM. So to improve the bandwidth, deduplication can possibly be utilized. For example, checking whether a data block to be written to persistent memory is already there in the memory. And also, persistent memory has a limited lifetime because this persistent memory device is, for example, using PCM or Intel's 3D crosspoint, they have limited write endurance, like 10 to the power 7. After this endurance, error may occur. To have lifetime better utilize the entire lifetime of the device, we're leveling the technique, that is to remap pages, those who are repeatedly written to a backend, so that we can utilize the entire lifetime of the device. And of course, where error correction will be utilized on top, so that we can eliminate other remaining errors. We have all those kind of collection of supports necessary for persistent memory systems in practice, and I call them backend operations because they all happen in the background of the processor. They are not exposed to the software. And here's something simple in those backend operations, that is the increased write latency. So now we have the hierarchy again. Let's see the timeline of the write. First, data is written from the cache through the memory, then performs memory access if we don't have those operations. But now suddenly we have the operations in the query path, then data needs to be first still written from the cache, and then be processed, going through those operations, and finally perform the memory accesses. And so some of those operations can even give us more than 100 nanosecond latency, which is degrading the write performance. So the question here is, do we really care about write latency? Is it so critical? Because in the volatile systems, usually writes are not on the critical path. But persistent memory systems are different. Let's take a look at the linked list example still. We have the 3 steps: create a new node, writing back the node, and then after the head pointer, write back the head pointer, and finally, we complete these operations. And in those steps, cache write back is actually on the query path because we have to block the execution until data is written to the persist memory. Then we can move forward to the next step. So in such a case, the crash consistency mechanism is putting write latency on the critical path. And since we have these backend operations here, the write back latency becomes even worse, which can even hurt this end-to-end execution time. So the challenge here is how can we possibly optimize the backend operations? And the main challenge I'm seeing is those backend operations seems indivisible. For example, we have a collection of backend operations like counter-mode encryption to provide confidentiality guarantees, integrity verification to make sure data is we meet the data integrity guarantees, and we also want to use deduplication to improve the bandwidth of memory. And now we have those operations all here. To implement that, we have to make them execute in certain order. For example, deduplication has to happen first because we need to judge whether this write is necessary or not in the first place. Then check the update the integrity of metadata after the write so that we have future reads to be verified. And finally, we need to encrypt everything before data reaches the persist memory. So in such a case, we have everything serialized and we suddenly make the latency longer. But we found that there's actually an opportunity to decompose those operations into smaller sub-operations. For example, let's just take a look at a counter-mode encryption. It actually can be decomposed into the following smaller steps. And with those decomposition, not only apply to one operation, but also apply to other operations we want to have in the hardware, we are seeing such a combinations. And those decomposed operations actually give us more optimization opportunities. The first opportunity is parallelization. So we see that we have all kinds of dependency here. The first type of dependency is intra-operation dependency that's in one backend operation, like in the counter-mode encryption operation, we have the counter generation step first, and then we can encrypt the counter for future encryption. And we also have inter-operation dependency. For instance, the counter needs to be generated before we can use a counter to enable duplication. Then we have those green arrows pointing from one backend operation to another that constructs inter-operation dependency. And now, since we have the dependencies figured out, if we have dependencies resolved, then we can have things happen in parallel. Like these 2 steps on top can happen in parallel together with other operations, so as the remaining operation can happen in parallel. So we suddenly reduce execution time. Instead of serializing everything in the strict order, we can make these sub-operations happen at the same time. And the other optimization is pre-execution. That is, we find that a write consists of address and data. They actually becomes another dependency, which is external dependency, because we need address to figure out where data will be written to, and the data also, of course, is necessary to tell what data will be updated to the memory. So if we have those sub-operations with external dependencies figured out, then we can pre-execute them even before we have the write being issued. For example, if we know where data will be written to, we can have some of those backend operations being pre-processed, pre-executed. And also for data, if we know what data will be, then we can actually perform some operations like deduplication operations to see whether data is matching something already existing in the memory. So we call it data-dependent operations. And for the rest of the sub-operations, if we have both data and address available, we can pre-execute them as well. So those are both dependent sub-operations. So putting those ideas together, we are building our system called Janus. The name Janus represents a Rome god with 2 faces. One face looking to the past and another face looking to the future. By saying looking to the past, I mean when we can figure out when data and address become available by understanding the program. And by saying the future, that means that we can pre-execute those backend operations with dependency resolved according to the knowledge from the past. So here is a brief view of the performance improvement from Janus. So those smaller stripes represent those backend operations, and in the baseline system, everything is serialized. And now we have more operations being parallelized using the parallelization idea. And further, if we pre-execute based on this dependency analysis, then we can suddenly cut off a huge chunk of overheads through the entire execution end-to-end. So Janus is enabled by software hardware co-design. On the software part, we are using automated software instrumentation to enable pre-execution. Given the original program, we use an LVM compiler path to figure out the data dependencies, and then find out whether there's an opportunity for pre-execution based on the address and data availability. And finally, the compiler path will instrument the original program so that it can be executed on the processor with Janus features. In practical applications, actually, we find that this opportunity for knowing data and address dependency is very common. Just like the linked list example, we already know that data will be added to the linked list when calling the function of let's append. And we know where the node will be allocated to as soon as we create a new node. So this is very common in all kinds of applications when we deal with persistent memory, so that this kind of instrumentation is actually very beneficial. And let's move on to the hardware side. Janus hardware is designed into the memory controller of the processor so that the instrumented program can enjoy all those benefits of pre-execution and parallelization. And the hardware system actually guarantees that before data is moved to the persistent memory, it validates the correctness of these pre-execution. Even though, say, the program issues a run pre-execution command, the hardware will detect such a missed pre-execution and still roll back to the original mode with only parallelization. But in most cases, our compiler path will correctly recognize all dependencies to guarantee the performance benefits and correctness. So here's the evaluation methodology. Because it involves a lot of changes to the hardware system, we use a Gen 5 cycle accurate simulator with all those features listed here. And here are a few design points. The first is the baseline with all backend operations serialized, and with Janus that enables pre-execution on the already parallelized backend operations. And we use a collection of storage class workloads like those persistent memory-based data structures and slightly larger TATP and TPCC transactions. And here's the performance. We see that overall, Janus will provide us with 2 times speed up, especially in a few workloads that involves a lot of memory movement, which will putting a lot of overheads on the memory write-back. So in summary, persistent Janus is enabling a high speed of 2x using this pre-execution and parallelization of backend operations. And this summarized the talk of the second project. And I want to also briefly go through some future directions that I'm thinking will be pretty interesting for persistent memory research. One is, how can we adapt persistent memory into larger scale systems? That is, how can data center workloads better utilize persistent memory, not even in a single server, but across multiple servers? And correspondingly, how can we redesign the network system to better leverage the low latency of persistent memory? So previously, when we talk about storage, we go through this the file systems and storage devices like SSDs. And now suddenly, persistent memory becomes much faster, but provides the same guarantee of persistence as storage devices. Then the latency becomes much shorter and suddenly puts the network latency on the critical path. It becomes more prominent. Question is, how can we redesign the system to better utilize the low latency opportunities from persistent memory? And at the same time, we're seeing that persistent memory actually is not a single simple device like the second project I've introduced. It comes with all kinds of features in the memory device. Then the follow-up question is, can we possibly integrate computational logic into persistent memory device as well? Because it has actually the capability of hosting more operations on the memory device. And it's not only giving us this lower latency, but also we can utilize a higher bandwidth internal in the persistent memory device. So the question is, what kind of computational logic can we place to accelerate memory-intensive workloads? And finally, previously I was talking about the new side channel vulnerabilities in Intel's Optane persistent memory. But as for new technology, I'm imagining that there are all kinds of challenges, especially in the security side, not only side channel, but also the software stack. how can we make sure that our software for persistent memory is actually ensuring the existing security guarantees, such as isolation, such as defend against these those buffer overflow attacks, for instance. So here are all the new directions. I'm thinking, so I'm actually open to collaboration. So this concludes my talk, and thanks again for inviting me to DSS. I'm happy to take your questions.
Thanks, Alakshan. So it was a great, insightful talk. Happy to hear from you regarding the most or the vulnerability of PMEMs in the current systems. So we have some bunch of questions. The first one is this is regarding the persist barriers, which you introduced in your code design. So what was the impact of introducing many persist barriers on the write amplification factor?
So can you actually repeat? Just I didn't quite get.
Sure. So the persist barriers through which we were cascading the writes from DRAM to the PMs. So what is their impact on the write amplification factor, or how faster?
Yeah, that's a very good point. So the persist barrier involves a cache on write back and also a fence. So frequent write backs, suppose you only update 1 byte. But now, because of the write back, it's actually internally writing back 256 bytes in the internal optimum memory. So of course, it's a huge amplification. And I think these are all the new problems we can possibly solve. For example, using some so Intel has the EADR as introduced in the previous talk. I believe it could be a good chance to optimize the performance, because now the cache is persistent. We can coalesce a lot of things in the cache before writing back data to the persistent memory in a sort of blocking manner. Does it answer the question?
Yes. And you also spoke about the repeated write blocks. How do you optimize repeated write blocks in your design?
So repeated write. So sorry,
the repeated write backs, the repeated write blocks or write backs. That is, a data on the DRAM is very consistent or very frequently modified, and you have a need to persist that on the Pmem. So, do you apply some optimization to blocks that are very frequently modified, or which are always the hot blocks?
I guess it's a kind of a general question in the software design, like how can we possibly optimize for the upper level software to overcome the, I guess it's a follow up to the write amplification question that essentially it gives you higher performance overhead and also will wear the memory faster. So I think there are multiple ways. One way I can think of is on the software side, we can redesign the algorithm so that we avoid such a repeated writebacks, to coalesce things as much as possible to write it in once instead of repeated times. But on the hardware side, I believe like EADR, like I said earlier, could definitely solve the problem. And also in the hardware side, we can adopt more robust algorithms to say where level the data across the entire DIMM to overcome this the lifetime issues.
Great. We have a question from Rohit. So the question is, rather than introducing runtime overheads, can the persistent memory SDK framework detect bugs at compile time by performing reachability analysis?
Yeah, that's a very good point. So I believe it's possible. So the work I've done is focusing on runtime, which is after development, we test the correctness. I agree that it's totally possible that we can introduce the other types of runtime, compile time systems, because many of those bugs, for example, missing a fence, can actually be detected according to the static analysis. I think so. By saying reachability, I'm not sure if the question is regarding the manager languages, but I'm actually aware that there have been work based on reachability to figure out the data persistence requirement.
Thanks. And echoing a question from Samir, in a software program memory allocation can be from DRAM or Pmem. Are there any known ways or tools to avoid programming errors, that is compile time or runtime? For example, volatile pointers written to a location where persistent memories are expected.
Yeah, those things can be detected in the compile time, I believe. So I think eventually it will be a combination for the testing domain. It will be a combination of the static techniques plus the runtime techniques. For example, like the question suggested, those volatile pointer to persistent data is supposed to be eliminated. So based on the type checking, you can figure out whether the pointer is volatile, but it's potentially be utilized in the persistent memory. But static methods always have limitations in the limited information compile time. So I believe eventually it will be a combination of both mechanisms to, at compile time plus at runtime to figure out those cross consistency issues. Yeah, that's a very good question. Thanks.
Thank you. The last question we have from Saurav. Right. So currently, a lot of research and a lot of works are happening towards using the persistent memory and the reliable storage like SSDs together. So is there any work of your specific interest that is happening around where we see that the combinations of file system on disk and PMEMs are being integrated well, and we can leverage it further?
Yeah, this is a very good point. I believe this storage tiering is gonna be a trend, like using persistent memory to keep hot data and using the slower storage devices to keep the code data or other more complicated ways, like based on the applications. Yeah, so I'm pretty sure this is gonna be the trend. As for the ongoing research on my side, I don't have a project yet, but I'm interested in this direction.
Thanks a lot. Thanks a lot for answering the questions. Thanks a lot for helping us out. Back to you, Rina.
Yeah, thank you.
Santosh. Thank you. Thank you so much, Siang Liu, for amazing session. On that note, I hope all of you are having a good time listening to various sessions and enriching your knowledge. And we have a good news to share, and that is we have about 120 plus people joining us via V-Link, and we have about 75 plus people joining us here at WebEx. And we are grateful. Thank you so much for your participation. And I hope all of you are excited, you're happy, you're looking forward for the next session. Before we head on to it, can you all type YES on the chat box for me to see if all of you are responding to us? Yeah, if you're really excited, you're looking forward for the next session, I want to see those yeses coming in on the chat box. And let me tell you, my chat box is exploding here. I love to see these responses here. Thank you. Thank you so much. Well, that looks like we're all set and we're looking forward for the next session. And that's why we would now go ahead to the next session, which is the session number 4 for the day. That is the role of Intel Pmem in advanced DOS storage architecture, which is led by Andrei Kudrysev, HPC storage architect at Intel Corporation. Andrei, are you here with us? The virtual stage is all yours.
Absolutely, Rina. I think the next session actually is a great segue on the last question that addressed to Sihan, and I'll be talking about a product called DEOS. So it's acronym. We at Intel like acronyms, we learn about this innovative development, what we are doing here at Intel, and how we actually see this while developing with the different application use cases. So before I proceed, please let me know if you can see my screen. So at least, great. Okay, let's get started then. Okay, my role at Intel, I'm product manager for this software product. This is quite a unique development that we have for several years already at Intel. Because as I mentioned, we like acronyms. I'll be using several of those. Of course, you learned the term of persistent memory already, so that's great. DEOS is an acronym on its own. It's a distributed asynchronous object storage. This is the framework that we'll be talking today about. I'll be talking about other Intel libraries such as PMDK and SPDK, which is the user space programming libraries for persistent memory and for storage and NVMe. And I'll be using also several more like CXL and other technologies that you'll see later. First, I want to introduce you to what DEOS is and what is actually our goal in developing this storage design. To begin with, I want to start that Deos is the open source development that we at Intel working on last almost 10 years. We started working on Deos way before we had a technology capable to support Deos. And with the introduction of Intel persistent memory, everything matched, everything became possible, and we launched the first release of the product. So today we are at Deos 2.0, which is the second production release. Well, technically it's a second version and the third production release. And I'll be talking about what we are doing in this domain later. So what does provide Deos? Deos is the distributed storage in a similar way, like you may know with other distributed and parallel file systems today, such as, I don't know, Lustra in HPC, such as Ceph, such as many other examples, well, Spectrum Scale, BGFS, and so on, so on. And the idea of a Deos, it's designed for the performance in the first place. So we look at the performance to achieve the maximum performance of a distributed environment of a shared file system. I don't want to confuse you. I want to be calling Deos as the, I would say, file system in the general terms. Deos is more than just a file system on its own. We typically call it as a storage framework because it provides way more advanced interfaces other than just a traditional POSIX file system with a POSIX layer. It's designed to running on the, I would say, standard hardware, commodity hardware, how we call that at Intel. So that basically means the standard architectures. We run on the latest NVMe and persistent memory technologies, but other than that, it's a standard off-the-shelf systems that you can buy in in any server store today, and we don't have any specific customized requirements for running this distributed framework. So because it started from the HPC area as the, well, historical development, I'm representing the HPC group of Intel, and the Deos development basically resides within the HPC group. We look at the HPC area, AI and big data in the first place. This is basically our origin of Deos. Certainly technology is not limited to these areas. We see the use cases and applicability in other different areas. We're working with pretty much all cloud partners today, and some of them already publicly launched solutions. I will talk about these later. But we also work with some enterprise-specific use cases of adopting databases and other key value stores technologies running on top of Deos. But I will talk about that later. I just want to bring you up to speed where we first seen that, because it makes things really easy to explain why some or another feature exists in Deos and what was the purpose and original motivation when we created that storage framework. So now we will get deeper into the technology. So expect several technology slides here. I want to explain the underneath architecture of Deos. I probably first start with the hardware layer because it makes it easier to explain what hardware technologies we are using. Then I'll explain how we are using exactly. And the last piece would be how users can see and consume these services that these hardware technologies provide. So the reason why I was so excited with the previous session, because it was a good segue to one of the use cases of persistent memory. Deos is not built around persistent memory. Persistent memory is actually fundamental technology component for Deos. It's not just something that we adopted to our existing architecture. We require technologies such as persistent memory to be able to deliver its unique services. So in a Deos design, it's a distributed environment. Every server consists of a combination of persistent memory and NVMe SSDs. And pretty much every systems are equal. There is no metadata systems, there is no head nodes, there is no monitoring nodes or other type of servicing systems in the environment. So all systems designed by the same principle in the hardware, sharing NVMe SSDs, a pool of NVMe SSDs, and a pool of a persistent memory. The reason why we are using persistent memory, because we are using let's say unique characteristics of it in the low latency response, persistency, and cache line access. Deus typically runs on top of a high-speed fabric, such as InfiniBand interconnect or Ethernet with RDMA, such as Rocky. And we are leveraging capabilities of the interconnect as well to address persistent memory remotely. So that's called, well, RDMA to the persistent memory. We at Intel call this technology Pmem. So basically it's RDMA into the persistent memory region. And that allows us to basically to access persistent memory directly from a client and put the data when we need it, especially such as for metadata. So the purpose of the persistent memory in the design is basically hosting all metadata operations. They never leave persistent memory, they only occupy persistent memory capacity. And that explains why we are so performant on the metadata operations, so the file creations, attributes, updates, find, and other operations specific to the metadata, because it all sits inside persistent memory. And secondary, we're using the remaining capacity of a persistent memory, which is, well, metadata is dynamic capacity. As more files you have, as more data chunks you have, basically more metadata you consume. So the remaining capacity is not wasted. It's always used for optimizing the I/O, and all small writes, they go to the persistent memory first, stay there, and only after that aggregated and staged to NVMe SSDs. So that provides us the ultimate class performance of the small write operations. But in the meantime, all big write blocks, such as any block, which is by the default more than 4 kilobytes, it goes to the NVMe SSDs straight. So for instance, if you does basically ultimate bandwidth, which is what we need to match the fabric performance. And typically in the system design that I'll show also later, we are using NVMe SSDs to, well, the bandwidth of NVMe SSDs is equal to the fabric performance. In that case, everything will be optimal. So why persistent memory? Basically, Intel launched persistent memory with technology called Intel Optane Persistent Memory 100 series. It was paired with Intel Scalable Xeon second generation codename Cascade Lake. And today we are at the Intel third generation scalable, the Ice Lake and persistent memory 200 series. So it's been already second generation of persistent memory, and gen to gen of persistent memory, we see performance improvement. And this is really what's important, because memory bandwidth is improving. We want to make sure that persistent memory also growing in the memory bandwidth. The bandwidth of persistent memory is not equal to DRAM bandwidth, obviously. It sits on the DRAM channel, but it's slower than DRAM bandwidth. But it provides persistency, it provides very high capacity, and this bandwidth, and especially the operations under a cache line writes, so very small operations like 64 bytes or 128 bytes, they are very, very fast and much faster than any other technology for basically with a non-volatile memory. So the 200 series that we have currently in production. Later this year, with launching of the next generation of Intel Xeon Scalable, codename Sapphire Rapids. I believe many of you already heard this term. We will be also launching the updated family of persistent memory 300 series. So similar to the step from the 100 to 200, we are growing into the better performance of a 300 series while staying within the same thermal package. So basically, users will see the advantage of on the overall bandwidth of the persistent memory. So this will continue growing, but some of you might heard already about actually the trends and directions for the well, consortium-enabled CXL technologies. And of course, with Sapphire Rapids, Intel will be introducing CXL support on top of a PCI Express electrical standard, the CXL 1.1. And the next Xeon family, codenamed Granite Rapids, so that is also, well, in the public domain, we talk about this. We will be launching the CXL 2.0 specification. So what would be fundamental change for persistent memory at that time frame? That the design of the persistent memory modules will be moving away from the DDR bus, from the DDR electrical, into the CXL bus. So that would be PCI Express electrical and CXL.man specifications. And that would allow us to decouple the traditional DRAM from a persistent memory on a memory channel. This is what you see here on the right. So today, in order to run the system in the optimal layout and optimal configuration, on every memory channel, we have to have DRAM. So that gives you full bandwidth of DRAM. At the same time, in order to have a full bandwidth of persistent memory on the same memory channels, we have to put persistent memory. So we are sharing memory channels between DDR and persistent memory. And for the next generations with Granite Rapids, Intel Xeon CPU, this is no longer the case. So DDR will stay separate and CXL attached persistent memory will be on its own. This will ultimately allow us to run well, other types of workloads which would be challenged today to run due to the bandwidth sharing between these two products, and also make it more flexible and open standard for other vendors and manufacturers to participate. So this is absolutely encouraging time. We looking forward to see this. Others will come up with their own CXL technologies. Deos today is ready to consume these hardware technologies. And so I'm switching to the next level and going to explain what is underneath Deos and how actually it's working, what is the main, I would say, design principle architecture of Deos. So the main Deos term is a container. Well, don't be confused with a virtualization container. It's a storage container. To explain it, it's a data set. But the unique thing of Deos that the container may have a different type, depends on type of the data that you store inside it. So container can be a POSIX. In that case, it has a file layout inside it and file type of a structure, how that's stored. Container can be HDF5, container can be key value, container can be a graph or S3 type of container. These all will define how data is accessible from the outside. But most importantly, underneath, Deos is high performance key value store. So no matter what type of the container you are using, we internally store it in a key value format. Basically, keys are stored in the persistent memory, but as the values can be another key value stores. So that is very highly encapsulated. I would say the paradigm of the key value inside key value, and that would allow us to create some complicated structures like you can see here and support these different interfaces to Deos. So the way users access these different containers is through the specific interfaces from the application. I mean, to make this really simple, by the default, probably every users they start with a POSIX. So they create a POSIX container and they basically set up the POSIX interface to Deos, and that way Deos will be just a traditional file system. All the operations with a file I/O will be a standard POSIX operations. We do support different types of POSIX implementation. Deos on its own is the user space on the server side and on the client side. But for some users who require transparency for existing applications, we also support Fuse for POSIX driver. So we call it Diffuse. And if users need a compatibility with their existing applications, they just run it with the Fuse for the best compatibility. If they can't go ahead, and they also can use the mode where we run it with the interception IO library. So that's a preload library that will pick the POSIX calls, and it will run much faster than Fuse. And if they're ready, they can also recompile their existing applications with just a Deus POSIX library. It's called DFS, Deus file system. And pretty much no change to the application. It's still POSIX IO. Is just a different library and different functions that you link to. So that would be very straight way how early users can jump onto Deus without changing their codes or with very minor changes to their codes. You can also see the multiple other interfaces for existing frameworks, such as for Hadoop, with the full HDFS emulation, such as to the AI framework with the TensorFlow, with TensorFlow IO integration, with PyTorch, which is currently in development integration, or just a direct Python programming. So within Python, you can call library PyDeus, and with that, you will be able just to store the data set in Deus like it's memory. So no file IO, no any files, directories, no serializing data into the sequential files. You just put the data like it would be a memory, and then Deus will deal with that on its own and put that into the proper key value layout onto the server side. So that makes it really efficient for programming, especially for users who require operating with lots of data structures. So you also see some other HPC interfaces, such as with HDF5, which is a file container, or such as with MPI IO. And also based on the customer demand, we are integrating Deus with the S3 and block interface. So it wasn't in the original storage design of a Deus. We always considered S3 to be the level, well, the overall slow protocol. But we see the demand for that, and we see users willing to use Deus for everything. So we now also integrating the S3 specification and block specification into Deus. Also, you see several of the, well, I would say ISV applications on the right is just example of some applications in the HPC segment. So we have several codes from CERN running the field sensor database. We have the oil and gas application called SIGWI, which is basically the array of data stored in the Deus, and some other applications such as data acquisition databases and so on. So these are examples of applications that already interface to the Deus natively, and basically they store the data in the key value format that gives them the best performance because we don't need to modify the data set. We just the file, the data with the application as it is, and just puts it to the Deus, and then it's already in a key value format. So, I mean, overall, this is quite innovative way to represent the data and access to the data, and also optimize the performance specific to the data types and Deus container types. As I mentioned, Deus already released in production. We are currently with release 2.0. We will be launching 2.2 shortly. So during this summer, we currently trending to the July. We will launch Deus 2.2, which is basically, we keep the idea of a Deus roadmap, we keep adding features to Deus. So we released the original 1.0 product quite long time ago. So that was a minimal product to run everything, and we keep adding the technologies into Deus. So with 2.0, we introduced a production release of Erasure code. We previously only supported replication of the data. With 2.0, we also introduced the different operation modes for Erasure code, which is configurable. So you are not enabling Erasure code for every data. You can enable specific per data container or even object inside the container. So you can get way more flexibility when you operate with the data. Depends what you are trying to do. You can have more protection, or you may have better performance, depends what you're looking for. We also continue improving the adoption with the different interconnect technologies. As of today, our two primary interconnect options are InfiniBand and Ethernet, including plain TCP and TCP with Rocky. We keep adding different, I would say, interconnect features, such as we are introducing the support of the Mellanox UCX transport, and also introducing support soon for other network technologies such as OmniPath with Cornelis network with their new transport layer called OPX. So the roadmap keeps developing and keeps adding more features to basically to extend our position. The core technology remains the same, and we just make it easier to access, easier to integrate, and also, of course, improve user usability and learning from user experience what they want to make simpler. So we really working all the last months on to actually simplifying the way how you can configure it and operate day-to-day basis. So what are our partners and how we see Deus ecosystem? And this is just a really tip of an iceberg that of different partners and customers we are working with. Our customers, well, several of our customers already launched their production systems and run Deus installation. The big installation of Deus, the biggest installation of Deus is coming later with the Argonne deployment of an exascale system called Aurora. And recently Argonne being public about what would be the capacity and the size of a Deus. So I'm really happy to share this publicly. It's over 1,000 of the Deus servers in the infrastructure. So that is amazing performance and scalability, and with a quarter of exabyte of the total capacity. So that is enormous system. Other systems that already deployed are smaller size on a scale starting from 1 petabyte and basically and more. And several installations that's been public recently is with University of Cambridge and LRZ. University of Cambridge is in UK, LRZ is in Germany. So two big institutions who launched their installations of Deus and recently submitted IO500 performance numbers. With the partner side, we split partners into the several categories from the hardware partners with whom we are working to validate and test their hardware for Deus. As I mentioned, we do not require any custom hardware, but we want to make sure that it's configured properly. So you have optimal balance of the NVMe performance, fabric performance, and capacity of persistent memory. And that is pretty much all OEMs today who are shipping standard dual socket systems. We're also working with resellers, which are smaller integrators, which could take the small components and assemble them together and deliver the full solution. And also we are working with a third-party software developers who are adding features around Deus. And again, to repeat, Deus is the open source model, but there are some companies who are building commercial business around Deus, such as Croyd. Croyd is the European, and actually today is American too. They opened the business unit in America. And this company offers commercial support for Ceph and for Deus. And they really work towards to the simplification, mass deployment, very nice looking GUI, all mouse configuration, and so on. So several others. I want here to highlight our recent announcement with Google Cloud. For Deus users, Deus is now available inside Google GCP, Google Cloud Platform. And you can provision it with, again, a few mouse clicks, and within minutes, it will be available at any size that you need within the Google Cloud Platform. And you see some others. So just wanted to bring some excitement about this and some examples what our partners already doing about Deus. Okay, what I want also to highlight that the current technologies, and that's again referring back to the previous presentation, we are seeing not only hierarchy of the different storage components within DEOs, such as persistent memory and NVMe SSD, but we also strongly believe on the hierarchy of the storage subsystems within the same installation. So when you come on a site, doesn't matter, is it HPC site, AI site, or some big data facility, you typically see several file systems designed for different purpose running together for different data temperature. Basically, DEOS is designed for performance, and while using the most performant products, it might be not the most, I would say, cost per gigabyte optimized platform, because certainly very cheaper technology to store the data, such as, well, typical hard drives are much cheaper than SSDs still. So we really believe into the in a way of the hierarchy storage deployment in a production where DEOS can be your primary performance tier, and it's really optimized for performance per dollar. So that is the lowest performance per dollar if your target is performance. Sitting next to the capacity tier, such as any other traditional POSIX-based file system, such as Lustra, such as Ceph, such as Spectrum Scale, or anything else. And also extending to the cloud technologies with the S3 interface storage systems. To make all of that happen within DEOS, we already have the development that allows to do the data migration and data movement by DEOS on its own. So within the DEOS framework, there are tools which are designed to say, well, please move the data outside of DEOS to POSIX compliant file system, and then DEOS will be moving that on its own without any interaction from a user. So that allows us to basically to process the data inside DEOS. And once that data processing is complete and we no longer need this data, we can stage it automatically to the capacity storage. And back and forth, we can prefetch the data from the capacity storage before running the workload onto DEOS, then proceed it, and so do that vice versa. So these capabilities already built into the DEOS design, and we strongly believe that this is the way how DEOS technology should be developed in a production. One of our well, latest updates with the DEOS performance numbers that I want to share with you, this is just a very recent numbers that we presented at ISC last week, and this is why the design of this slide is different. I just took it from our keynote presentation. To make a reference for users on the relative performance difference between DEOS and Lustra, one of our partners, University of Cambridge, they took exactly the same hardware configuration with persistent memory and NVMe SSD. They deployed DEOS on this system, measured the performance with the IO500 benchmark set, then deleted everything from this system, provisioned the system with Lustra, and measured the performance again. So what they found that across the workloads, which create the, well, really small IO, random access to the data, or heavy metadata access, we see performance improvement of DEOS comparing to Lustra, well, anywhere between 6x and 10x, depends on what type of well, actually data access you have to your data. If it's only about streaming the data and it's only about bandwidth delivery, of course, DEOS as fast as your scalability of a traditional file system such as Lustra, because for streaming data, your hard drives in a huge quantity can be also good enough to provide this. So we're really focusing on the delivering the performance of the most difficult, I would say, workload patterns. And this is where DEOS, well, shines, really. Okay, so to close my session, again, a little bit of the technology, what type of requirements we have to the storage server side. As I mentioned, it's pretty much any commodity type of a hardware. Standard dual socket system will work just fine. We just want to make sure that it's configured in a balanced way. So in that way, persistent memory and DRAM populated in all memory channels. So we call it 222 or 22222, depends on the CPU architecture. So that basically means that you have in every memory channel, you have DRAM and persistent memory. That gives you the maximum bandwidth of DRAM, that gives you the maximum memory of persistent memory. Also, we want to make sure that it's populated in both CPU sockets in case of a dual socket configuration. And if so, it should have corresponding the dual interconnect interfaces, whatever it is, InfiniBand or Ethernet, having separate host bus adapters for the HFI cards for the network would only benefit. And then the shared pool of NVMe SSDs, the bandwidth of NVMe should be more or equal of bandwidth of your fabric. That is obvious because we're writing all the big blocks straight to the NVMe SSDs, and you want to make sure that it's not a bottleneck. And finally, there is a capacity ratio of persistent memory to the NVMe. So you have to have anywhere between 3 and 6% of persistent memory, capacity of the NVMe storage capacity. So for 100 terabyte storage total, you have to have between 3 and 6 terabyte of persistent memory for storing your metadata. And because it's dynamic, it varies from application to application, but remaining capacity will be always utilized for the small IO operations. So with that, I want to point you to the Deos resources. The Deos.io is the main website for Deos. You will find the links to the GitHub with all source code available. I highly recommend you to sign up for the Deos mailing list. In that case, you will also receive invitation to Deos Slack channel, and you will be able to communicate with all 50 Deos developers currently working hard on Deos, pretty much at any time. So, thank you for listening, and I'm happy to hear if any questions in chat.
Thanks a lot, Andrew. Appreciate your time. So we have two questions. One is regarding the EADR adoption. Is EADR adopted in DAOs? And
Yes.
if yes, what were the major changes or what are the major challenges that were to be handled?
Yeah, well, first of all, for Deos, there is no changes because Deos relies on the persistent memory PMDK programming toolkit. This is a software framework. And that makes, first of all, this is very easy to program persistent memory and easy to adopt new technologies because it transparently handles all the enhanced ADR improvements in the persistent memory 200 series. And where we see that advantage of that, obviously, in all write operations, we'll see performance boost. So we pretty much doubled write operations of metadata in Deos with a persistent memory 200 series compared to the persistent memory 100 series.
Okay. And I was glad to hear regarding RDMA on the Pmem. So traditionally, we talk about RDMA on the PMs via the DRAMs. So, but does DAOs do the same, or do we have dual channel of RDMA to DRAM as well as Pmem in DAOs?
Deos client goes to the Pmem straight. We are not using DRAM for any type of buffering. So we have very minor requirements for the DRAM system capacity because we pretty much don't use it on the Deos storage side. We don't store any IO on the flight. There is nothing that would compromise the file system consistency on the data loss. That's a reason why on the power loss. That's a reason why we use RDMA to the Pmem because it guarantees us with, of course, enhanced ADR enhancements. This guarantees us that the data stays in the persistent region right away.
Okay. We have a question from Ankit. What are the thoughts of having high availability solution? Do the class of applications that use DAOs primarily rely on checkpointing and restarting, or do you see HA coming in DAOs at some time?
we don't need HA. We have, well, I already mentioned we have a rigid code that you can turn on for any data container. But we also have a data replication built into there. So you can have n copies of the same data, depends what is the goal. The goal could be a data protection, of course, but the goal also could be increase the data parallelism, especially for AI applications, which can be reading the same location over and over again from thousands of compute nodes. Then you can increase data parallelism just having that copy several times, and that gives you more throughput. But in general, we don't require high availability such as Lustre requires. And that's another advantage of Deos because we are totally designed within the software and the data protection and resiliency over the failure is provided with software and Pmem capabilities.
Okay. Great. I think that will be the end of questions for this session. Back to you, Reena. Thanks a lot. Thanks a lot, Andrew, for your time.
Thank you, Andre. Thank you so much for joining us here today. And we had a great session. Thank you, Santosh, for curating the entire Q&A. We would now quickly move on to our next session. But just before that, we would like to ask our audiences who have joined us here. So you have been thoroughly listening to all our speakers, all our sessions so far, and I'm sure you are excited for our next session. But just before that, I really want to know if you're excited. I want you all to write the word excited on the chat box. Can I see that response coming in on the chat box from all of our guests who've joined us here today? As many responses possible. Fantastic, fantastic. Looks like the chat box is literally on fire. And I know we have 2 more sessions that's left out for the morning session. And after the break, we have a few more sessions that's waiting for you. But the time has come for us to move ahead to our next session. And that is, thank you for your response again on the chat box there. Thank you, everybody. Thank you, Lakshman. Thank you, Sanjay. Thank you, everybody. The next session is on domain-specific accelerator DSA architecture for signal processing, communications, and machine learning. And this is led by Dr. Kiran Gunnam, who is the Distinguished Technologist, Western Digital, Santa Clara. It's lovely having you with us, Dr. Kiran. Am I audible enough to you? Good morning. Is it morning or it's good evening?
Yes, good morning. Can you hear me well?
Very much, very much.
Okay, sorry for that. I have on a low data bandwidth connection in a hotel. So I just arrived in India actually. So therefore for a travel. So hope you can hear me well.
Very much.
Thank you, Reena. You can make me the presenter when you're ready. Okay, thank you. Hope you can see my screen.
Yes, we can see your screen.
Okay, thank you, Reena, for confirming. It's a great pleasure for me to give a talk in this event, and thank you for organizers for inviting me into this. And this talk is more in terms of the acceleration of different applications. So essentially, mainly in terms of the signal processing and communications and machine learning. Even though it appears that there are 3 different applications, so these all share the same paradigm, like in terms of the how these accelerators are designed. And there are some specific customizations you do for each of the applications, but all these applications share same principles in terms of the how you optimize the algorithms and how you optimize the hardware architectures for it. And those I have 2 modules in this presentation. I think I have around 30 minutes for talk and 10 minutes for Q&A. So, but we can have this as interactive one. If you have questions, you can raise your hand and then ask a question. I can try to answer those questions. So I think to start with, we can go with the basics, like what are the domain-specific architectures? So like you can basically like start with a base algorithm that can be a signal processing or communication or a machine learning application. And so a particular algorithm in each domain can influence the underlying architecture as well as the microarchitecture. So essentially, you're kind of designing doing a co-design in three dimensions. One is algorithm, another was the software and hardware. You're kind of doing a co-design in all these three dimensions. And only when you do the co-design in these three dimensions, you get an efficient DSA. And also the DSAs typically, like what are the features of these DSAs? They usually feature custom arithmetic, and they also usually feature custom interconnection network, and also they feature custom instructions / microcode. So one of the examples, this is from my own work, and that was done at Texas A&M, which is widely adopted in the industry. So these decoders, like these are error correction decoders, these can be classified as the signal processing as well as the communication application, because essentially error correction falls into both the areas. So these feature simplified algorithms, and also these feature novel hardware architectures. And as I mentioned earlier, these are both, you can classify as a signal processing or communication. So in terms of application, these are used in both communication and storage, like Wi-Fi, as well as the storage such as flash and hard disk drive. Some of the concepts we introduced in these architectures are the following: like you have a block serial scheduling and value reuse, and scheduling of layered processing and out of order block processing, master slave router, dynamic state, and speculative computation. Some of these things are more specific to these error correction decoders, but these concepts are actually can be applied on the other accelerators also, as we see later. The other key aspect of these domain-specific accelerators is while you are customizing your acceleration for a given application, you need to be able to support say for instance in the case of the Wi-Fi, you have to support multiple ports within the same standard. So you need to be able to change dynamically. Like you don't, you have only one chip already built. You can, but you should be able to support in the software. That means you have to do this configuration in the runtime. And then you can build a separate chip for WiMAX, which is mentioned as 802.16e, because typically when you're building a chip for Wi-Fi, you don't need to build a chip that works for 802.16e also. You can make a decision. This is essentially like a market driven, because when you're making a chip, you decide that, okay, I'm not going to support all these different wireless applications. I pretty much need to support a Wi-Fi. Then you can build a very efficient chip for the Wi-Fi itself. And the reason that you need this kind of a focus is that some people try to build a generic an LDPC decoder that works for each and every application. Like they want to support Wi-Fi, WiMAX, they want to support storage applications, they want to support anything you take from anything that's available as an application, they want to support it. But that's kind of very not recommended, because then when you try to support it for so many applications, then you would lose the advantage that comes from the customization. But at the same time, you don't want to customize too much, because some people also tried customizing for just running one kind of code for one given length and one core rate. That is also kind of a suicidal mission, because these codes would change. The core rates have to change based on the channel conditions. So essentially, too much customization for a specific product or too broad customization for all markets is not recommended. So you need to have a right focus in terms of what you're focusing on. Then the other aspect is that the fourth line kind of fits in there. When you're building in this architecture, you want to be able to reconfigure offline. In a sense, you have the same design. It is just that for a given application, say for Wi-Fi, you want to build one chip. For WiMAX, you want to build another chip. But the designs are quite similar. So you don't want to, again, redesign the whole thing. So you want to be able to reconfigure your design. Like say the difference between the WiMAX and Wi-Fi codes, if you're familiar with these standards, the difference is that you have a different kind of a interconnect network needed in the WiMAX chips compared to the Wi-Fi chips. So essentially in the design, you would select the option that way, like the chip that is designed for WiMAX don't need to have the interconnect that is needed for the Wi-Fi. So that way you're saving the area in that. So, but at the same time, you don't want to redesign the whole decoder for different applications. So the key aspect is that when you're doing a DSA, you want to have some configuration, the static reconfiguration possible for different applications. And then within application to support these different changing channel conditions and different runtime conditions, you need to have a software support for it. And then the other aspect is that in terms of, say, for instance, for machine learning, all the DSAs, these typically feature a matrix multiplication core, and sometimes they feature dot vector cores, and they have a additional support such as rectified linear units and pooling, and you have some programmable microcode. So these actually don't support only one network. These can support multiple networks. And the key to support that multiple networks is that you have these runtime reconfiguration to support multiple layers. Because if you start with like some of the companies started with, they support only ResNet, and you can build everything that supports ResNet, but then it cannot support the other networks that have some kind of different kind of layers. So the key aspect is that when you are designing your accelerator, you want to have flexibility, enough flexibility that you can support these different changing applications. So, and also you want to see in terms of what is the minimal primitive that is needed to support these applications. At the same time, you get enough speed up. And now, as I mentioned here, you can do these DSAs. DSA is a recent word, but application-specific accelerator is one of the words that was used before. And but in general, these DSAs, this can be a combination of anything. This can be an ASIC with some programmability. So TP is essentially an ASIC, and it has some additional firmware to configure it. And then you have you can simply build one SoC and with some programmability. And similarly, you can implement this DSA and FPGA as well. And you can, in FPGA, you can have a hard core, like some FPGA vendors provide some matrix accelerators as well as Systolic Array has a hard core, or you can have as a soft core and FPGA. So the key aspect is that whatever you're accelerating, you could implement as a combination of the hardware and software. And again, you have a choice in terms of whether you want to do as an ASIC and an FPGA with the different trade-offs. Now some interesting questions here. And so some people ask that is DSP a DSA? So in general, it's more of a political question. In general, I would say my personal opinion is it's no in general, because it supports broader signal processing and communication and machine learning applications. But the focus is on very base primitive. It focuses on MAC unit only. So if you increase the level of at which level you're looking in terms of the underlying building blocks, if you raise that, then you can go you can come to the different accelerators. So for instance, some DSPs have the ACS unit, like accumulate, compare, and select unit, and that accelerates the Viterbi. So you can, some recent DSPs again have the the ReLU unit as part of a the acceleration part of they're connected right after the MAC units, so they have the additional acceleration. So it's kind of it's kind of a very blurry, I would say, it depending on how the corporate marketing messaging is done. So then the next question is again, is GPU a DSA? So in general, again, it's no, and the current GPUs are kind of, you can consider it as it's kind of a SoC, has so many it's a combination of so many accelerators. It has a graphics accelerators, and it has the neural network accelerator, and it has the if you look into the some of the GPUs they had depending on if you look in terms of the AMD GPUs, they have they optimize for the video games as one kind. They have one kind of GPUs that are optimized for the video games. They have another kind of GPUs that are optimized for the supercomputing. So in the GPUs also you have the domain-specific accelerated GPUs. And but again, this slide I would say that it can be interpreted broadly by different companies in different ways. So it's better not to get stuck in this discussion. But the key question is that if you are doing some kind of a hardware change and software change to support an acceleration, you can broadly call it as a domain-specific accelerator. And so the key aspect is that you have a base data processing algorithm and you have these area, power, and speed constraints. And the time to design is one of the crucial factor. So one of the things you may notice that you would see so many AI accelerator companies in the market, but at the same time, you would see that none of them are gaining traction compared to the GPUs. The reason being, the GPUs, when they're when something comes in, you can run any neural network. But when somebody says that they have some AI accelerator, by the time it comes to the market, that chip may not be supporting the latest and greatest neural network. So because the time to design, it takes almost 4 years or something, and they don't have enough flexibility, while as the GPUs have enough flexibility to run any neural network. So it's still difficult for custom AI accelerators to gain a broader market adoption. But at the same time, if you are designing a accelerator, if you have the control over the application, say for instance, for storage companies like that, like us, we have some applications which we want to accelerate, so we have control over of what neural networks we want to run. So if you want to specifically optimize for those neural networks, we can build those ones into our products. But at the same time, if you're selling these neural network accelerators to a broader market, then the broader market needs may change. So unless you put more flexibility in that, it is difficult to sell those accelerators. So I would kind of skip this one. And so I think one thing I want to point here is that most of these accelerations are based on some of the simpler ideas. You have doing some kind of operation, you're doing operations A and B, and you're doing it at 0.5 gigahertz, and it is taking 2 nanoseconds. Now, how do you speed up? You can do things in parallel. And if you have 2 tasks to do, you can put 2 computing paths in parallel. That way now you can finish these 2 tasks together in 1 nanosecond. Or you can pipeline, you can basically insert a timing element between A and B, and then that way you can speed up this one so that you can finish this task in 1 nanosecond. But then you have a little bit more latency, but when you're doing the things at a faster rate, you're looking for a higher throughput, this latency is minimal. And I would skip this slide here. Then the other aspect is that most of these things, if you're more looking in terms of the hardware, you're looking in terms of a signal flow graph, you can see that if you're doing say for instance in this one, you have to do different for instance, if you're doing a regular signal flow graph, you have almost the m times the time due to the adder, and then you have the additional multiplication delay. But if you're using a tree adder, then you have a log 2m times the delay due to the adder. So you can actually reduce the speed up here. But the trade-off here is that you're putting a little bit a different structure. And so essentially the trade-off is that you're trading off the hardware for getting the more a speed or reducing the critical path. And I would skip this one slide. You can basically transform the signal flow graph to get even improve the signal flow graph. So in a sense, if you are stuck in only this signal flow graph, right, you are only changing the structure here, but here actually we change the signal flow graph. So it's kind of you're using the same algorithm, but you represent the algorithm in a different way. So it's sometimes what we call as a SFG transformation or algorithm retransformation. So then the other aspect is that you are doing a block processing or vectorized parallel processing. Again, here is that you look in terms of the formalizing in terms of a matrix equations, because once you write in terms of matrix equations, you can again use all the traditional techniques how to speed up the matrices. So that's one way to speed up the application. So this slide I would skip, but the key aspect is that you can do like what we call as a time multiplexing, where you have two streams coming in, where you have a, let me show my slide pointer here. So where you have one block that is operating at a higher speed, and then you can feed in two streams. And the other operation we do typically is the folding. So folding is nothing but you can you're giving a reference, you're looking at the reference architecture, you're giving some input and you're getting some output. Now you can consider this as a iteration, so that you're doing 4 iterations. Now instead of putting hardware for each iteration separately, because sometimes you may need variable number of iterations, so you can simply put only one unit and then iterate it over. Now the key aspect is that sometimes we are saying that, oh, you have to do folding. Sometimes we are saying that you have to do parallel operations, and sometimes you have to do the pipelining. So these are different kind of techniques. The key aspect is that for a given algorithm, where you can actually look in terms of the new way of rewriting it, or sometimes we can come with a completely different algorithm. Now the choice of the right mix of these operations would be evident only when you look into the algorithm, what kind of mix is suitable for this algorithm. Sometimes you may need to think in terms of a completely different algorithm. And I would skip this one. This is kind of unfolding. These are if you have look into this one, this is an IR filter. You have a dependency for a current output on the previous output. So now again, you can do the unfolding in this one so that you can do 2 output samples at a time. And then you can do retiming. Most of the digital designers do the retiming through the tools now. They don't need to do it manually. And the other aspect here is that if I move on, you can do systolic architectures for most of the matrix applications. So systolic array is nothing but you have an array of the processing engines that are connected in a very tight fashion, so that you're not wasting a lot of time in moving the data to register files and memories and then bringing it back. So the data is being given from in this particular one, you're feeding from the from the columns and rows, and then you have the local compute. And I don't want to get into the details on this one, but most of the accelerators, machine learning accelerators, use a systolic array. So the systolic arrays have been used in the military applications and other applications for more than 50 to 60 years in signal detection and tracking, like radar. So let me skip on this one. And let me move on to the next module here. Give me 1 second. So any questions so far?
We have a question from Jayanto. Let me echo it. So what you mentioned about DSA in machine learning, is it actually DSA for deep learning?
Yeah, you can consider that as a DSA for the deep learning, but at the same time, the systolic array, you could use it for the regular machine learning also, because most of the machine learning is essentially matrix operations. Say, for instance, if you're using a say, for instance, the MLPs, right? You have a lot of matrix operations. They're kind of dense matrix operations. You can use a systolic array to accelerate it. So in fact, the TPU has this systolic array and some additional compute, like a sparse compute and so on. But it can accelerate both MLPs, CNNs, and LSTMs.
And then there's a reported question on it. Is there any effort on designing DSA for large-scale statistical machines learning problem?
I probably didn't get your question correctly. Let's say if you're doing a large-scale statistical machine learning, right?
Right.
So yeah, so I think it may depend on the specific application, but when Google has done the, say, for instance, TPU kind of architecture, right? So they're more looking in terms of their recommendation engines. They're looking more in terms of the image inference, and they're more looking in terms of the like the speech translation. And now when you're looking in terms of a large scale statistical machine learning, right, you need to see what is the core of that algorithm is. Like, is it still dominated by matrix operations? Then you could still use a systolic array kind of architecture. But if it is something different, then you could come with a different architecture. So maybe I think we can come back to that. Say, for instance, for in our research at Western Digital, we built a new architecture that doesn't use historic array actually, so that uses a different one to accelerate the CNNs. It's more on the deep learning side, but we didn't use a standard systolic array that everybody is using. We got actually like the anywhere from 2x to 5x savings compared to the systolic array. So because we deeply looked into the, okay, what is this application? Okay, we looked in terms of the, okay, we are interested in the image inference. So what is the right way to do it? We looked into the algorithm, we looked into the hardware architecture, we looked into the software. So let me get into that, and then maybe you can come back to your question to see whether this kind of approach, you could use it for your application.
Sure, please.
See, okay, so probably I might have, how much time I have, Vina?
We have 20 more minutes.
20 more minutes, okay, thank you. So let me see here. I think this slide, you might have seen this one. The essentially, if you have considered the AI as a field, ML is a subfield of it, and deep learning is a the subfield within the machine learning. And now the other aspect is that, right, why there's so much buzz in terms of the machine learning on ops as well as the deep learning. So hardware has improved a lot recently, and because of that, starting from around 2010, some of these algorithms which were not able to run on the conventional hardware, you can run on the GPUs, and people are able to train AlexNet on 2 GPUs. And so that made the machine learning mainstream. And so as you see, most of these complex tasks now are performed by machine learning. Sometimes you may actually loathe it, in a sense, if you may not like it, because when you call a customer service center, most of the times you would be greeted by an automated agent. And then, but most of the basic tasks can be done by the robo agents at this point of time. But at the same time, in future, you can expect that most many complex tasks also will be performed by these agents. So I think you probably be familiar with this one. There are so many applications. The self-driving car and the translation is one of the thing most of the people use in daily life. And robotics is another one. You'd be seeing it being deployed in the industry automation. And then some application like big data and analytics and so on. So this is a kind of a very dense chart, but the key aspect I want to highlight is that in late 70s, and there was an AI winter, essentially the funding was reduced on the people who are doing the research in terms of the AI and machine learning. And again, there is another winter in late 80s and early 90s. And there was so much hype at the time that, okay, these are going to solve all the problems, but it didn't happen that way. But this time, this is not a hype, because you're seeing a lot of mainstream applications using the machine learning. And now, most of the people probably are familiar with the traditional machine learning. You have a hand-designed. Give me a second here. So you have a hand-designed feature extraction. If you're from the image processing point of view, you'd be using these different feature extractors such as SIFT, and then use a SVM, a support vector machine. So this has been the norm until 2010. People are coming with the different updates to these kind of feature extractors, and they're using SVM. They're getting from 74 to 75, 76, and that kind of thing. Then when the AlexNet came, they came with a 85% accuracy. That's a top 5 accuracy. That's almost 10% more than these traditional ones. And any question here?
Would like to request those who are joining us here, if you're not the speaker, to kindly stay on mute. Over to you, Santosh. Is there any questions?
No, I guess it was somebody's unmuted speaker mic, so I think we can proceed. Sorry for that.
Okay, no problem.
Sorry for that, Kiran. Please go ahead.
Thank you. So in terms of machine learning, you can look from this aspect also. You can look in terms of there are three ways: supervised, and then unsupervised, and then reinforcement learning. And the supervised learning typically is that you probably would be very familiar with that. You have both input data is given and output data is given. You have a lot of examples. Say, for instance, if you're looking for an image classification, you're given millions of images of dogs and millions of images of cats, and you have also there with the correct output labels. And you give all these millions of images to to train a machine learning model, and then eventually it would learn to classify whether it's a dog or a cat, and then you can do the same thing by adding more sets of examples. But the supervised one has a flaw. In a sense, if you trained with a capsicum, it can detect capsicum, but when you make a hole in capsicum and show the image, it doesn't detect as a capsicum, because it's a very it doesn't have much intuition as humans have. Now the key to is that again you need to train with the capsicum with a hole, and say that you have to say that okay, it's still a capsicum, then only it will detect that as a capsicum in the later inferences. So essentially the supervised learning, it can't generalize much. Whatever it can do, it is based on the examples you have given. And so in terms of the unsupervised learning, so it's kind of finding patterns within data. So when nothing is known, right? Say for instance, if you give some set of coins to a child, right? So he or she may organize the coins based on the size and shape. So that's the same thing in unsupervised learning. Also, you have an agent that simply looks at, okay, which are similar, and it tries to organize them into one group, and then it organizes the other group, and so on. So Google News is one such example of unsupervised learning, where you see all the news related to Modi are classified under one thing, all the news under Trump are categorized under one thing, and so on. Similarly, it applies based on the region, state, and so on. And then you have the reinforcement learning. So in the reinforcement learning, it's kind of you're introducing what we call as a reward system. So when the child is learning, it's pretty much more on the reinforcement learning. For instance, when the child tries to do something that is dangerous, and the parents would be shouting at the child, and the child now knows that okay, it's dangerous to do that. And so when you're having a machine to drive, people use reinforcement learning. But the key aspect for the reinforcement learning is that you can tell that okay, you have to go from point A to point B in, let's say, for instance, in Bangalore, and you have to if you give just a reward saying that don't make any accidents, that is not enough for the machine to adjust its course of action, because from going from point A to point B, it has to do so many decisions in between. So that means for each of those decisions, you have to give micro rewards. Those micro rewards are difficult to difficult to establish. So that's the kind of the problem, the reinforcement learning, but we'll get to that. And so this one I would skip this, and I would skip this reinforcement learning also slide. So again, there's so many different algorithms in this one, but I think the key aspect is that you have these different choices for each of them. Especially for reinforcement learning, some of the things are suitable for when you have everything is known, like a model based, such as chess and Go. But for the self-driving, the model based won't work, because you don't have a perfect model of the world. You don't know how the humans are going to behave on the road. So let me skip this one. This is a typical data pipeline. Usually, I think the key aspect from this slide, this kind of again dense slide. So you would see the machine learning used at some of these places, and the key aspect is that machine learning is kind of one of the tool. It is not everything. It's kind of a tool that is needed in all the modern applications. It's not sufficient by itself. And again, if you look into the retail data pipeline, this is one chart, I like it. You would see that you would see both the classic machine learning and both the deep learning are used in these retail data pipeline. So again, this is a dense chart. I will try to have these slides communicated through to the organizers. But the key aspect is that you're doing some of things in offline. Most of the classic machine learning is done offline, and the deep learning inference is done typically in the real time. And but there are some applications where they are done in offline also. And this is kind of a Netflix kind of a recommendation pipeline, like what movies you want to watch and so on. So again, there's a different, as I said, ML is one such, the enabling the application layer. And I would skip on this one. And this, in terms of the self-driving pipeline, right, you would see a lot of sensor processing that is done, and then you have perception. This is more signal processing based, where you're using the nonlinear least squares for the SLAM, like simultaneous localization and mapping, and as well when you get to the the navigation, path planning, and so on. There's so many control-based algorithms. So what is happening right now is that there is a lot of ML based things, such as the CNN based, and those kind of things are coming into these techniques. Say, for instance, when we're doing a perception, you need to have a what we call as when you're doing a SLAM, you need to extract the features. And when you're extracting the features, you need to detect, okay, what are the objects that you are interested in. So for those object detection, you can use the deep learning. So it kind of like here in the self-driving pipeline, you see a very good mixture of both classic signal processing techniques as well as the classic control theory techniques, as well as the deep learning techniques. And I would skip this slide. This is in terms of how the map generation is done. But one key aspect in this one is that there are a lot of things that are done in this HD map generation. Say, for instance, when you look into the Google Maps, especially for any reason, some regions have a better accuracy, some regions don't have a better accuracy. So these maps are more for the humans driving cars. But for the self-driving cars, you need a high definition map, because you need in terms of the centimeter level accuracy. And most of these things, you need a lot of labeling. So there are like thousands of people working in the to do these labeling. So most of the things, even though like some people say that like here maps and other companies, they provide HD maps, they are using a lot of like the manual processing to generate the this tags and so on. There is some progress in terms of using the mix of unsupervised learning to speed up this process, but unfortunately most of these map generation are still limited by the labeling needed from the humans. But I think coming to here, right, this is from the Google data center. I think one of the question that earlier was asked is that, okay, does the acceleration like only support the deep learning? But in terms of the TPU, and you build a systolic array, it can support both MLPs and LSTMs and as well as the CNNs. And but the key aspect with just doing a systolic array for CNN is that you can build a better accelerator for CNN by not using systolic array, but by using a different hardware architecture that I have time to show that architecture. So this is in terms of the Facebook data center workloads, how these what they're using mostly CPUs and a mix of GPUs. And again, if you see that most of their workloads are MLPs and CNNs and the RNNs. So let me skip on this one. These are more generic slides here. Yeah, I think this is again, let me see whether I should have something here. Give me a second here. I think unfortunately I don't have the slide on the the accelerator we have done on the machine learning in these slides, so it may take more time to bring me the slides. But I think the key aspect in terms of the acceleration is that you can actually, like, instead of just choosing a systolic array to build an acceleration for the CNNs plus RNNs and MLPs, if your application just needs to support the image inference, you can build a better accelerator. So that's what I'm saying, like, depending on your market, right, you can choose a customization. So the one we have done for the for the image inference is that if I go back into these slides here, so let me show here. So if you see this slide, hope you can see this, what does each layer learn? So in this one, so you have these different layers. If you see this one, there is so much sparsity in this one. So typically what the systolic array does is that even though it is all zeros, most of them are zeros, they still do a lot of computations on zeros. So what we have done is that, okay, we built a specific accelerator that doesn't do any processing on zeros. So when we're building that specific accelerator that doesn't do the zero processing, the difficulty we had is that it can't do more than, let's say, 16 values at a time. That means it can't, like, it is very difficult to build an accelerator that does more than 16 MAC computations at a time because of the complex interconnect needed. So now the way we solve the problem is that we said, okay, when you're doing a convolution, there is no need to do the convolution on the whole image at a time. You can do actually partitioning as long as the mathematical properties of convolution are satisfied. You need to maintain some overlap in the partitions. And as long as that overlap is maintained, if you're doing a 3x3 kernel, you need to have an overlap of the two rows. Say, for instance, you have a 1000 by 1000 image. Let us say simply you're partitioning into a 500 by 500 and 500 by 500, and so you have 4 such partitions. So as long as you have two rows and 2 columns common with each of those partitions, then you can do convolution on each of them separately. So now the other key aspect we have done is that you can actually do a very just-in-time the repartitioning. Like, it doesn't need to be 500 by 500. Depending on the number of non-zeros, you would do a runtime repartitioning. So one partition may be only 100 by 100 because if there's enough number of non-zeros, you can assign to one compute unit. So having this combination of these 3 things, like have a specific hardware unit to handle the sparse compute. Then we have a partitioning mechanism. Then the third one is that we have this partitioning is done in runtime dynamically, so that based on the input image, you're kind of doing a workload balance. So given these 3 things, we have an additional advantage of 2x to 5x depending on the underlying neural network. So I think having said that, I will stop at this point of time, and I can take more questions.
Thanks a lot, Kiran. Interesting was one of the folding, what you said in the last PPT, right? Looks so very trad and adding to thoughts that you had put in the discussion. So what do you see as the example or the use case of the folding technique?
Okay. So for instance, right, like in the case of machine learning accelerator, right, let's say you have 100 layers in one network, you have 10 layers in another network. And you can build an accelerator that has a hardware to support all the 100 layers at the same time. But then that would be super inefficient when you're trying to support a neural network with only 5 layers. So now instead you can design hardware accelerator that supports only 1 layer, and then you would that can run much faster, and then you can use it 100 times when you're running a 100-layer neural network, and you can invoke the same hardware accelerator. You can invoke the same hardware accelerator 5 times when you're running if the network has 5 layers. So essentially, folding is kind of instead of putting the hardware more times, you're making a choice in terms of, okay, do I need to put this one in hardware, or do I need to just put one instance and call it multiple times?
Could you help us with any real-time example or workload that uses it the most?
Yeah, I think you can, as I mentioned, right, the neural network is one example. Most of the accelerators people are building, they support typically one layer at a time. And they don't, they essentially, you can think that they're folding they have one compute unit for a layer, like you have a layer compute unit, you can consider that way. And then you are essentially like your entire application has 100 layers, and now you're folding those 100 layers onto one layer compute unit.
Okay.
And the other way to look at it is that some people even don't do the layer also, because layer also sometimes you have multiple feature maps. For instance, what we have done is that we have only a feature compute unit, feature layer, like a feature map compute unit. So we actually like the do a time folding using the feature map compute unit.
Okay. Thanks a lot. We have a question from Jayanto. Is there any specific DSA for optimization tasks such as linear programming or quadratic programming?
Yeah, myself not very familiar with the with this specific one, but in general, right, when you want to build a domain specific acceleration, you need two things. One thing is that, right, whether you can do a domain specific acceleration on that. That's the first thing. Then the second thing is that the second one is that, does the market need it? My belief is that maybe that linear programming, you probably can do the domain specific acceleration, but maybe the second thing is that the market may not need it, because if it is a like an application that is well served by the current processors and GPUs, and many people may not want to spend additional chip to support an application such as linear programming.
Thanks a lot. Rina, do we have time for one last question?
We're actually short by 2 minutes, but you can probably take one more question.
Thanks a lot. Thanks a lot, Kiran, for answering them. So the one last question again from Jayanto is, apart from deep learning, what are the other domains where TPU is used?
For the TPU, right?
Right.
So the TPU you can use for the recommendation engines. You can use the TPU for the like MLPs, and you can use for the speech processing such as LSTMs. And so pretty much as I mentioned, right, like for TPUs, you can use for all the machine learning as well as the deep learning applications.
Thanks a lot. Thanks a lot. Thanks for your time, and thanks for the very insightful session. Back to you, Rina.
Thank you. Thank you, Santosh. And thank you, Dr. Kiran, for coming back to India and then not taking break, but being here with us and making time for this session. You've made our day. Thank you so much for the knowledgeable session. It was lovely having you with us.
Okay, my pleasure. Thank you, Rina. Thank you, Santosh. And thank you, Prashant. And thank you for all the organizers.
Thank you. Thank you once again, Dr.
Thanks
Kiran.
a lot.
Well, on that note, I hope all of you are excited for our next session, because the next session is going to be a panel discussion session. We have our panel members, we have a moderator who are all set to start the session. But just before that, if you've got your questions, you can leave that on the chat box and our moderator will pick that up and answer them via our panel members. Let's take you through the session, and this is how to make life simple for applications and developers in the era of emerging media and interconnects. And panel members are Alex Kirkop, founder and CEO at Ondat, Professor Umesh Bellur, IIT Bombay, Rajkumar Kannan, HPE, and our moderator is Ankit Mathur from Huawei. Over to you, Ankit.
Thank you so much, Rina. And I know this is one of the sessions people have been waiting for. The entire morning was pretty interesting with multiple sessions, right from like how to develop storage for different newer applications, and all the way now developing AI and models. So now let me bring in my panelists one by one. So these are all eminent experts from the academia and the industry. So Chengappa, if we can have a panel view for everyone, so that maybe a spotlight kind of thing. All right. So we first introduce Professor Umesh Belur. He's head of department for computer science and engineering at IIT Bombay, and he's working on some cutting edge technologies like DPU, accelerators, persistent memories, serverless computing, function as a service. Well, I'll let Professor Umesh Belur introduce himself.
Thanks, Ankit, and thanks to the organizers for having me here. Actually, I'm no longer the head of computer science. It's a rotating position, and I just finished my stint, which is actually a good thing. Yeah, so I'm currently a faculty member of CS at IIT Bombay. Been working on a number of cloud and virtualization technologies over the past 8 to 10 years. We've recently started looking into the intersection of newer hardware technologies, primarily persistent memory, GPUs, other accelerators, SmartNICs, and so on, and how it intersects with the space of serverless computing as well as storage. I guess the latter is probably why I'm here. And that, yeah, so those are my areas of interest primarily.
Great. It's great to have you here. Next, I would like to introduce Alex Kirchhoff, and he is currently CEO of OnDat, and also he happens to be the co-chair for CNCF. And let me say, his experience is he has booted up computers using floppy drives.
Oh no.
So, Alex, would you like to talk about yourself a bit so that audience knows you better?
Thank you, Ankit. That makes me feel very, very old. I'm sure some of you have also been doing those sorts of things. So I'm the CEO and founder of OnDat, and as Ankit mentioned, I have another hat where I'm co-chair of the CNCF storage tag. And for the last number of years, in my role in a startup, I've been and with the CNCF, I've been focusing on container native and orchestrated solutions. And prior to that, my background was in infrastructure engineering, working with some of the larger financial services companies.
Great to have you, Alex. Next up is Rajkumar Kannan. He's currently with HPE, but then he has worked with digital. He has done multiple things, right from developing file systems, done virtualization, and now doing manageability with the cloud. Raj, please tell us more about yourself. Raj, you're on mute.
Yeah, I think I'm unmuted now, right? Really happy to be here. So my name is Rajkumar or Raj. I work as an architect in HPE, HPE storage division. I have about 24 years of industry experience working mostly in storage. And I've worked on a range of technologies like something you said, right? Virtualization, multipathing, distributed file system, compliance archives. And off late, I've been focused on how we deliver storage as a service to our customers through the hybrid cloud HPE GreenLake offering. So I'm more focused on getting how our file offerings can be sold as a service and the control plane, as well as some aspects of the data path in the backend to plumb this to the cloud and those parts. That's where my interest lies. Other than that, I am also looking at how disaggregated storage is going to change storage architectures and how it's going to make it simpler for building scale out applications on distributed storage. So this is what keeps me busy now.
Great, Raj. And finally, I'm your moderator for the day, Ankit Mathur. I have been doing storage for around 18 years. Have been associated with Huawei and have been doing the next generation unstructured data storage architecture for Huawei for the past 5 years now. So that's all of us in the panel discussion today. So first question, let me try to put it across to Professor Belur. So since you have also been associated with the Synergy group, that is the systems and networking group at IIT Bombay, just wanted your feedback or your views on like when POSIX was introduced as a way of an API to develop applications and then use the system. So it has done some good things and has helped application developers take the pain out of like considering all the different systems, And many of the things the underlying operating system or file system would isolate and keep separate. So what is your take? Did POSIX do its job, or?
Well, yeah, I think it's certainly done its job in a nutshell, but I think times have changed. And the talk on DEOS was a very revealing talk as well. I think the separation of the kinds of data structures that programmers need to play with in memory and the serialized representation in storage, I think that separation has caused some issues. I mean, issues in the sense that something to smooth out, maybe even remove, make completely transparent, whatever you pick, right? So I think the time has come for us to look at that, as particularly in light of newer technologies that support byte, byte addressability, for example, as opposed to a block addressability. There is no reason why we have to, read a file in a serial fashion and bring it back and change all of these to data structures in memory and then start operating on them from a compute perspective. Now, if we can cut that cycle short or make it, completely transparent in a way that really the data structures are the only things that programmers are dealing with and everything else happens behind the scenes. That's what we're moving to, right? I mean, that's sort of what object storage and more flexible storage systems do today. The point is very well illustrated in the talk on DEOS earlier today. So I think while it is there, it's done its job, and people are still using it. I mean, POSIX is the most comfortable interface that people would like to program to, many of them. I think the time has come to sort of look ahead and remove the divergence between a file, holding data and data structures in memory, which are organized fundamentally differently. That's my take on it.
Sure. So Alex, you also look into having a consistent API across multiple organizations. That is a standardization in a way. So what is your take on the same? Like all of these developments that are happening, many of them are happening in isolation, and is it something that's remaining niche, or is it, and still like application developers may want to sit back and do what they have been doing, or adoption of the new technology is on the cards?
Right. I think my one takeaway is there isn't one solution for everything. Different applications and different use cases require a different set of compromises and attributes that are required by the storage system. So and it also depends on, when we're talking about an application developer, are we talking about an application developer, that's building a traditional front-end application, for example, and they just need access to an API to persist information? Or are we talking about an application developer in terms of the next generation of databases, for example, and distributed persistence mechanisms? So, when we look at storage systems, I kind of see storage systems as having multiple layers and multiple layers of abstraction, and in many ways the access part to that storage and the data plane part to that storage often goes through many different technologies. So, for example, you might have an application talking to an API that's going through various load balancers and distribution mechanisms, which then hits some sort of object store, which then does some level of sharding, which then does some level of erasure coding, which then hits some sort of physical media in some form. And all of those things have different APIs and different interfaces. So you'll probably find that in many cases, the object store might in fact be using POSIX on the back end, for example, but this exposing a different API. But the other aspect, I think, is the in order to get the ubiquity, and in order for these technologies to become in common use, you have to have the use cases that can drive them, and even things like object stores took a number of years to get to that level of ubiquity. But because they were simple and because that API was available to be used across lots of different platforms, it has become almost ubiquitous for certain classes of use cases, and now it expands into new use cases as the underlying technology becomes, say, faster or lower latency too.
Sure, sure. So as regards simplicity of deploying applications, so to say, and isolation, Raj, you have experience with virtualization from back in the days. So go ahead, Raj.
Go ahead. I'll let you finish. Sorry.
So basically, what I was coming down to, that virtualization has a lot of good sides. You can package things well, and now even container is a way of packaging your application together. So, but then you are also drawing a line between, like, you can't go beyond this interface. Everything else is a black box. So what do you see as a plus and a minus on having such APIs being able to deploy anywhere?
The first thing, I mean, that's a good thing, right? So to some extent, everyone doesn't want to be looking into the black box, right? That approach works for a lot of apps developers who don't want to get into that nitty-gritty, right? So to have APIs that abstract that and how it's implemented may not be everybody's cup of tea. But if I kind of step back and see what, we can talk POSIX or any of the other kind of subsystems, right? Even I worked a lot on Windows and Win32, for example. The idea is that there's a lot of legacy, right? And the legacy is still alive. For example, you work on protocols, right? So NFS v3, for example, is still the bulk of all the, like, so many customers using NFS v3 still, right? And it's still popular, right? How do you get them? The problem is technology goes exponentially, right? But its usage, which comes down to the application, right? It's still a lot of legacy is alive, right? And so what happens is we still need to end up having to support these hooks and APIs that need to bridge that legacy to the current or the contemporary technologies, right? And kind of provide that as a segue into, eventually migrate them into the new paradigms. And I think abstraction is good in some sense, because everybody doesn't want to be bothered about the nitty gritties, but yet, like in the past, you would have access to everything inside it, be able to tune it, change it, redeploy it, and therefore maybe extract more performance. But here we look at it as more of a, like a building block that you just use. For example, libraries that will not tell you when you use it that it's actually providing you GPU based compute, right? It's providing you access to GPU. But this very same library can use GPU, or it could use CPU, right? And you could build that abstraction, right? So that is one thing that I'm seeing, right? That abstraction is kind of helpful to a lot of people who just want performance out of it, and not like how is it giving them that bridge, right? How is it implemented inside? So in some sense, it's good. It standardizes the way people behave and start adapting new technology, right? And from just the evolution perspective, right? Storage that we are talking about, like from going from way back, data access. I think the professor just said that there's a serial access to storage, right? On that, I would say that today technology storage has gone closer to memory than it was ever, right? It's almost like storage class memory is almost as good, or I mean, it's a little slower than primary memory, but it's pretty much memory centric. Storage is closer to memory than we have ever been, right? So persistent memory is kind of changing. It's a big game changer, right? What does it do to developers today, right? We don't have to worry about caching anymore, right? Everything is cached, everything is persistent. So it's kind of changing that for the developers, right? Fundamentally, and you don't even have to be bothered about how is it coming, because the technology abstractions that are provided, right? NVMe, NVMe over Fabric, and persistent memory technology, they kind of bridge you directly into that without you having to rewrite a lot of it in the application layer, right? So that's my take, I would say, on this topic. That makes sense?
Sure. Yeah. So yeah, I'm bringing the spotlight back on Professor Vellur, and you have been working on some cutting edge technologies. And where does such standardization not work? So yeah, we have talked about how is it good, and how the legacy can make use of things fairly well. But where does it stand in the way, like you see as a bottleneck in future research? Like, oh, it's because standard, and most of the people are there. So
I think this is an age-old question, right? I mean, as programming languages started moving up in the levels of abstractions that they provided, today most programmers prefer to program in Python, which is a little far removed from the machine as compared to, say, people who are programming in C or whatever. So there is that standard tension between how can I get to use the features at a very fine-grained level that are available to me, and then I don't have the benefit of the standardization or a more higher level of abstraction, if you will, because Raj mentioned the question about GPU versus CPU programming. Actually, GPU programs are written differently today. You have to, if you're really programming to the CUDA API, then you have to know the CUDA API. You have to write to it. You can't just deploy a function which is generic and then expect that if a GPU is available, it'll run on it, or not, it'll run on a CPU. That doesn't happen. So I think as technologies are new, and even Pmem, right? Using Pmem is not easy if you're a developer. However, there are libraries that Intel is providing today to try to smooth over access to Pmems and how you utilize them. But these libraries are coded in a particular way. Now, you as an expert may not want to use that, and you may feel that there's more to be wrung out of the Pmem performance than what the library APIs provide you. So there is a tension, and that's always going to be there. I don't think that's going to go away, right? Between the ease of use afforded by a intermediate layer of some kind that smooths over some of the difficulties of handling the technology versus I want to go in there, get my hands dirty, and do something myself. And that's always going to be there. There'll be a few people who want to do this, few people who want to do that. I don't see that changing really. But I think as researchers, we are certainly looking almost always at trying to see whether transparency is something we can provide, at least how to provide transparency. The mechanisms of providing transparency are certainly going to be important. There'll always be a class of people who want the transparency. And it's an interesting challenge in itself to try to come up with these mechanisms, which is what we are looking to do.
So, Alex, you agree, disagree, want to add to what Professor just mentioned?
I think what we're seeing is in this space, in order to get this new technology to end users, is that the place where intelligence in the storage stack is happening is moving up the stack, right? We're kind of seeing a set of services that are making storage more about being application centric rather than being service centric. We've been for a very long time where we've either been, say, presenting a volume of some type to a server or to an operating system instance, or accessing something via an API like a database or a key value store, an object store. And I think now what we're looking to do in especially in orchestrated and in cloud native environments, where we're seeing the developer want a declarative approach for the way applications are deployed, especially with containers where the applications are portable. The developer has a superpower, really. They can specify their application in terms of the container, but also memory, network, and storage requirements. And then the orchestrator can make that happen and in a sense abstract away. And talking about what the professor was mentioning there around the abstraction, I think that orchestration is a large chunk of it. But in order to do that, we're having to see a different paradigm in terms of where the intelligence happens. So we're seeing disaggregated storage and storage being offered as services, whether it's in private clouds that enterprises are building or hyperscalers. And then what we're seeing is additional layers on top of that in terms of things like replication and failover and data protection services and data management services that are getting applied over that. And then we're seeing a layer of middleware on top of that to do things like database services or sharding and things like that. And we're even seeing that apply to how applications now are scaling across regions and scaling across hybrid and multi-cloud scenarios too. So I think the one thing here is that the way that these new technologies are going to become ubiquitous and be adopted is probably, in my opinion, not because end users are going to adopt new APIs, but they're going to probably be adopting the middleware and that extra level of intelligence that's further up the stack that's ultimately consuming those new technologies. And I think if we think about persistent memory, if we think about some of the things like NVMe over fabrics and CXL and other ways of disaggregating storage, I think those technologies are probably not going to be consumed by the end user, but they'll be consumed by that middleware layer in the middle, and that's how they'll become pervasive.
Sure. So now let me take a moment and a reminder for the audience, like you have the panelists here. Please use the chat window and post your questions, and we will take those questions maybe a bit later and ask the panelists what are their views about it. Yeah, Raj, you were going to add something to it.
Yeah, I mean, it's a favorite topic because if you look at disaggregated storage and what NVMe over Fabric, I mean, these are technologies that have been there, right? But they've all come together. If you look at capacities, especially, you can get 32 TB drives today, right? And the sheer amount of capacity that you can throw on in a fabric, and then all of that is pretty much persistent, right? You don't have to deal with caching layers and even the interconnects. We're talking about 200 gig backplanes, right, for interconnects. And clients are talking, essentially you don't have enough bandwidth to actually use the drive's capacity. That's the throughput that it can offer, right? You have dual ported drives all connected. So I think all this can be easily abstracted because today this technology is all built on standard components. It's like RDMA over Ethernet. Ethernet is kind of everywhere. It's kind of going on carrier Ethernet. You can have NVMe over Fabric running on regular Ethernet networks, and it's really bringing the storage and collapsing the storage, compute, memory, all of it into a single entity, right? And then essentially you're able to kind of partition or look at it at a more abstraction, like what are my workloads that are going to use it, right? What kind of tenants can I build on top of it, and how do I consume the power that is being provided to me, rather than worrying about how much of caching that I have to do at the host side and how much I have to manage that. So a lot of that headache, even from a development standpoint, because we're talking about how does it make life easier for developers. I think we can look at higher plane kind of user experience that we want to give to the end user, rather than be bothered about how much we want to manage that storage itself, because all of that is now contained. These technologies provide that kind of ubiquitous access, and their interconnects have matured, and so we are experiencing that at this point of time, right? NVMe over Fabric and disaggregated storage is really turning things around for storage, especially. Kind of making an industry standard kind of architecture, right? Platforms don't have to be very different, and the focus just goes on to applications that run on it.
Sure. So actually, sort of, let me draw a parallel, so to say, and I wanted all three of your views, and more specifically, Raj and Alex. So you have been playing around with cloud yourself in your day-to-day work. So like around maybe a decade or so back, right, the technology of cloud suddenly came in and swept and became so ubiquitous that everyone in at least the industry, everyone has been talking about what is your cloud strategy. If even if they haven't moved to the cloud, they talk about this. So from the success of how the cloud could really sweep everyone along, and like everyone is talking about it, like how can we be there if they are not there, and most of them maybe are also there. What are the parallels we can draw? What are the parallels and bring to making some of these emerging technologies, some of these so successful, like persistent memory, interconnect, CXL, and all? So, like, it's a parallel thing. It's not really the same, but there was few things that really appealed, got adopted. So, are there any things that you see? Oh, well, this could be actually, if applied here, could make it also a faster adoption, faster development, better, faster innovation.
I, I I can go first here. So I think the hyperscalers are already building using some of these new technologies, right? I can't imagine any hyperscaler who hasn't fully adopted, NVMe and some sort of fabric on their back ends to enable disaggregated storage and to provide storage services within their environment. I think what we're also seeing is that some of those technologies that are being built for hyperscalers are also beginning to bleed out into enterprises, and we're seeing things like DPUs and other network accelerators and things like that, which are also being extended to data centers outside of the hyperscaler space. But ultimately, I think what it comes back down to the types of services that those systems are exposing, in the sense that I don't see a scenario in the near future, for example, where you will log onto a cloud provided host and will see some native CXL interface to connect to some sort of storage. I think what they will do is they will be providing that storage capability either as a service in some way, or say as part of a database offering, or an object store offering that they provide you. And we will see then that with services like Kubernetes and orchestrators being built on top, that you will have that additional layers of intelligence being added into the stack to provide that capability. So, for example, today in nearly all the cloud providers, you can get access to instances that have access to extremely fast ephemeral NVMe storage, and that is unbelievably good value for money, because you get the capacity, but you also get incredible amounts of performance. But the problems with that is that it's ephemeral. So it's often used for things like machine learning, but it's also great for any sort of databases or applications or cloud native storage that sits on top, that can actually then provide data services and replication across those instances, and actually give them the failover capabilities and the resilience capabilities, despite the fact that it's just fast ephemeral storage. So I think we're going to see a mix and match of these capabilities, where the hyperscalers adopt these technologies, expose them in interesting ways to the end users, and then the end users build middleware and intelligent cases further up the stack there.
Sure.
Yeah, I mean, great points, Alex. Actually, in fact, it's a good. I would say it takes me exactly to the spot where we are kind of doing some of that stuff, right? Because like you said, the hyperscalers and the cloud infrastructure providers, right? Infrastructure as a service, right? Your AWS and Google and all of these folks, right? They have kind of democratized how you consume your technology, right? You can define everything, kind of put it together, and really you don't have to know too much about it, except for what's your intent, right? The intent of your deployment, what you seek out of it, right? And what the takeaway for us has been from an enterprise perspective is we have been involved for decades in kind of making your data center all lights out and, making that like the cloud, right? Your cloud in the past was basically your data center, your captive data center. And today, I think we're kind of merging cloud and on-prem into what we would like to call as hybrid cloud, for example, right? It's kind of the on-prem cloud into a seamless kind of experience, right? Where you would use your cloud for some things, you would use on-prem for something, but essentially have the same consumption-based model across all of it. Use a single pane of glass to kind of manage the whole thing and the experience. And taking off from where you said the word, right, you would define these abstractions. I would say today we have simplified all the storage provisioning, for example, right? Where do I need do I need a 7,000 RPM spindle versus 15K RPM? Like, who cares, right? Or do I need, like, what is my access speed? It's more about intent. So in fact, one part of it completely where we are trying to make this accessible to our end users, and these people are administrators. I'm not even talking about the end user who's kind of using that NFS or SMB wallet. I'm talking about administrators is they just want to say, hey, this is my QoS, right? I want this kind of throughput. I want to be able to potentially retain my data for so long. And they just say all of those things, right? That's my requirement or the intent. And then the provisioning in the backend, right, which is sitting on this kind of disaggregated platform, gives us the opportunity to kind of compose that experience for the user, right? It seamlessly blends software as well as the hardware into a very composable entity. And it's all potentially possible because of these interconnect and technologies today, right? They are providing you the ability to be able to software define almost everything, right? Once you've set them all up. So that I feel, I mean, Alex, I think that's what you are also kind of trying to speak towards, right? So that is what our take also is today, right? The hybrid cloud experience, right? That spans private data centers and into public cloud.
Absolutely. Yep.
Right. So actually, very interesting point. Like you're talking about something that's composable. Like really, it's not a server that you're picking up. Even if you're getting an instance in the cloud, you're actually asking for, at a component level, what's the kind of QoS or what's the kind of performance characteristics that you need, and you put together a system for yourself virtually, right?
That's absolutely right. And one thing I would I would suggest is we put together in the cloud in the CNCF tag we put together a cloud native storage white paper, and in fact one of the key things that we wanted to identify here was the different attributes of storage. You know, whether it's how you measure performance, how you measure scaling, how you measure durability or data protection, or etc. But because those attributes are at the end of the day what the end users want to consume. They want to define and they want to define, how am I going to scale my application? Am I going to scale it by having lots of clients? Am I going to scale it by having lots of throughput? Am I going to scale it by having lots of transactions, for example? And those actually then define what you actually need out of the middleware and what you actually need out of the backend solution, rather than do I need POSIX or do I need NFS, for example? Those are the definitions. And when you come to the hybrid cloud specifically, it becomes even more important to have that portability, because you really need sort of that software defined layer at the top that's kind of giving you that bridge to allow your applications to move and the data to follow with the applications.
Sure. So Professor Belur, next question. Like you can express your views on this, but additionally, I also wanted to ask you about like we talk about hyperscalers where because of their scale they can also do the investment and bring in some of this. Then individual bigger organizations who have research labs and they are investing, startups which are working on an idea that are going towards something. It may fizzle out or it may see the light of the day if the idea was like you are a university and driving research with your group. So where are you see challenges like in this direction? Because the application writers are elsewhere, the middleware, OS file systems and other things, they are elsewhere. And for the hyperscalers, either you are inside the organization and then your research and technology is for your own organization per se. And I guess you get the drift, right? So what are the challenges going forward?
So I'll just try to address the previous point that the other speakers
Sure.
were making here as well, just a little bit from my perspective. I think storage is a different beast when it, as opposed to, let's say, GPUs for compute acceleration, right? I mean, so storage, I completely agree that people may not want to get involved. The end users do not want to get involved in the nitty-gritties of how things actually go to disk and come back. Really, nobody cares, right? So they want to specify QoS and then say, make this happen for me. And however, GPUs or other accelerators are a slightly different ballgame, right? So if you take a serverless platform where function developers are the people who are actually, sort of deploying applications, and they want to use acceleration capabilities in the cloud that are, they have to be aware of all. They have to be aware of how to deal with it, how to, it's without being aware of the details of how to manipulate these devices and how to leverage them, you're really not going to get much out of all of this stuff, right? I think clouds are at a point where cloud providers are exposing these devices for now. They're not quite sure what the middleware layers on top of this is going to be, which will make GPU programming completely transparent, for example, to the application developer, or any other sort of DPU that may exist on there. Or if you're doing an image processing application, or you want to do some kind of encoding, there's enough accelerators on chip that are being provided today, but you need to know how to use them, right? So I think there's no one size fits all here. It's storage, I think, is a different ball game, and we should talk about that slightly differently than some of the new technology that has come in, which is being used directly by application developers for speeding up compute. That's just the point that I wanted to make on that. With respect to the challenges for researchers, I think this has become a universal thing everywhere. The Googles and the Microsofts of the world are sitting on the data today that really drives research within these organizations, right? And very few people outside of these organizations have access to the data that will allow us to investigate it, take a look at new research problems that can be cropping up because of the presence of the data, and so on. I'll give you a simple example. So for the Azure platform, for example, they are sitting on a mountain of data on the kind of function triggers that are coming in for the serverless Azure platform, right? So what is the frequency of such triggers? Where are these triggers going? What is the duration of these functions? What kind of resources these functions are using? And so on and so forth, right? There's a very rich, there's a lot of information out there, but it's not available to most university developers. The same thing with Google, for example. So I think this has been a question that I've been asking at almost every conference. Right? How do you bring, as a result of which, I'm not saying that all the papers published at these conferences are always by people from Google and Microsoft, but certainly there's a lot more of them today than you would have seen, say, compared to 30 years ago. And that's largely because of the access to this data. I think that's a huge challenge we face in academia, because we don't have access to the scale of data that companies have today within themselves. So any company, right? So you take VMware, take HP, and so on. They have access to customer data that they use for the betterment of their services, which is fine, which is great, right? But it's also used to sort of clean out research problems from the data that come out and so on. So I think that's a challenge, and many people are trying to come together. So Microsoft did release some amount of data. Google has released some amount of data. Periodically, something happens and some stuff comes out, and then we sort of jump on it and use it to the extent possible. But that's the biggest challenge, really. I mean, no question about that. Right. And lots of other smaller things, but that's the number one challenge that we face.
Democratization of data, you mean, right? Make it
Yeah,
available.
I mean, yeah, and I don't really see that happening. I mean, people have confessed that
But
they
there is
don't see
also
it
a
happening
compliance
either.
aspect to it also, right? I think people are wary about
Well,
what they want to do.
I think suitably anonymized and so on, right? I mean, we don't obviously need to know who the customer is, who was calling this function and so on. What we need to know really is what, in abstract terms, what is the resource consumption of a function, for example. And I don't think that's, that doesn't need to be hidden in any case. Yeah.
Makes sense.
So, Alex and Raj, your views about what are the key challenges going forward in research in some of these areas, the DPUs and GPUs. Just for example, Professor Belur brought up that if you're using an NVIDIA GPU, you need to program against the CUDA library. But then if you happen to be not using NVIDIA, still a GPU, let's say from another provider like say AMD, then you are programming against ROCm library. So there is an isolated development, and so this could be challenge. And I think I like the statement earlier in the talk today, which was like there are optimizations and research happening in areas where it shouldn't be happening as well. So that was actually amusing. But then coming back to the question I have is that there are siloed researches that are happening. And so what are the challenges and maybe some solution you think, like if the world were this way, then it would help and make research and bringing things together much easier, because network is going in its path, the DPUs and GPUs are going on their path, and also individually in isolation.
Yeah, I mean that's an interesting question. I must admit it's not I don't have a tight affinity for things like GPU, but I have sort of viewed how technology has kind of changed, especially in the storage space over a couple of decades. And I think what we certainly see is that there are always going to be certain areas, and GPUs and machine learning in general, for example, is an area where they're driving innovation in persistent memory. They're driving innovation in memory bus technology. They're driving innovation in overall throughputs and distributed systems. And we've certainly seen high performance compute and the research in those areas, but also in sort of niche areas in, say, finance, where maybe there was a drive for low latency, or perhaps a drive for risk analytics that drove similar sort of parameters in the storage. And we see those technologies evolve. So things like many distributed file systems, for example, came out of those type of research. We've seen even things like Ceph, for example, which has become almost like the de facto storage for having those object stores, came out of high performance compute environments, right? But we also see, technologies like perhaps InfiniBand, for example, that came out of those technologies, which then, of course, didn't necessarily get to the point of ubiquitous adoption or becoming, commoditized in the way that some of the other things have. So I think there's a mix. I think in all of these things, probably the single biggest thing is whether the technology is too complex to be adopted out of the niche environments. That's probably the single biggest factor as to whether the technology in the research space ends up hitting enterprises and end users directly. I think there's sort of like some level of complexity quota. And if you go above that, it remains niche, and if you stay below that, you get the ubiquitous technology sort of breakthrough. But I think that is always a huge dilemma, because when you're talking about, say, gigabytes or hundreds of gigabytes per second, and you're talking about, distributed clusters and things like that, it is going to be complex, and it's actually really hard to make those things simple.
Yeah, the one part, I mean, from a research perspective, right? I wouldn't say research, but I would say today, at least in the storage and from an enterprise perspective, one of the most important things from a customer's perspective is the cost, right? The cost per GB. It all comes down to that, right? And despite all the research and memory centric computing that, I mean, storage class memories that you might have, if I have to make sure my customer can get a benefit out of that, it'll still have to be within the same cost per gig, right? It has to be near something that makes it, because storage is a volume kind of thing, right? It's not a one-time thing. It kind of keeps growing, and it's a growing problem, right? And enterprises have huge retention and oceans of data like that need to be preserved, and they're kept for internal reasons, analytics, whatever it is, right? So in the end, it comes down to a cost game, right? How can I take that technology and offer it within a certain cost band, right? And we are seeing some of that happen with costs falling drastically with persistent memory. Storage class memory costs have come down, but not so drastically. But we're seeing how we could blend things like SCM with NVMe all flash drives, or how do we use all flash, more consumer or consumer grade NVMe flash drives, and still use software to probably manage write endurance in a way that you can get better life out of it, right? And still give it at a low cost per GB, right? So that is where I would say the bridge between R&D and research. I'm not talking pure research that happens in HPE labs. I'm talking about the stuff that in a year or two we need to get it out of customers, right? And this is where we are focused at, right? How we can take some of that stuff that is still a little more in the lab, but still bring it at a cost economy that makes it a viable solution, because storage is always a growth thing, right? It's growing. You seldom have a problem where you're saying my storage is shrinking year over year, right? It's always going to be growing, right? So everything is about managing that tier, how to manage it cheaply, store it, and that's why tape still exists, right? You still have tape storage, which is pretty popular for the lowest level of archiving, right?
So Raj, what you're pointing to is like it's finally boils down to business. Like if
exactly, right,
if something sells, that's what industry is going to do.
Exactly. And just a point is we just now, I mean, last 2-3 years, I see some enterprise products, right, which are using storage class memory so effectively, right? Maybe they're not using it for actual storage. They use it for metadata acceleration, but it kind of provides that layer of acceleration to how your storage is managed and is accessible to the end user, right? So I see that kind of penetrating into the market in solutions, and probably nobody knows that it's storage class memory. They don't know it's Intel Optane or Kioxia SEM drive that is there, right? It's just a percentage of the total storage there. But software has kind of abstracted that and is able to do something fun with it, right? I would say fun because it's kind of interesting when you look at what we're doing with it. But it's now kind of made it out there, right? People are paying for it, but without knowing how it's actually benefiting them. But it's still a small percentage. Now, in research, you could say, hey, can I take an exabyte of storage class memory and do something with it? Probably you could if you have the budgeting and the funding, but it's going to take a long time before that is something that you can practically expose to your customers. So in the end, it's a business, right? Even whether you're selling it as a cloud provider or an on-prem data center, it all comes down to the cost per GB.
Great. So I thought we
just
were sort of.
I just had.
Yeah, go ahead, Alex.
I just have 2-sentence finishing remark to that because honestly, I loved that summary, but I think taking that back to the storage attributes and how people are consuming the storage, it's actually now become much more refined, and this is something which is actually exciting me. In the past, you used to have a storage system, and the different storage systems would have a different price per gig. And the price per gig, you're right, was the only thing that people cared about. But I think now in cloud native environments, what we're seeing is people are actually willing to pay not just per price per gig, but they're also doing it on different axes. So it's price per IOP or price per transaction, or even price per replica, and the durability of the data and that sort of thing. And so I think now we're able
the
to
services.
Exactly. And so this is the exciting new world that the end users live in, because as they take advantage of these new technologies, they're actually able to carve out the shape of what they need from their applications in a much more granular way and actually pay for the specific services.
Yeah. So I thought I was actually overtime with our session, but then I think the organizers had put in a glitch, and I see that like we are at a train station. If people who have watched Matrix, it's between like lunch starts at like in 5 minutes, and there's a 10-minute window there. So closing remarks, just 60 seconds. So many of our audience might not have experienced it, but then I think all of us have seen like all of the hullabaloo around the Y2K, like how the applications really couldn't move forward. The rest of the technology, Moore's law, everything happened, the lower layers progressed, but then because of the inertia of applications, those issues continue to exist. So in just 60 seconds, all three of you, like the entire stack cannot progress in lockstep. Some of the stack may progress and some of stack may catch up later. Let's start with Professor Belur.
No, you're right. I mean, it's rare that all these new technologies coming in together will be considered holistically by everybody. Different people are just going to take advantage of different technologies the way it suits them. So there's, like I said again, there's Pmem, there's a whole bunch of acceleration technologies that have come in, SmartNICs, TPUs, whatever. Then there is, so given all this, and there are different classes of applications, right? The storage is a class of application on top of all. And then the serverless application stacks and so on and so forth. So each one of them will leverage different technologies differently. That's really all that's going to happen. That's what we see happening already. So
great. So Alex, we always need to take care of the legacy.
We always have to take care of the legacy, and that's the reason why we have mainframes today, still in use, right? But I think if we look at the last few decades of computing, you see the compute and the CPU type environment innovate and iterate very, very quickly. You see networking iterating a little bit slower, and storage iterates even slower than that. And the reason for that is because it's harder. There are harder problems to solve to innovate in some of those spaces. And And then finally, applications iterate the slowest in my view. And sometimes you go into organizations and they have applications that have been running for 20 years. And so in order to take advantage of these new technologies, I think the middleware and the intelligence further up the stack is where the game is going to be at. And if the innovation doesn't happen there, I think a lot of those applications will be stuck on older platforms.
Sure, thank you. And I see Reena is already back on stage, so maybe in 30 seconds, Raj, before she purges us out.
Yeah, I think from a business perspective, I think the legacy is still a big thing for businesses, right? Legacy apps especially do not transition that fast, though we want them to, so that we don't have to support them forever, right? We want them to move to new things so that support gets cheaper for enterprises, but it doesn't happen that way, right? If they're happy, a lot of apps, like Alex said, they 15, 20 years, you have the same thing running, right? And supporting that, that is still that. I think that's the lowest kind of change that happens in that area, right? So I think paradigms like software as a service, for example, right? People are moving away even from owning those apps. Those apps are just subscription based, and those are sitting in cloud, which is again pieces of components which are kind of giving you a service based on what you pay for, right? So I think that might end up kind of giving you an end-to-end experience where everything is kind of caught up on the latest and greatest, right? Your software as a service, your infrastructure sitting below it as a service. And so the interconnect and everything is whatever you paid for, right? You want the highest throughput, you probably got the best, right? Composed for you. But truly the legacy is there. Like I said, NFS v3 we see is so popular, right? Though 4.2 is still is there, and URN protocols. I'm just saying it's not going away. Even today we talk about NFS v3 in a big way, and so it's the mindset change and adoption and changing the legacy,
Sure.
right, which works, and taking advantage of the backend. That needs to happen, right?
All right. Yeah, great thoughts, Raj. And thank you so much, Professor Belur, Alex, and Raj for joining us today. And those are some great views and from your experience and from the industry and academia. And yeah, thanks, Reena, for giving the extra minute here. Back to you. Thank you.
Thank you, Ankit. Thank you so much for moderating the entire panel discussion. Hearty gratitude to all our panel members for taking time out and joining us for the session. Thank you so much. And those of you who have joined us here, still with us and ready to chat with us, please type claps on the chat box. Thanking all our panel members for taking time out and joining us here. I want to see claps coming in on the chat box. I love that. I love that. I love to see the responses. I love to see the emoticons being shown up there. That's brilliant. Fantastic. So on that note, it's time for us to take a break, but listen to me completely. We want all of you to be back as quick as possible, say by 1:30 p.m. By 1:30 p.m., we will have you all back and the sessions will continue because we've got amazing sessions that's lined up for the afternoon too. We have a session by Kishore Sampath, followed by Sundara Ramalingam. And we also have Professor Jelin, who's taken time out and joined us today. And we also have Yusuf Ildiz, who will talk on TBD. And we also have another special session by a special speaker today. And that is Professor Onur Mutlu, who will tell us more about fireside chat and a lot more, which means all of you get to speak to him. And you can leave your questions again on chat box, and Professor Onur will answer to it. Well, this is going to be an exciting afternoon, and we will now take a short break. See you all back by 1:30 p.m. Indian Standard Time, which means that's about 37 minutes from now. See you all very, very soon. Thank you. But though I'm not seeing too many of you participating here, I have like 5 of them giving me the right answer. We have 49 people participating. Would be great if all 49 of you contribute to the right answer. Even if it's wrong, it's okay. Doesn't matter. But contribute to writing the right answers on the chat box. What according to you could be right. But here's my next question. Listen to me carefully. On a TV or a computer, the monitor that you see, what does the measurements, for example, when you say 42 inches or 50 inches, refer to? When you talk about a TV or a monitor, what does it refer to? Is it A, height? Is it B, width? Or is it diagonal? And this time, Ankit is like, I am going to win this. I'm going to make this big. I am going to take those vouchers home. He's been the fastest to give us the right answer to this question, even before I gave the options here. Ankit, that was awesome. Congratulations. Looks like the fight is between you and Mohammad Ashraf there. Let's see who takes home a lot of vouchers. I think, was that from one of the gold store? Is that Jos Alucas, Bhima? I don't know which one is that, but I'll soon tell you which one would that be. Mahendra, congratulations. Divakar, Santosh, Venki, Ravi, Sanjeev. Looks like the questions are getting interesting because I see a lot more of you participating. Now I have 2 or 3 more names coming in. Thank you, Janaki. I love that. I love to see more responses here. Well, the first person to give us the right answer is Ankit. Congratulations to you. I'll soon tell you what the voucher will you receive. But moving on to the next question, this time I'm going to be as quick as possible. I'm going to stick on one question for 15 seconds only. My question is, before becoming the web's video giant, what was YouTube supposed to do? Why was it built? What was it supposed to be? Your options are A, music download site, B, video dating site, C, a virtual movie theater for independent use. These are your questions. Before becoming the web's video giant, what was YouTube supposed to be? These are your 3 questions. Ankit has written virtual movie theater. Asif says it's a dating site. Mohammed says C. That's the fastest. You know, you're still there. And we have so many of you giving us the right answer. Well, the first person to give us the right answer, I'll come to it, but most of you have been writing all 3 options. Okay, I see all ABCs here. In that case, Ankit, that's the wrong answer. The right answer is what Asif Ali Ahmed told us here today, and that was a video dating site. Initially, in about 1991, YouTube was supposedly to launch. It's much prior, probably it's 2005. In the year 2005, YouTube was supposedly to be launched as a dating site, and that's Feb 14th, 2005. That is 2005. And Asif has given us the right answer. Congratulations to you, Asif. And we have so many of you. Mohammad Ashraf is still in the race. I like that. I like that. You've already received 1 voucher. We have Ankit for the second question. We have Asif here for the third one. I'll ask you one final question before we head on to our sessions here today. And that is, what is the unofficial name of Android's green robot mascot? Is it A, Androbot? Is it B, Krubdroid? Or is it C, Bugdroid? My question is, what is the unofficial name of Android's green robot mascot? Is it A, Androbot? Is it Krubdroid or Bugdroid? Looks like the only person who's given the answer correctly and the fastest answer, that is Asif. That's my question. You've written green mascot. You supposedly choose one amongst the ABC, and that is Janaki, who's told us Bugdroid. That's the correct answer, Janaki. Congratulations, Dr. Janaki, for giving us the right answer there. So fantastic. Santosh has also contributed to the question. I love this. I love to see, and I'll soon come back and tell you what are the vouchers that you can purchase yourselves at these gold stores. But I love the participation. I love it. I love to see that so many of you participated. And I hope you took your break, you had your lunch, you're all refreshed, you're looking forward for the session because the time's begun. The time's begun for our next session. Stay with us. This session is on data caching solutions, software, practice, and experience, and being led by Kishore Sampath, storage expert. Hi, Kishore, are you here with us? Do we have Kishore Sampath with us? Kishore, are you here with us? Are you taking a little time before we set up the technical side of it? Are you here? We'll just wait for Kishore to join in. Meanwhile, you do know that you get a lot of applause here. For those of you who participated in Weighted quizzing here today and you've got the right answers, come on, type applause on the chat box before we head on to having Kishore with us this afternoon. Could you all please type applause or could you please type claps on the chat box? Ankit is like right there. Celebratory mode is on, he says. Mahendra Takwade, Santosh Paul, thank you. You're all applauding there. Thank you, Saurabh. Thank you so much. I want each of you to type applause. Congratulations again, Dr. Janaki, for giving us the right answer. And you've been typing applause there. Sanjay, Dibakar, Mohammad Ashraf. Fantastic. I love that. I love the thumbs up too. It's great. It's great to see all of you participating here and all of you congratulating each other, right? So we do have some quiz that's lined up later on too, but the afternoon sessions are very, very important as we have our speakers. The first session will be led by Kishore Sampath, followed by the next session is from Sundara Ramalingam, who will take us through the recent advancement in AI computing technologies. And the next session is on co-designing distributed storage with programmable network hardware, which will be led by Professor Jialin Lee. And we have our next session from Yusuf Ildis, who will take us through the topic using LinStore to make your infrastructure failure resilient and boost with persistent memory. And after which we have the most important session of the day, which is a closing session towards closure, which will be led by Professor Onur Mutlu, and that is a fireside chat. Well, on that note, we're just waiting for a moment until we have Kishore joining us here this afternoon. Meanwhile, if those of you who are here with us, we'll just take a moment. I have my questions ready, and I'm sure you will be looking forward to answer. Meanwhile, my next question is going to be very, very easy. I don't know how many of you use Twitter today. If you use Twitter, could you please write yes on the chat box? If you do not use Twitter, can you please type no on the chat box? I want to see that because my next question revolves around Twitter. Hi, Mahendra. Fantastic. A lot of yeses. Oh, I thought a lot of yeses. No, a lot of no's indeed. Many of you do not use Twitter. I get it. It's the millennial kind of thing because we like to tweet everything about us and everything that probably the tiniest detail that didn't go as we wanted it to. And we tweet about it. We tweet. Sometimes you get responses, you're grateful for it. Sometimes you don't. And well, a lot of no's, but my question still stands. I hope you guys know it. Let's just try it out. If not, we learn something new, and that is from 2017 onwards, how many characters long can a tweet be? How long can a tweet be? How many characters can you use to tweet something? Is that 140? Is that 280? Is that 346? So you have three options there. Is that 280, 140, 346? Well, I have answers coming in. The only moment is to see who has given us the fastest correct answer on the chat box. And the fastest to do so is Mahendra Takwale. 280 is the correct answer. Congratulations to you. And this was previously 140 from 2006. It was later doubled. And that's the right answer there. Fantastic. And it's okay, Dr. Janaki. Doesn't matter if the answers are wrong. We love it. We love to see the participation that's coming in here. Well, on that note, I'll just quickly look through the answers. Did I miss on something here? I want to see if I missed out. No, Sanjeev has given us the first correct answer. Sanjeev Kumar. I stand corrected. I probably said Mahendra has given us the right answer, but the first person to give us the right answer was Sanjeev. Sanjeev, congratulations to you. Meanwhile, my next question to you, and that is to all of you here. You can participate, all right? That is, aircraft flight recorders are often known as black box, even though they actually aren't of this color. Which color is the black box? Well, looks like Ankit was waiting for this question. He's like, I don't care. I know the answer. Even before she completes, I'm going to type it through. I know I probably think this is the right answer. And Ankit has given us the right answer, and that is orange color, which is
The fastest correct answer. Ankit, go in. You've made it 2 points there. Fantastic. Congratulations. And to all of you who've been participating, I had a great time talking to you. Our talks will continue, but now we have our speaker who's joined us right here for the session. Ladies and gentlemen, wherever you are, please type welcome on the chat box because we have with us Kishore Sampath, our storage expert, who will lead us through this session. Hi, Kishore. Good afternoon. Are you doing great today? You're on mute, Kishore.
Hi, thank you very much, Reena, and hi, everybody. I'm very glad to be part of this IEEE Data and Storage Symposium, and look forward to I hope I'll be able to give you a very good session on my area related to data caching.
Over to you, Kishore. The stage is all yours.
All right, I will share my screen. Please confirm to me if everything is in order, okay?
Absolutely.
Is that showing up all right?
I guess the presenter right is just given to you.
All right. So once you confirm, I'll proceed.
Yes. Back in, please note, Kishore is sharing his screen. Have we pinned his screen? Are you sharing your presentation, sir?
1 minute. What I did, I'll just confirm that.
Yes, please.
Yes, I'm sharing, yes.
Perfect. We can see your screen.
Yeah.
Over to you.
So I'm in the full screen mode. Is that visible?
Yes, you are.
Thank you. Thank you very much. Hi, everybody. The topic I'm going to speak on today is data caching software, practice and experience. Hi, I'm Kishore, and I'm the founder and CTO of Storage Brew Private Limited. I've worked for over 30 years in developing storage and infrastructure software on Unix and Linux. I've worked in various companies. I've filed quite a few patents, most of them on data availability, data performance, and data caching. My expertise in clustered volume managers, data mirroring, and data caching in particular, and Linux kernel in general. Those are my contacts. Let me go over the practices in data caching software. Let's start with the basic theory, and then I'll drive home the various aspects involved, the problems that emerge, and what is being done about it. So the fundamental theory of how caching operates is when you have access to data, there is an IO read, and there is a cache layer that does a lookup. If there is a miss, it goes to the disk. And then what you get is performance X. The same thing is shown on the right side. Without caching, an IO read goes to the disk and gives you a performance X. If there is a cache layer, it does a lookup. If there is a miss, it goes to the disk. But before the IO completion, the cache is filled, which means the cache device needs to be updated. After which, the IO is signaled as complete to the IO read issued. This completes the IO read. Note that the IO for the update of the cache usually does not result in any penalties because the performance of the cache device is 4x to 10x of the regular disk. Hence, the update happens fast enough not to have any noticeable delays or overheads. After this, on every subsequent IO read, a cache layer does a lookup. The lookup results in a hit, and the hit results in a read from the cache, and the cache responds at the speed at which the cache device can operate. So a typical enterprise SSD can operate at least 10x times speed of the regular hard disk drive. This is how you have the caching going on, okay? You can have advanced read-ahead caching also. Linux buffer cache, for instance, does this kind of scheme where the file system code goes and does a read ahead. So if you have a particular set of blocks read, it will go and try to read ahead and then tries to pre-fill the cache. That is the simplest scheme. There are advanced schemes where you have a control layer through which you can have a read ahead loop so that the cache layer can reserve a separate scratch memory. For instance, in media, a lot of media software require certain buffers to be pre-filled so that there is no jitter while viewing due to temporary loss of connections and so on. So there are separate control layers to ensure that there is a separate scratch memory through which you can fill the cache, so that, as a typical example, there is a buffer that can hold 15 to 18 seconds of your video, whereas what you really need is only 2 to 3 seconds. So this kind of advanced schemes are also implemented, but the idea is the same, that you do a read to fill the cache. Let's go over the nuts and bolts now. For caching, you have different strokes for different folks. That is the caching policy, right? So you have write through caching, write around, also called read through caching, and write back, also called write behind caching. In all these caching schemes, the reads are handled in the way I explained earlier. That is, the read happens from the cache. If there is a miss, then you have to fill the cache. If there is a hit, you read from the cache. This is the same scheme used in all these caching policies. The difference comes in the writes. In a write through caching, writes go both to cache and data disk, and write around or read through. Write only goes to the data disk. It invalidates the cache. In a write back, write goes to the cache. It's written in a delayed fashion to the backend. Let's go over each of these to understand how these writes are happened. So I've explained the read already. Hit, read from cache, miss, fill the cache, correct? After that, you serve from the cache. Writes, there is variety and there's a reason for that. And I'll try to give typical examples on why these are required. Take the example of writes in write through caching. If a write comes, the cache layer does a fork of the IO. That is, an IO is issued both to the disk as well as to the cache device. So the cache device is always kept up to date. But notice that since it is written both, the source of truth for data comes from the disk only. Always, when in doubt, you go back to the disk. It has to be reliable. So the source of truth is disk. The cache is also updated on all writes. Why is this done? So that on subsequent reads, your reads can be processed at a performance of 10x, correct? Where is this heavily used? Take the example of a Linux file system. You have a 2 terabyte file system, and then it's already populated. And as in when you read the various metadata of the file system, it will get updated and then will be in the cache. Later on, if you do metadata updates, they better go to the disk, because if the system fails and then when you come back, if the cache device is gone, you should ensure that the disk always has the data, right? If the cache has a problem, you should be able to go to the disk. The disk is the source of truth. So write through relies on writing both to the cache and the disk, but the source of truth is from disk. What happens if the cache write fails? If the cache write fails, the cache is invalidated. The portion of data written to the cache is invalidated. Disk is still fine. What happens if IO to the disk fails? Even then, the corresponding data blocks in the cache are marked invalidated, so that you have no valid data for that in the cache, and the read always picks whatever is on the disk. So the disk is the source of truth for write through caching. All right. What about write around caching? In write around caching, when a write comes, the cache layer first does a lookup. It finds out, is there a hit? If there is a hit, it goes and invalidates the cache. Remember, we're talking about writes here. When it invalidates the cache, and then it is deemed as a miss and directly returned to the disk. In effect, what we are doing is that every write results in cache invalidation. What is the goal here? The goal here is to ensure that writes do not populate the cache. But as we already said, all reads populate the cache. So clearly, write around is very useful when you want reads to populate the cache, not the writes. Where is this heavily used or useful? In a multiple set of scenarios. Say you are going and initializing a file system for the first time, a 2 terabyte huge file system. You do not want to go and write everything to the cache because you do not know the dynamics of the usage of the file system yet. So based on heavy usage alone, you want to fill the cache, not on write. So write around is ideal at this point in time because you want to go ahead and not write to the cache but to the disk, and you want the cache to be populated only when the corresponding disk regions become hot or continuously red and thereby fill the cache. You see, so write around is very useful when you want reads to populate the cache, not writes. Okay. Write back caching. Write back caching operates in a way where you want to maximize performance due to the cache. Now your write comes, the cache layer commits the data to the cache. It updates the cache, but it does not write to the disk. As you can see here, no disk writes to the disk at that point in time. So the application or the IO writer who has issued the request is signaled completion at a rate of 10x performance. So they get very good performance. The cache is then returned to the backend disk in a delayed write manner. So the delayed write is to ensure that the disk is in sync because finally the disk also should have the data. Where is this used? This is not used in too many cases. Though it at the face of it, it looks like this must be the most popular one. This is not. I'll explain the problems with this later, but it is heavily used in a couple of scenarios where you say, for example, you have a high performance computing application in various weather forecasting and related to oil exploration, natural gas exploration. In all these high performance setup, you have huge, large 1 MB, multi MB reads and writes happening. So there, you pretty much don't need caching because they're very large writes. So disks perform very well on large sequential writes. But then there is a lot of other workloads that are small writes. The small writes are a huge problem because in such large multi-disk, RAID 10 configurations with 40 disks, 60 disks, small writes will result in pre-filling and writing the whole stripe of data. When that happens, performance really tanks. But then nobody can predict that there are no small write workloads coming in between. So there's a huge amount of jitter, and there is no predictable performance on all these large IO workloads that are primarily used, but there is no guarantee on small write workloads also coming in, and you want to give a guaranteed performance. The graph has to look even, otherwise you cannot predict anything. In these cases, write back is a boom. What is done is all the small writes are committed to the cache, and then they are not updated to the disk at that point in time. And then as and when more small writes come, they can even be coalesced very beneficially, and it does happen very often. And all these coalesced writes can then be returned to the disk in one shot, almost as a sequential IO. And also, you not only absorbed the small writes into the cache, but you also coalesced them and then made them sequential, though they were not sequential to start with. But this comes at a price. The cache itself is now a single point of failure. And your disk, which is does the heavy workload, should have the data. So there are issues. We'll discuss those things. But as you can see, write back is more complex, but very beneficial for workloads where you benefit from writes. It's not for heavy writes, but it's for small writes primarily. Okay. Those were the basics of read different kinds of policies. I'll switch over now to tell you my experiences and then what are the issues in all the things we just talked about. I worked as a chief architect of many SSD-based data caching solutions on Nitro XT in LSI Avago. There we implemented write through and write around caching. I worked on the small block acceleration for L300, G300N products in Seagate, where we also, in addition, implemented the write back caching, which I just talked about. And right now, I'm the founder and architect of Speed Cache in a startup I founded called Storage Brew. And this is a Linux SSD caching of built ground up, which has only write through and write around caching. Okay. This is my experience of over 8 to 9 years on caching exclusively. I want to give you an overview of the various things that I have evaluated, studied, and tried to understand, and want to share with you what exists out there for data caching software. There are different flavors. Can be on Linux servers, and it could be on NetApp or kind of NAS boxes. So we'll go one by one. On Linux servers, there are quite a few choices. On Linux kernel, you have Bcache and DMCache. They're open source. Intel, Facebook, and STEC, now bought over by Western Digital, have their own softwares, CAS, Flash Cache, Enhance IO, which were quite popular before. All of them are currently inactive. On hardware firmware, there is a lot of activity today in data caching software, actually. So Samsung, Western Digital, Intel, AMD, PMC Sierra, Broadcom, Avago, all of them have their own either hardware-based or firmware-based caching. And I've listed all these things here. If you see, notice interestingly that a lot of such software and hardware combinations from Fusion IO, FlashSoft, Virident, Velobit's HyperCache, right? All that got acquired by Western Digital. And now none of them are really having any life. All of them have been kind of either lost completely or have been integrated in pieces into their own hardware-based caching. Samsung similarly acquired NVLOS, Dataplex, Proximal Data, which were all, many of them were software solutions. Now they've either been used for some time or integrated in pieces, but don't exist in the original form. Primarily hardware-based caching from Samsung today. So Intel and AMD, they have their approach of configuring an SSD for caching at hardware setup time. Intel has Smart Response Technology, SRT, and AMD has Store MI. PMC Sierra has Max Cache, which is a firmware caching solution, and Broadcom and Avago, they have the firmware-based caching solution, which they inherited from LSI when Avago bought over LSI. On HPC systems, Nitro XT, which I heavily worked on, is now part of HPE. From LSI to Avago to Seagate to Cray, now acquired by HPE. That's their HPC systems caching, or HPC systems, high performance computing systems caching, which has different set of issues, which I told you about, the write back caching to absorb small block acceleration related issues, right? And then DDN is a major player in high performance computing. They have IME, Infinite Memory Engine, which has its own caching. On NAS, you have various solutions by various NAS providers, which I have listed here. As you can see, NetApp acquired Cache IQ, PlexiStore, which are again software solutions, but they're all integrated into NAS. So these are the various places where caching has been implemented. And as you can see, variety of deployments, different issues. On VMware alone, there's a class of them, which I've listed here. Most of them got bought over, like Pernix, Data, AutoCache, or bought over by Nutanix and Samsung. VFRC, VMware's own homegrown, is now deprecated. They will no longer be using it. FlashSoft got over by Western Digital. And then Virtu Cache for Virtunet Systems is one of the leading ones on VMware today, and Infinio as well. These are the various solutions on just on VMware, because they have a different set of interfaces. Problems in caching software, past and present. Write back caching is very risky, very single point of failure based, because it's not easy to address it. A cache disk fails, everything goes for a toss, right? So very difficult to address because now it has to be in a central place. It should be distributed. Otherwise, it's impossible to ensure caching that can be retained, right? Single point of failure requires strong data consistency guarantees, and write-back caching is not used in the most common scenarios apart from small block acceleration. So it's not very popular, okay? Memory requirements defined by all caching policies supported results in too much of cache used unnecessarily. You support write back, you need huge amount of memory, but in reality, you really don't want write back caching many of the times, but you can't deconfigure it. So you're stuck with too much memory requirements. Lack of granularity. If you see, most of the caching solutions have a cache line size of around 4K. Now, the moment you have 4K as the minimal granularity size, then all the algorithms are now based on doing a IO range interlock and shared synchronization locks, everything in 4K. But the workload itself may have no overlaps in that 4K region, but because of your lack of granularity, now you have to mandatorily assume that it is an overlapping IO and do interlocking and synchronization locks, which is a huge overhead. These are the problems. Poor IO tracing capabilities. There are tools like BlockTrace, which give low-level IO tracing, but that cannot be correlated between high-level IOs and IOs issued to underlying cache devices and disk devices. So overall, most of these do not have very good tracing capabilities at all. Cache metadata allocation scheme, user has no choice at all today. If you see, either it is guaranteed performance through static allocation, which is more common, or dynamic allocation, which doesn't have predictable performance. User would want to choose these. Poor configurability. Most of these caching systems have baked in all their algorithms for searching. For large hash tables, maybe some situations, if it's write intensive, red black trees are better. If it's search intensive and not write intensive, AVL trees are better. Skip lists are handy in some situations. So these are the choices. For cache replacement, it could be LRU, MRU, or you may have your own custom replacement. You need choices, but there are no choices today. Real-time memory calculations for kernel memory needed, you hardly any today. The amount of real-time memory used, you do not have a window into it. There are not enough control knobs in caching. Just ensuring a pass-through so that you don't cache, or no pass-through but is enable caching will not do. You need to have more robust schemes where you can have active and passive caching so that you can say, I want to cache, but what I've cached is enough. Now don't cache anymore. You need more controls based on IO workload, based on sizes, and so on. Hinting frameworks are coming in, but again, that's not enough. Poor visualization. This is an area of analytics which analytics is heavily needed, and you need good visualization using monitoring graphs, cache warmth graphs, distribution graphs for IO. All these are needed. So there are newer ones that are trying to address some or all of these. Cache Live from Facebook is a very interesting choice. It's come out very new. It's an open source new caching library. Speed Cache, which I have architected, also tries to address many of these problems. So Speed Cache, the one I've implemented, has many of the features that addresses the problems I talked about all kinds of cache allocation policies that you can choose from, dynamically enable, disable, or active passive caching, good IO monitoring, good tracing, and advanced analytics for IO pattern analysis and hot and warm cold data analysis as well. This is the architecture. In the interest of time, I don't want to continue too long, and I will explain various things in the context of questions as they come up. So it's given good performance for 45 million files, listing of a massive photo database kind of directory search. We have with and without speed cache enabled, as you can see, it was 6 to 7 times better performance with speed cache. FIO is a standard tool in Linux. We get very good performance for with and without speed cache, very good performance. And then for VDI workloads, tried with Ubuntu VMs and Windows VMs, excellent performance, at least 3 to 5 times compared to without caching with speed cache. So I'll stop here. These are the features in detail. This is the monitoring interface we've come up with, which gives you fairly good analysis of the IO, IOPS, and then spread of IO and workload among multiple cache devices, and so on. Okay, I'll stop here for questions.
Thanks a lot, Kishore. So the first question we have from our HQ China, we have an engineer who is working currently on the power consumption of the SSDs and HDDs. So is there any difference in the power consumption when we do a write back or write through?
I didn't ask what the bar consumption. I didn't hear
the
that.
Power, the power consumption.
Yeah, right. Between write back and write through, you said?
Write through, yes.
Okay, yeah. See, write back and write through are almost similar. So I won't be able to really distinguish between write back and write through in terms of power consumption. I would say if the question was about write back, write through versus write around, I would say write around gives excellent savings in power consumption. Write back is marginally better than write through because it tries to coalesce and doesn't write everything, tries to coalesce a lot of writes and then tries to write once. So it's marginally better, not noticeably better. And the reason is this: write back and write through both write to the cache. It's just that in the case of write back, certain writes are coalesced to be written later, to delayed write. So there is. But the thing is, too much of delay causes too many issues. And more importantly, write back, the use cases are not for regular file system, regular usage semantics. They're for high performance computing kind of workloads where you need small blocks to be written. So from that point of view, not a big. Theoretically, write back is better performance for power consumption. Practically speaking, not much.
Sure. Great, thanks a lot. And then the next question is the read ahead impact on the Pmem. So do you recommend or have you seen any use cases where the read ahead done by the file systems are cached to the Pmems, and because read ahead, there is a probability of not being used at all. So do you see any advantage of or any use case of doing a read ahead on Pmems?
I see advantages of using read aheads in the cases of semi-sequential workloads. That is a smaller percentage. Some of those workloads which are semi-sequential, like media-related workloads, always benefit from a little of read aheads.
Right.
But many practical workloads are quite random in nature. They don't benefit. But if the granularity is small, and which is very important, if the granularity is small in caching, then read ahead is useful because usually many of the IOs from the user space are in the range of 4K to 128K. So if your granularity of caching is itself less than 64K, or say it's just 32K, then the chances are you will benefit. So it's a function of the workload in terms of how sequential it is, and secondly, the IO sizes.
Thanks a lot. So sorry, I had some glitch. I lost you in between due to my headphone. So I'm being pounded with a lot of questions. Rina, I think I'll have to take a little more time, borrow some more time from you. So the next question we have is from Saurav. So the question is, what kind of consistency model is used in speed cache? Is it strong consistency or is it eventual consistency?
It is strong consistency. Yeah, it's strong consistency. And the motivation for that was that most databases, if you see realistically, will not even touch your software if you cannot give strong consistency.
Okay. Again, from Saurav, the next question is how to ensure data and metadata consistency when same set of files or directories are being accessed and modified by multiple applications, or in terms like if in case the file is centric towards the M-time update and so. So what type of consistency or what type of mechanism does speed cache use?
Correct. See, it's a very good question. Unfortunately, it's outside the realm of speed cache. See, the consistency of the metadata versus data that you brought up really comes from the file system. So if you see, I have to explain it in the context here. If you look at the architecture here, the way I have designed is that the IO comes from the file system into the Linux kernel and is issued to the block driver. And from the block driver through a filter driver implemented using device mapper, we reroute that to the speed cache driver and then decide whether it should be cached or it should be just directly sent as a pass through to the backend hard disk drive. So the decision related to data, metadata is already done by the time it comes to speed cache. I've implemented this consciously to stay away from too much of integration to file systems and therefore be able to scale across all kinds of file systems and also provide a transparent level of caching which is non-intrusive. But that comes with the downside that you do not have insight into the file system logic that you just talked about.
And I think the next question is from Raja. It's on the same context that when we're talking about host-side caching and then being connecting Saurav's question where multiple client servers are communicating at the same time. So what are the benefit of host caching when they are connected to a NAS system which has its own caching?
That is correct.
Yeah. So yeah, please go ahead.
I get the question. Yes. I would say upfront, a blunt answer would be, and an honest answer is very limited. Okay. Having said that, very limited to the extent that I myself would recommend that you do not put SSD-based caching on the clients. You should be putting on the SSD caching on the NAS server side. Having said that, if the client-side workloads are substantial, which does happen in some of the HPC workloads, then you will benefit because the client side itself is considerable. The amount of IO that happens and the hits that are coming. That's very specific to HPC though. So in practice, a practical answer would be that yes, there is not much benefit at all from having SSD caching on the client side in a client server setup. It's primarily on the server side that you get benefits from.
Okay, so mostly if it is a one-to-one comm, that's when the host cache plays the better role.
Absolutely correct. Absolutely.
I'm still being pounded with a lot of questions. So in the interest of time, can I request you that I'll unicast the messages to you on the WebEx chat and request your time and help to answer them out.
My pleasure. I'll gladly answer. Yeah.
Thanks a lot, Kishore. It was really nice session, and I guess it was so well put that people are pouring in the questions. So thanks a lot for that, and kudos to you.
Yeah, thanks you organizers for helping me out. I had some glitches in the beginning due to my internet. Thanks for filling in, and the audience for patiently listening and asking so many questions. That's what keeps it interesting and alive. I'll be glad to answer on the chat after the call. Yes.
Sure. It's our pleasure. Back to you, Reena.
Thank you. Bye-bye.
All right, so I am filling in here for Reena. So our next session is by Sundara Ranglingam. He is Global Director for Deep Learning from NVIDIA, and his session is on the recent advancements in the area of AI computing technologies. So a warm welcome, Sundara. Over to you.
Thank you, Ankit. I think somebody needs to give me presentation rights so that I can share my screen, please.
Sure. I think you should be able to share now.
Yeah. Excellent.
Yeah, you're good. Thank you.
Thank you. Are you able to see the full screen part of it?
Yes, yes. We can
Excellent.
see your
Thank you.
slides.
Thank you. Good afternoon. My name is Sundar Ramalingam. I work for NVIDIA and I deal a lot with the AI consulting program that NVIDIA runs, where we work very closely with solution providers and enable them in the recent trends in AI computing techniques and adoption of AI and helping them with the recipes of success when an enterprise is trying to adopt modern AI, machine learning, and deep learning techniques in their workflows. So over the next, I would say about 30 to 35 minutes, I'll run you through the recent trends that have been happening in the industry so far as AI computing is concerned. And possibly we will have about five minutes left for Q&A as well. So just to set the stage, I think this is commonplace knowledge now. I don't think I need to repeat it, but very quickly, today's business, modern business is driven by AI. And it is across verticals and industries. I mean, it's not restricted to any specific industry. That was the case like about 3-4 years ago, when there were a few industries like, retail, healthcare, etc., that had a faster adoption when compared to others. But today, more or less every industry is embracing AI in one form or another. Retail, in terms of supply chain and inventory management, dynamic pricing, telecom in terms of specifically 5G. Once again, the core 5G itself and the applications of 5G, where many modern workflows run much faster thanks to the speed provided by 5G. Healthcare, in the areas of medical imaging, genomics, proteomics, drug discovery, etc. Manufacturing, the modern AI-driven factories. Financial services, consumer internet, a big vertical that uses AI, specifically deep learning quite a bit in terms of serving the recommendation engines, personalization of advertisements, churn reduction, etc. Oil and gas, once again, traditional machine learning techniques, and more of modern machine learning techniques are being used. And last but not the least, automotive, the self-driven cars, about which a lot of excitement is happening in the modern world today. It is all possible thanks to deep learning techniques. Now, that's a very short introduction, and I specifically kept it short because I think this is more common knowledge to all of us. But what goes behind this scenario, and what type of computation happens, what type of high-performance storage and networking happens for all this to run seamlessly? That is what I'm going to focus on in the next 30 minutes or so. Now, excuse me. If we look at any deep learning problem, right, there are two major substreams contained in it. The first box represents what we call as training. I'll explain this with the help of one example. Let's say my task is to recognize faces, okay, face recognition. The art of creating the deep neural networks, what we call as deep neural networks, which are nothing but models that can detect faces and identify, hey, this face belongs to Sundar, this belongs to John, this belongs to Julie, etc., etc. That type of recognition, the models that are needed, AI models that are needed to recognize them, those are created in the data center, and that is what we explain with the term training. And a very typical characteristic of the training need is that there are two prerequisites. Number one, it needs to handle very large amounts of data, huge amounts of data. And number two, it needs to work with very complex models, AI models, right? And both these things, one common underlying factor between both these things in terms of the ability to handle very large amounts of data and the ability to run very complex models needs enormous computational power, brutal computational power. Now, this is one part of the work stream, like I said. Assuming I have a great model, a set of models that can recognize faces very well, and it is running fantastic in the data center, testing is running fine. But what will I do with that in the data center? It's need to be deployed, maybe on a police station or on railway platforms or on the airport entries, etc., where actually smart cameras will be able to look at faces and recognize that this face belongs to this person, and hence this action needs to be taken. So whatever was created in the data center needs to be deployed, needs to be implemented at thousands of places. And that is what we mean by inferencing or deployment. And that is what is represented by the second box, right? And one very important characteristic of the second phase, which is inferencing, is that it deals with a very large number of problems. Once again, I mean, if it is in the case of a smart city, there could be thousands of cameras that are running simultaneously, feed coming from thousands of cameras, and one needs to make sense of the data that is collected by thousands of cameras together simultaneously. So the characteristic of inferencing is that it needs to deal with very large number of problems. Now, the AI computing techniques used, when I say computing, I'm using it as an umbrella term. It involves the traditional processing, the high performance storage, high performance networking, etc. And AI computing is needed. It's a totally different ball game when it comes to training and what is needed for inferencing. So let's go a bit deeper into it and discuss what is that goes into each of these work streams for an enterprise to adopt AI at its best. Right. So this slide, whatever we are seeing here, this is the software abstraction layer of the NVIDIA data center platform. What I'm going to do is I'm going to start from the bottom of the stack, right? The first two layers at the bottom of the stack, they represent the GPU. Now, GPU, as we all know, is graphics processing unit, and a very important difference between a GPU and a CPU is that a GPU is a parallel computing engine. In the sense, it takes a very large problem, breaks it down into a large number of small threads, right? It breaks it down into a large number of small threads, and each of those small threads is run in parallel, right? And this is what we call as parallelization or accelerator computing. I mean, a typical example that I always cite is like if I need to travel from city A to city B, and city A and city B are connected by a 6-lane highway. A given set of cars takes, let us say, it takes 10 hours. Now, instead of a 6-lane highway, imagine if I construct a 10,000 lane highway, right? I replace a 6-lane highway with a 10,000 lane highway. That is what we call as parallel computing or accelerator computing. So the same city A and city B, the same number of cars, X number, let's say 100,000 cars. Instead of taking 10 hours, we'll cross from one point to another point in let's say 10 minutes. That is what we call by accelerator computing, where we increase the throughput of computation by increasing by parallelizing the job that needs to be computed. And that is what GPUs do. That is the bottommost two layers that you are seeing. On top of that lies the acceleration libraries. These acceleration libraries are all based on a parallel computing software framework that is called as CUDA, CUDA, Compute Unified Device Architecture. And all the parallelization is done based on this framework called as CUDA. The computation happens on top of this framework, parallelization framework called CUDA. And we call it as CUDA X, and the X could be several buckets. The X could be machine learning and data analytics, or it could be AI training or AI inferencing. It could be high performance computing. It could be rendering and visualization. X could represent any of these type of computational needs. Data analytics and machine learning, AI training and inferencing, high performance computing, rendering and visualization. And there are developer toolkits that are built on top of CUDA or CUDA X, if X represents the other all the buckets, that make the parallelization run in its most efficient way, specific for the buckets that we talked about. Could be data analytics or high performance computing, etc. Now, the one on top of that, what is labeled as application frameworks, that is the most interesting one, where there are specific application frameworks for specific workflows or specific needs. For example, if it's a smart city problem, predominantly we'll be talking about video analytics, high performance video analytics, streaming video analytics from tens of cameras if it is a process plant, or hundreds of cameras if it is a very large process plant, or thousands of cameras if it is a case of a smart city. Right. So Metropolis is a framework that does this. And there are several of them. Conversational AI, it's called Riva, autonomous vehicle called Drive, and things like that. So I'm not here to read through the names, but the idea here is that the message here is that there are specific, very vertical, very contextualized frameworks, application frameworks that are available for each of the use cases that one can think about. And these are very tailor-made with multiple features embedded in them that make it suitable for that particular function. It could be conversational AI, or it could be driving autonomous vehicles, or it could be recommendation systems, etc., etc. This is what we call it as the NVIDIA data center platform. The topmost layer, which is business applications, that is what is developed by our clients, and the clients could be our partners who render IT services for other companies, or it could be the end users themselves, the enterprise companies which invest heavily in AI and which have their own developer team creating business applications. And these business applications, there are like it's countless, from customer engagement to patient diagnostics to quality assurance to precision marketing. There are so many of them that are necessary, that are available, that are built on top of this. On both sides of the stack, you will see two pillars, and these pillars represent the overall managing the operations part of it, like we call it as machine learning operations, ML operations, where you resource allocate, you do orchestration of layers, and then you ensure that the right resources allocated to the right person, you measure utilization and things like that. That is what is represented by the operations and monitoring part of it. Now, this entire stack is what forms a modern AI data center platform, right? This represents AI data center platform, where there is a specialized hardware which can take care of parallelization needs. And on top of that, there are acceleration libraries, developer toolkits, and very importantly, very verticalized and contextualized application frameworks on top of which business applications are built and run. This is what is a modern AI data center platform. Now, so how does this transformation happen with AI? Once again, like I explained, there are specific application frameworks that are available. And these frameworks are for specific industries, right? Once again, I'm not going to read through the names. The slide is in front of you. I'm sure you can read through it. But then, for example, if I talk about speech AI, I'm talking about a platform called Reba. Like that, for recommended systems, there is something called Merlin. For healthcare, there is something called Clara, etc., etc. So once again, I want to drive home the message that it's a great practice to ensure that we understand what type of application frameworks are available for my specific domain, because somebody has done the work and there are pre-trained models and model scripts that are available that cater to the needs of those specific domains, that talk the language of those specific domains, and might as well make use of them and ensure that we build an AI practice quickly and, very importantly, much more efficiently. Now, each one of these topics, be it Riva or Nemo or Merlin or Metropolis, etc., so on and so forth, each one of them deserves a minimum of 45 minutes of talk, which obviously we don't have today. But I included this slide just to ensure that we all are aware that such verticalized domain-specific application frameworks are available, which will make the life easier because they talk the language of those specific domains. You need any further information? Yeah, I mean, a lot of information is available in our website, and of course, you can reach out to any of the NVIDIA people who you already would be in touch with. I'm going to pick up a couple of them, a few of them to drive home the point. Once again, like I said earlier, I don't have time for covering every one of them, but there are some generic, very commonly used frameworks that are available, which I'll touch upon. The first one is what we call it STAR, which is train, adapt, and optimize. This is essentially a transfer learning toolkit. So basically what we do is we provide, as I mentioned earlier, pre-trained models and sometimes public data sets that are available in the internet, and model scripts, etc., from our software repository. The software repository is called NGC. Now, which obviously cannot be used as it is, because that model needs to be retrained using your data or your client's data. Then only it becomes suitable for that particular need. And that is what is done by TAR. It trains, adapts, and optimizes in a cycle. Train, adapt, and optimize in a circle. Yeah. That tau toolkit basically helps you to apply transfer learning techniques onto pre-trained models in a much easier way than what you would do if you were to do it from the scratch, and which caters to almost all the industries that we talk about. The second very important one, which I feel I see a lot of application and adoption, is what we call as deep stream SDK. Once again, like I mentioned earlier, this is specifically for streaming video analytics, where there is a large number of cameras which capture high fidelity images, high fidelity videos, and stream them. And somebody needs to look at them and make some decisions, or a machine needs to look at it and do the right decisions. That is what is enabled through deep stream SDK. The next very interesting one that I'd like to talk about is what we call as NVIDIA Rebound, which is an accelerated SDK for real-time speech AI. Real-time speech AI. When I say speech AI, I am not talking about synthetic questions like what is the temperature outside? The answer is 25 degrees. What's the temperature outside? 25 degrees Celsius. How far is the airport? Airport is 30 kilometers away. No, that is not what I mean by conversational AI. When I say conversational AI, what I mean is very contextualized, human-like speech, which follows the syntax and semantics of human language, human expression. Like what I'm talking to you now, or let us say if we meet outside in a cinema, how we would talk in a friendly way, in a very casual way. If I am able to talk like that, and there is a response from the other side, from an entity, and I'm not even able to, distinguish whether the entity which responds to me is a machine or a human being, that is what I mean by conversational AI. It is a very complex thing to achieve, but then we are there. We certainly are there. And this needs very big models, huge NLP models and speech recognition models to be trained and deployed, and we play a big role in this area, right? So, having talked about a few tools which are used for training, now going to the inferencing part of it. Like tau is used for training, transfer learning in particular. Then we have tools like TensorRT, Triton, etc. TensorRT basically what it does is it takes very heavy pre-trained models and applies multiple optimization techniques to make it lighter weight model for deployment or inferencing. And then we have tools like Triton, which basically help you to deploy large number of use cases as microservices. This is what we call as deploying AI at scale. I repeat, deploying AI at scale. What does it mean? See, when you want to set up a POC, or when you bring something in your lab or as an experimental setup, everything will run fine. But it's a totally different ballgame if you need to deploy AI at scale. If you really need to deploy it in a smart city and need to handle hundreds of cameras or sometimes multiple hundreds of cameras, then that's a totally different ballgame. And that is where tools like Triton come into play, which help you to scale multi-framework inferencing server for high performance and utilization. Okay. And so these are tools that are available specifically for inferencing. The last tool that I go a little bit deeper into is what we call Rapids. Now, Rapids, what it does is it accelerates the entire data sciences pipeline. Okay, starting from data collection to running it on frameworks like Spark or Hadoop, etc., and then defining data frames, running your machine learning or deep learning models, building your graphs, visualization, high-end visualization. The entire data sciences pipeline is accelerated on what we call as Rapids. And this might be a slide which might be familiar to many of you. What you're seeing on the left is the traditional approach. You might be using pandas for defining your data frames, scikit-learn for machine learning, etc., etc. The corresponding tools which are GPU accelerated is what is shown on the right side, right? Instead of pandas, you run BootF. Instead of scikit-learn, you run OML, and so on and so forth. Now, the most beautiful part of this story is that Your existing pandas code can run as it is. Your scikit-learn code can run as it is. You don't have to rewrite. All you have to do is edit the first 2 lines and replay. Instead of importing pandas library, you import QDF library. Instead of importing scikit-learn library, you import Pmem library, and so on and so forth. So with minimal editing, your existing codes can run as it is in a much faster accelerated platform like what we talked about. And this is very specific for scale out analytics and all the modern computing devices, networking devices, high-speed networking devices, and very importantly, high-performance storage devices. They all support this particular type of one. So basically what it means is that couple of things. Number one, obviously it runs much, much faster, lightning fast. We're talking about 70x, 20x performance as well. Please note that I'm not talking about 70% improvement in performance. I'm talking about 20% increase in performance. I'm talking about 70x performance, 20x performance, or 20x cost reduction. That is what I'm talking. And what used to take tens of CPU nodes or sometimes hundreds of dual CPU nodes can now be replaced by a few GPU nodes. And hence the total cost of ownership, as you can see on the rightmost side of the slide, has come down drastically thanks to all the techniques and the technologies that we have been talking about so far. Now, so basically what it essentially means is that you can maximize productivity, very top model accuracy, improving the accuracies at the lowest TCO. That is what we are talking about. With that, I would like to shift gears a little bit, and over the next, I would say about 7 to 8 minutes, I'm going to talk about a very exciting technology. The whole world is very excited about it, what we call as metaverse or virtual world. And I mean, the excitement around that is very similar to the excitement that was on deep learning, machine learning, let's say about 5 to 6 years ago. So what exactly is this? And what is that we do from NVIDIA perspective? What is that we do for this? So NVIDIA Omniverse is our platform for developing virtual worlds. And virtual worlds are becoming essential for every industry, right? It is in early stages, don't get me wrong. It is in early stages, it's in very nascent stages, but almost every industry, like architecture, engineering, construction, of course, media and entertainment, and product design and manufacturing, scientific visualization, robotics, autonomous vehicles, etc. They are fast adopting the concept of digital twins, where you build digital replicas of the entities, the physical entities, and visualize them, interact with them, and simulate them, and do a lot of things that actually happens in the physical world. And hence, by observing them, by training them, you make building the physical worlds much faster and much more efficient. And that is where the concept of digital twin comes into play. And virtual worlds are becoming necessary for every industry. And as I mentioned, NVIDIA Omniverse is our tool. It is our development platform for developing virtual worlds, creating and connecting virtual worlds. There are two fundamental aspects involved in this. The first one is collaboration. Data could be coming from multiple 3D content creation software, but how do you collaborate real time in its native format? That is what is done by the central sphere, which is called nucleus, which helps you to collaborate inputs from multiple sources in multiple formats and apply several rendering, high performance rendering and visualization techniques on top of that. So that you create virtual worlds that look very much like the physical world. And this input can come from any of the devices that you are seeing, or any of the software that you are seeing on the left side of the slide. I'm sure these are very familiar names for all of us. And the enterprise nucleus is where they're able to interact and collaborate and give you an output which can be visualized and experienced in multiple computing devices like workstations, virtual reality devices, and things like that. Now, this involves a lot of tools and techniques, and a few of them are listed here. nucleus, as I mentioned, helps you to store. It's a sort of a database for files from multiple sources. Connect helps you to create those connectors which talk either unidirectional, bidirectional. A kit for development of platforms and simulation and rendering platforms. So these tools and technologies work in unison to bring out a virtual world that not only looks real, it also behaves real, right? Let me repeat it. It not only looks real, it also behaves real. And that is what we call as digital twin. And what you're seeing on the screen is what we call as a factory digital twin, where two very advanced techniques come into play. The first one is advanced rendering and visualization for creating worlds that look real and behave real. The second one is the operationalization of the digital twin, which involves a lot of training and machine learning and deep learning, and hence you predict the behavior of the digital twin and operate it accordingly. So, in summary, the Omniverse is a very powerful platform that combines two very important technologies. The first one being advanced rendering and visualization, and the second one being AI and deep learning. An amalgamation of these two, advanced rendering and visualization, and AI, specifically deep learning, is what forms the platform called Omniverse, which is our development platform. Now, so how do I use this in an enterprise? That is done through a suite which is called as NVIDIA AI Enterprise. Now we are talking about actual deployment of this in an enterprise. And the good thing about this is that it uses the traditional virtualization layers like the ones from VMware, Red Hat, etc., where these virtualization suites are now GPU aware, can now be virtualized for running your computation. And hence, NVIDIA Enterprise is a software suite that helps you to optimize performance and provide the virtualized layer, which everybody is familiar about, to run for AI, machine learning, and deep learning workflows. Right? That is what is what we call as NVIDIA AI Enterprise Software Suite. And whatever we have been discussing so far can be done on top of the software suite. To ensure an easy and very importantly an efficient deployment. Once again, this is sort of summarizes what we have been talking so far. The entire data sciences pipeline, namely data preparation and the training at scale, and then optimizing it for inferencing. We talked a lot about it, and then deploying at scale. So data prep, train at scale, optimizing for inferencing, and deploy at scale. This entire pipeline, AI pipeline, is now accelerated by all the tools that we talked about on GPUs. So, what does all this mean at the end of the day, right? I mean, that's important. The last message is that because of all these modern AI computing techniques, whatever we have seen so far in terms of the elegant software suite that is needed to run this, basically the cost of computation has gone down drastically, right? The cost of computation has gone down drastically. What you are seeing on the left side is CPU-only infrastructure. Let's say 220 self-hosted Cascade Lake servers are there. They can be replaced by just 4 accelerated servers for running AI problems. Right? I repeat, 220 servers get replaced by 4 GPU accelerated servers, which obviously brings down your initial investment drastically, which occupies much lesser space, 1/10 of the space, and obviously consumes much lower power. So essentially, once again, let me repeat it, thanks to all these techniques that we have been talking about, the cost of computation has come down drastically. The total cost of ownership has come down drastically. And that is what is the biggest achievement of all the AI computing techniques that we have been talking so far. Right. That marks the end of my talk. And I'm very happy to take any questions that you may have.
Thanks a lot, Sundar. Thanks a lot for the insightful thought. So, you triggered in the fantasy world of metaverse in your talk. So, we have been hearing of our Indian monuments on sale on metaverse. So connecting back to Omniverse, what NVIDIA has. So could you please help us understand what type of storage need does applications or tools like Metaverse expects from the storage packet?
Excellent. Great question. Thanks so much. So Omniverse as such, Omniverse, as I mentioned earlier, is a development platform. It's a set of SDKs and libraries that help you to do two things. Number one, advanced brain visualization, and number two, applying deep learning to predict the model of entities and hence create digital twins. They themselves need enormous amounts of data. So the answer to your question is, it is decided depending on which data, what type of data we're talking about, how much fidelity of data that we're talking about and things like that. And so wherever deep learning is needed, it's very important to have extremely high performance storage. And as we all know, when I say high performance storage, it is obviously just not the petabytes and the zettabytes of it. It is the ability to run it in a parallel mode, the ability to supply data at the right time through a high performance networking and things like that. So in a nutshell, a high performance storage system connected to the networking, connected through a high performance networking to the computing devices is a necessity for running such problems.
Okay. And adding on to the same question from Jayanto, how much data should be persistent, or is it mostly transient, is what we're looking at with Omniverse or Metaverse applications?
Right. So it depends. Once again, it depends on the model of deployment, right? For example, if I'm looking for almost real time, I'm very hesitant to use the term real time because nothing is real time. It's always almost real time, right? So if it is almost real time, then you need to have data that needs to be read immediately. Within few milliseconds, few microseconds. That is what we need about. But then not all inferencing needs to happen online, right? For example, if using modern IoT techniques, if you're collecting temperature and sensor data from an aircraft turbine engine and creating a digital twin, and you are going to predict when the maintenance has to be done, instead of doing scheduled maintenance once in 3 months, 6 months, etc., if you're able to do a predictive maintenance, then you can afford to collect data, send it back to the data center, analyze the data, and then take an informed decision. Things like that do not need real-time inferencing. But if you're inside a self-driven car, there's no way the signal can go to a data center, get inferred, and come back to the car. It needs to happen in situ. That is what we call as edge-based computing.
Edge storage, yes.
So it depends on the type of inferencing or type of deployment that we are talking.
Great. Thanks a lot, Sundar. Thanks a lot for the very informative, astonishing talk. I think I was more impressed by the Omniverse, reminded me of Metaverse again. I don't see any more questions from anybody yet, so I think that should be it. So back to you, Reena.
Thank you, Santosh. Thank you so much. And thank you, Sundar Ramalingam, for taking us through such a wonderful session. And I want all of you to type claps or applause on the chat box, thanking Mr. Sundar for taking time out and joining us here. We had a great session. And on that note, the time has come for us to move to the next session. I see the claps coming in. That's wonderful. Thank you. Thank you, each of you who've typing claps on the chat box there. We're about to move to our next session. Thank you, sir.
Thanks, everyone. Bye-bye.
Thank you so much. On that note, it's time for us to move to our next session, and our next session is on co-designing distributed storage with programmable network hardware. And the speaker who's joining us here today is Professor Jialin Lee, who's the Assistant Professor, School of Computing, National University of Singapore, who would join us shortly. Jialin, are you here with us?
Hello.
Hi.
Hey.
The virtual stage is all yours.
Hello. Hey, can you hear me?
Yes, you are audible.
All right, awesome. Hey, how is everyone doing?
Fantastic. Go for it, sir.
All right, okay. So I guess I should share my screen.
Yes, you will be made the presenter and you can share your screen right away.
Can you see my screen now? Right, so I think that's a yes.
Yes, we are good.
Yes, we can.
Right, awesome, awesome. Okay, so I guess it's 2 minutes early. Should I start now or should I wait until 5:30?
We can get started, Jeremy.
All right, cool. All right. All right, so good afternoon, everybody. So for those of you who are here in Asia, so here today I'm very excited to talk about some of our recent research in co-designing distributed storage with programmable network hardware. Okay, so just a quick introduction. So my name is Jialin Li. I'm an assistant professor at the National University of Singapore in the School of Computing. All right, so with that, let's start the talk. So building distributed systems is a really challenging task, right? So we have a bunch of these challenges when we're building a large-scale distributed system. So for example, the problem is that the distributed system, one of the things it tries to provide is to remain availability, right? So even despite the large number of failures happening in the system. So another challenge is in a distributed system, data is replicated, is partitioned, is sharded everywhere, right? So there are multiple copies, your data is everywhere. Right? How do we make sure that your data is strongly consistent so that the behavior, the user behavior is still expected? So at the same time, so we are trying to give all these guarantees, but also give some kind of performance guarantees to users, right? So this always comes in the form of performance SLAs, SLOs, whereas the users are especially for interactive services, right? So the user expects there are some latency and throughput of the system. So as a systems person, so how do we address these challenges, right? So what we do is we build system software to provide fault tolerance and strong consistencies to programmers so that they don't need to handle all these problems themselves. Right? These system software include fault tolerant systems. For example, you replicate your data across multiple replicas. And then on top of it, you provide a service that guarantees linearizability, meaning that the system, even though it is replicated, it behaves as if it is a single correct system. And then we also build ACID transactional systems. So like MySQL or PostgreSQL databases, where even though your database is sharded into multiple shards, and then concurrently running different transactions on each shard. So what the system is providing is an illusion of a single correct database that executes these transactions in a serial order in an atomic way. Right? So these are really great guarantees to users of the system so that they do not need to worry about the underlying problems, things like fault tolerance, failures happening, or data being distributed. Right, so these guarantees are not free, however. Right? So all these systems have a very high performance cost. So here I'm showing a canonical distributed transactional protocol. So I'm not going to like explain the details of what is happening, but basically what protocol is doing is having a two-phase commit protocol with a replication protocol on top of it. So it's running multiple of these distributed protocols to guarantee fault tolerance and atomicity and isolation of your distributed database. Right? So you can see even committing a single transaction take multiple round trips, and it's very complicated protocol, so which is limiting the overall system performance. So because of this cost in guarantee all these strong properties of the system, right? So there have been proposals to provide weaker guarantees for better performance. So for example, the NoSQL movement is an example of this, right? So they want to give up transactionality, they want to give up linearizability, they want to give up some isolation guarantees so that the system provide higher performance, right? So your system is performing better, but the problem is that now you're exposing some of these issues in distributed systems to users, right? So that translates to burdens to application programmers. Right? So many industry companies eventually realize that even though they got better performance, they are paying more because of all these hard to debug issues in distributed systems, right? So eventually decide we still need strong guarantees. So the question we are trying to answer is that, can we build distributed systems with both strong guarantees and high performance? Right. So to answer this question, we try to ask ourselves, right? So what are some of the fundamental assumptions when building distributed systems that leads to this explicit trade-off? So one of the assumptions we found that is interesting is that most existing distributed systems, when they design, they consider the network as a total black box, meaning that they only assume the network can deliver messages from point A to point B. And also there's a best effort network, right? So the network can arbitrarily drop messages, reorder messages, or duplicate messages, essentially meaning the network is completely asynchronous, right? So because of these very, very basic assumptions, or basically no guarantee assumptions about the network, so that's why they have to build this complicated application level distributed protocols to guarantee certain properties. But we observe a trend that, so this is no longer 100% true, right? Especially in data centers, right? So the assumption that the network is composing of very dumb switching devices that can only provide very basic best effort guarantees. So the trend we are observing is that data center switches are becoming more and more programmable. Right? So a very, very good example is the Intel Tofino switches. Right? So these are the new generation programmable switches that are becoming commercially available, and people are starting to deploy it in their data centers. So compared to the traditional fixed function counterparts, right? So fixed function switches. So these new generation of switches have very different set of properties. So for example, they will include programmable packet header parser, meaning that even after you purchase the switch, you can define new packet header formats, right, for your own application or for new network protocols, right? So you are no longer restricted to the traditional IP, TCP, IP, UDP, and Ethernet formats. And also, you can fully define your own packet processing pipelines. You can define how the switch process each packet, and then you can even include simple computations in your processing pipelines, right? So simple ALUs and stuff like that. And moreover, so these switches provide general purpose stateful memory, right? So that means you could store some amount of data on the switch data plane. And then so that means you can build some kind of general purpose computation plus memory, right? So when processing packets. Right? So this translates to a capability of this switch is that they can perform application specific computation. And then the important thing is that they can perform this computation at line rate. So these switches are pretty massive, so they can process packets at terabits per second. So that means while you're processing these packets at terabits per second, you can still do some application-specific computation, which is very powerful. Right. So with this new kind of network devices that is becoming available, so we are using a new approach to designing a distributed system by co-designing distributed systems with the network. Right. So our approach is that we no longer treat the network as a complete black box. So instead, we leverage these newer programmable network devices to design stronger network primitives. So these are no longer best effort guarantees, right? And then we build new distributed protocols and systems around these new network primitives. And the results are that we can able to build practical distributed systems with both strong guarantees and high performance. Right. So today in today's talk, I'm going to give you a few instances of this new approach based on how much time I have. So the first concrete instance of this new approach is to co-design distributed storage systems with the programmable network devices. Right, just to motivate. So many real-world workloads are highly skewed and dynamic. So when I say the workload is skewed, so you can, for example, right? So in the Twitter, right? So social media, right? So there are some of these social media objects, like tweets from a celebrity, that has much higher access rate than, for example, many of the other objects like tweets from myself, right? So usually these objects follow a high tail access pattern, right? So sometimes it's called the power law, right? So, and then when I say dynamic, so dynamic means that some of these objects, right, so their popularity changes over time, right? It's highly dynamic. Some of these tweets can suddenly become very popular, but after a short period of time, then they stop being popular and it's totally unpredictable. So that's about the workload. From the storage perspective, right? So we have massive data stored today, right? So it's impossible for us to store the entire data set on a single machine. Right? So what do we do? So we partition the data set, the data, onto multiple machines. We call shards. Right? It's called data partitioning or called sharding. Right? This is essentially to scale the system. When you combine these two, suddenly there is a pretty hard problem for distributed storage, right? So that is load imbalance. So because we are partitioning data, so the shard that is storing a popular object, right? So it will receive significantly more requests than, for example, the other shard storing non-popular objects. Right? And then, so this will lead to these servers holding popular objects being overloaded, right? So, and then when the server is overloaded, it has all the problems, and so it will, the request going there will suffer higher latency, and sometimes the request will be dropped, right? So this is certainly not desirable. And because the workload is dynamic, you cannot predict which objects will become popular at what time, right? So it's hard for you to provision statically how to partition these objects based on popularity. Right. So the other challenge is that these skilled workloads are also very diverse. There's not just one type of skilled workloads. Right. So based on recent studies from like industry companies, right? So these real world workloads, they can be read heavy, they can be write heavy, they can be read write mixed, right? So there's no certain pattern of these workloads. And also the storage system itself, they can store small objects, large objects, or combination of both. Right? So what it means that a single solution that targets a particular workload or a particular object kind of distribution will not work across different deployments, right? So we need a common solution that address the load imbalance problem across all different kind of these workloads. Right, so there are two common approaches to deal with the highly skilled workloads in distributed storage. Right, so the first approach is caching. So the idea is very simple, right? So you have a caching layer that is faster, significantly faster than the storage layer. And what you do is you cache these popular objects in the caching layer. Right? So because of these caching layers are much faster, right? So they will be able to absorb the traffic going requesting these popular objects. Right? So the effect is that effectively it will reduce the load on the backend storage servers, especially for those servers that holding popular objects. Right? So make the load across servers more uniform. So caching is a great solution, but it does have several limitations. So the first, which is the biggest limitation, is that the caching approach is only effective for read-heavy workloads. Right? Because for updates to the objects, you do have to invalidate the cache and update the backend storage. Right? So, and I just mentioned, so there are many other workloads that are not read-heavy. So this solution will only work for a certain type of deployments. And then the second requirement for having an effective load balancer solution with caching is that the caching layer needs to be orders of magnitude faster than the storage layer. So this is easily achievable in the past, where you have in-memory caching and very slow spinning disk storage servers. But these days, the storage services are also catching up. You have better software, you have better hardware, especially with high-speed SSDs or non-volatile memory, right? So the speed of storage layer is getting faster. So it's harder and harder for you to build a caching layer that is orders of magnitude faster. So I promise there are two approaches. So this is the second approach to deal with load imbalance, is what we call selective replication. So in a selective replication scheme, so instead you replicate these popular objects onto multiple servers. Right? So the benefit of this approach is that then requests to these replicated objects can be forwarded to any of the replica. So if you do this forwarding properly, then now you can effectively distribute the load across multiple servers, so that the load will not, so the request will not overload a single particular server. Right? So this sounds pretty promising, right? So it's a good approach to load imbalance and doesn't suffer the problem from things like read-heavy workload, right? So even for write, maybe you can distribute the write to multiple servers, and then it doesn't require a much faster caching. Right, but the problem is that building a selective replication scheme is very challenging. Right, so why is that? So let's say one of these objects, object A, is really popular. Right, so what we want to do is to replicate this object. So obviously you do not want to replicate every single object, because that requires a lot of extra storage. Right? It's certainly not feasible. Also, you do not want to replicate these objects onto all the servers, right? So that will also increase your storage overhead, right? So you want to selectively replicate these objects onto a selective set of servers to minimize the storage overhead, right? But with this setup, then how do you route these requests to the right server? Right? Because a request may go to a non-replicated object or to a replicated object. How do you know which one is replicated? And for this replicated object, where do they live? Right? So how do you route this request? And then at the same time, once you have these multiple copies, a natural problem is that how do you ensure the consistency across these multiple copies, especially when you're doing update and reading these objects at the same time. So this is what we're thinking, right? So what if the network itself can track which objects are replicated and where are the copies? And then that will solve all the problem, right? But obviously currently there's no network that can do this for us. Right? So that's how we design our new distributed storage system called Pegasus, right? So in Pegasus, we take this approach of combining selective replication and an in-network coherence directory, right? Which I'll explain next. So coherence directory is this data structure that is used by CPU computer architecture to ensure coherence between caches on multi-core CPUs. Okay, so we borrowed that idea and applied that to distributed storage. So what this data structure does in our system is that there is a centralized directory that tracks which objects are replicated and the location of each replica. Right, so with this centralized directory, then the directory will take all the requests and then forward the request to the right server. Right? So it knows which objects are replicated and knows where these replicas are. So it can pick one of the replicas, and it can also do it with the load aware manner, right? So it can pick the replica with some spare capacity, try to make sure that the load is balanced. Right? And then this coherence direction will also ensure strong consistency. Okay, so let me just quickly illustrate what a coherence directory looks like and how it works. Right, so here I'm showing an example with 3 storage servers, S0, S1, and S2. And then we are showing 3 objects that are currently being replicated. Right, so we have object A, B, and D being replicated. Right? A not yet, but A will be replicated later. Right? So and then the left bar there shows the current load of each storage server, and currently S1 is being overloaded. So in this coherence directory, we will keep track of the objects that are currently being replicated. So these are the popular objects that receive more requests than the remaining objects. Right? So for the other non-replicated objects, we don't really care. Right? So we don't store them. So the reason being that the directory has very limited memory space, especially for these switches, so that we can only keep track of a limited number of objects. So, and then for each replicated object, the directory also tracks the set of replica servers. Right? Now, when there is a request for any of these objects coming, so we will first forward them to the directory. Right? So this request is for reading the object B. Right? So what the directory does is first do a match on the object ID, and see that this object has a match in the table, which is the middle row. And then it sees that there are 3 different replicas, right, for this object. Then the directory can freely pick one of the replicas to forward the request to. So in this case, it may decide to forward to S0 because that has a lower load. A more interesting question comes when there is a write request, right? So here we have writing to object, updating object A. So in this case, you may assume that the only thing it can do is forward this write request to S1 because that's where A is currently being replicated. So, but the interesting fact about Pegasus is that we are able to redirect this write request to a different server than where it's originally being replicated. Right? Because it sees that S1 is being overloaded. So what we can do is we redirect this write to another server that is currently doesn't have too much load. Right? Now then you are creating a new copy of this object on a different server. And then we can do that to the next write request to A as well. So we may pick another server to process the write. So now we have newer versions of the object on different servers. Right now, here's the problem, right? So the problem is how do you able to read these later versions, because the coherence directory still keep track of the older version, right? S1 still have the older version. Right? So what we do is that when the write finishes, when the replies comes back to the client, we also ask the reply to go to the coherence directory. So, and then we are able to update the directory to reflect where are the latest copy of these objects. And then in this case, when subsequent read requests come to the system, we will be able to direct them to the servers with the right copy. Right. So based on my description, seems like the coherence directory needs to be in the middle of every single request, right? So all the requests need to go through the directory, all the replies need to go through it as well. Right? So certainly, if you have a large-scale system, having this single point may become the bottleneck. Right? So that's why we are targeting a rack-scale storage system, and then we are implementing the coherence directory in the top of rack switch. So the rationale behind this is that in a rack-scale system, all the network packets needs to go through the top of rack switch anyway to reach any of these servers. So it is already going through that switch, right? So by implementing this coherence directory in that switch, we are not adding any additional latency overhead. And then because these switches are provisioned in a way that they have enough capacity to process all network packets, all network bandwidth for the entire rack, right? So this Tor switch is not a throughput bottleneck of the system as well. So that what makes this programmable switch pretty amazing is that as long as you'll be able to have your program compiled and run in them, so they will be able to provide line rate processing for the entire bandwidth going into and out of the switch. So I gave a fairly informal description of how this coherence directory can guarantee consistency, right? So what we do is the switch processes all requests and replies, and then it tracks the servers with the latest copy of this replicated objects, and then we update the directory when receiving replies from the storage servers. However, there are many other corner cases, especially when you have concurrent updates and read requests to these objects, right? So to actually guarantee linearizability, which is the strongest guarantee of a storage, a distributed storage system, so we developed a new version-based coherence protocol. Right, so here I gave you a very quick example of how it works. Right, so on top of just the objects and their locations, so we also keep track of two things on the coherence directory. So the first thing is a single global version number. So this is the next version number for any objects. And then for each object, we also keep track of the completed version number. Essentially, what is the most recent version of that object being completed, written to the storage system. Right. So now imagine we are having a write request for particular objects come to the system. Right. So we're updating object A with value B. Right. So remember, we first route it to the directory. So in this case, what directory does is that it puts the next version number stored in the coherence directory into the packet. Right, so now the packet now will say that the version of this object becomes 4. Right. At the same time, the directory will be updated. So we'll update the next version number, incremented. Right now, we forward this write request to the servers, and then actually we can actually broadcast it to multiple servers. The reason we are doing broadcast is that once we finish the broadcast, then we'll have multiple servers having these objects, so that later we can. This is better for read balancing, because read later can read any of these objects, any of these replicas. Right? Supposedly now we finish processing this write on these servers. Right? So when replying back to the coherence directory, so the reply will also contain the version number of that object recently being updated. Right? Now assume one of the replies reaches the directory first. Right? So what we do is we compare the version number in the reply, in this case 4, to the object's currently completed version number. In this case, this is 3. So we see that this is a higher version number, so it's a new version of the object. So what we do is we update the completed version number to the next one, and then also we update the replica location, right? Because now we need to know that S2 has the latest version of the object. Right? So now let's assume asynchrony in the network, right? So S0's reply is still pending, it's being very slow. And now we have a new request, write request for that object. It's updating to value C. Right, so we go to the directory, we go through the same process. We write the next version number into the packet, it's 5, and then we update the next version number. So this time we forward it to S2 only. Right, so we update the object again, so A now equals to C. And so when reply, so we attach the version number 5. Right, so when that reply reaches the directory, right, so we do the same check. It is higher than 4, so that this is a higher version number. So we update the completed version number for object A. Well, this time we also need to update the replica, but it's still the same, right? So still S2 holds the latest version. Right now, the interesting part comes, right? So now the reply for S0 finally completes, and then it goes back to the directory, right? So if we do not have this version number protocol, right? So if we just simply update the directory to have S0 for object A, then that is no longer consistent, right? Because we are reverting back to an older version of the object. So the next read will read the older version, which violates linearizability, right? But with this version number scheme, we're able to compare these version numbers and see that the 4 is smaller than 5. So we do not actually update the directory, right? And directly reply that to the client, right? So that's how we use this version-based protocol to guarantee linearizability in the system, right? So there are many other details of the protocol, but due to time constraint, I'm not going to cover those. But if you're interested, please refer to our paper. All right, so I talk about this our Pegasus design. So what kind of benefits do we get from this in-network coherence directory? Okay, so we compare our system to two other systems. Right? So consistent hashing is the popular approach adopted by many systems to do load balancing. And then we also compare to a more recent work called netcache, which uses programmable switches to cache objects in the switch. Right? And then we compare that to Pegasus. And here we show 4 different kinds of workloads. So there is a uniform workload. And then we have the Zipf distributed workload, right? So the higher coefficient means it is more skewed towards some popular objects. And then we measure the maximum throughput achieved by this system given certain SLO. Right? So we can see that when you have a highly skewed workload, right? So the throughput of a consistent hashing system drops significantly. So the reason being that when there's a highly skewed workload, then one of the server becomes overloaded, right? And able to provide still guarantee latency SLO, so what we need to do is to over provision, or in this case, provide lower throughput, right? Otherwise, it will violate the latency SLO. With Pegasus, we're able to selectively replicate those popular objects when the workload is skewed, and evenly distribute the request to all these different servers. Right? So we observe a 10 times throughput improvement when there is a highly skewed, the access pattern is highly skewed. And then we also compare to netcache. So here in this case, because this is a read-only workload, right? So netcache is able to provide a very good performance because it's able to cache those popular objects into the switch and to provide additional throughput. Right? But here, so then we do a different experiment where we no longer do only read-only workloads, right? So because I talk about the workloads can be very diverse. So now we try to run a highly skewed workload, but with different read-write ratios. From 0 write ratio, meaning that is read-only, to 1, that is write-only workload, right? And then we do the same experiment. So here, consistent hashing is still pretty bad, so it doesn't affect consistent hashing. But with netcache, you can see quickly with additional writes in the system, the throughput drops significantly because, as I said, if there is a write, caching doesn't really help. Right? So effectively, the throughput dropped by more than 80% when there's only 10 or to 20% of writes. However, in Pegasus, we're able to maintain our high throughput even when there is a very high write percentage in the workload. The reason is that, as I described in the selective replication scheme, we're able to redistribute writes to different servers as well because we're able to track these replicas in the coherence directory. Right? So it doesn't suffer the problem faced by a caching approach. So that's the work we did by co-designing distributed storage with programmable network switches. Right, so well, I don't have too much time, so I have about 7 minutes. So I will quickly talk about another work that we use similar approach, but this time we applied it to state machine replication. So which is another important technique for storage systems.
Oh, so sorry to interrupt, Jalen. So we have a whole bunch of questions. Do you want to take the questions or do you want to go with the next presentation? It's your choice.
Okay, so if we have a lot of questions, maybe then I will just skip this part and then answer questions. Maybe that's more more interesting. So let me just skip this part. So since I already covered one work, and let me just jump to the conclusion slide and then take questions. Do you still see my screen?
Yes, we can.
Okay, all right. Right, so, well, unfortunately, so I don't, okay, so not this slide. All right, so unfortunately, I don't have time to cover my other work, but today I quickly discuss this co-designing distributed systems approach with the network. So on a high level, so we found that the interesting part of this kind of approach is to identify the right abstractions to be implemented in the network, and then co-design protocols to take advantages of these network primitives to provide strong guarantees. Right, so the result is that we're able to design distributed systems with both strong guarantees and high performance. Right, so I spent most of my time discussing this distributed storage system, but there are other systems that we use the same approach. And with that, I'm happy to take questions.
Thanks a lot. It's a really interesting topic. I think, with the quantum of questions we get, it looks like too much of involvement into this particular task that you have done. So let's proceed further. So the first thing is, what is the memory capacity of these switches we are looking at?
Yeah, this is a fantastic question. So I didn't mention specifically, but one of the limitations of these switches is that they don't have a lot of memory. Usually you are looking at memory capacity from 10 to 100 megabytes, about that, right? So that's not a whole lot, right? So when you design these applications in these switches, you have to be very careful what you store in them because of the memory capacity.
Okay, so then the coherent directory structure, is that we store in one of the servers, or where is the coherent directory structure rendered from?
I see, right. So the coherence directory is implemented completely in the switch, right? So all the coherence data, directory data are stored in the programmable switch. And okay, I think these are related questions because you may ask that you have limited memory, right? So that's why we can only store a few of these objects information in them. So first of all, we do not store object values. Second, we use hashes of the key to, so we don't store the full key, right, to reduce memory usage. And then we only store a limited number of objects in the directory.
So by hash, you mean maybe Bloom filter or Cuckoo filter. So do we use any of those to hash them up?
So currently we don't use Cuckoo hashing or Bloom filter to further reduce memory usage, right? So when I say hashing, I just say I do not. For example, you have a very, very long storage key, but we don't store the entire key in the directory. We just take a hash, a fixed width hash of the key, and store that in the directory.
Okay, and how about the directory structures we are looking at per million objects, or the directory coherence directory structure? What is the size we are looking at? For an example, say a million object.
Okay, so that is also a very, very good question. So there is a very interesting theoretical work that shows to provide guaranteed load balancing, right? So you do not need to store these coherence directories for every single, right? So to provide good load balancing, you only need to store n-log n objects into the storage directory. And this n is not the number of objects. This n is the number of servers in your system. Right? So you only need to store the most popular n-log n objects, popular objects in the directory to ensure good load balancing. And because we are targeting a rack scale system, right? So that n is fairly small. And then by empirical our study, right, we only stored about 100 objects in the directory to provide load balancing for millions of objects in the storage system.
Okay, okay. And initially, the first few slides, you spoke about the packet header farser. Like we can have our own packet headers. I can think of encryption or security as one of the vital usage of it. Is there anything else other than this, or what is the core purpose of this?
You mean the purpose of having programmable packet parser in these switches? Right. Okay. So initially, when people design this switch, so they want to. So one of the problem with existing switches is that, for example, you have some new kind of TCP protocol, new kind of network protocol. Right? So, but this requires a different format of packet header. Right? But for an existing switch to adopt to that new packet header format, when you want to experiment with new network protocols, it takes years to design a new ASIC to parse those new header. Right? But here, when you have a new this programmable switch, then you can immediately write a new parser and then load it to the switch, and then it can immediately understand the new headers. Right? And of course, we as researchers extend on the original intention of that to actually design our completely new application level header. And then they can also still able to process that. So it enables a big wide range of applications. So this is being one, you can do any kind of application kind of processing in the switch now.
Great, thank you. I'll just go with one last question, and rest of them I'll put it across on the chat. So I think that way I don't have to get Rina angry on me. So the last question, what I have is it under plan to have a shard or data migration based on the latency what the switch is encountering, or is it already there, or is it in the plan, or is it in the thought of anywhere?
So may I understand the question? So what does it mean by data migration?
The migrating data from one server or one shard to the other shard based on the data latency itself. As you said, the hot servers will have a very, very high latency. So
okay.
Is there? Yeah.
Yeah. Okay. I got it. Right. So yeah, that's certainly possible, right? So that's a policy question, right? So it's basically which objects do you migrate, when do you migrate, and where do you migrate to? Right? So currently, so that is all possible with this design. So we provide the mechanism of doing that. The actual policy you can define. So what we do in the system, right? So one simple policy is that, for example, you have a new update or new write to the object, and you found that the old server is overloaded, right? Then redirect that to a server that has spare capacity, right? But you can also do it actively. So this is more a passive way, right? So you only do that when you receive requests. You can also do it actively. So actively, you can migrate things from server to another server. But then you have to make sure that you update the directory to reflect that migration, right? So the nice thing is that because these switches is top of a rack, so all these migration requests also go through the switch, right? So it actually monitor these anyway, so we can update them without an extra protocol.
Okay. Great. Thanks a lot. So I have another 8 odd questions. I will send it across to you on the chat. Sure. We would wait for your reply, and thanks a lot for your time. It was a wonderful presentation and really something that opened up a lot of thoughts. So right, thank you for that. Back to you,
everyone.
Rina. Thanks a lot.
Bye.
Rina, we are not able to hear you. I think you're in mute.
Thank you, Santosh. Thank you so much. And thank you, Professor Jielin. It was wonderful having you amongst us. And Santosh, I'm not at all angry. I'm glad you asked those questions. And it's wonderful that you're sending in the rest of the questions to Professor Jielin lately. And on that note, I'm certain that all of you are infrastructure failure resilient and boost with persistent memory. And to do the same, we have our speaker, Yusuf Ildis, Solutions Architect Linwood, joining us here. Hi, Yusuf. Are you with us?
Yes, I'm here. Can you hear me?
Over to you, Yusuf. The virtual stage is all yours. We can hear you.
Say again, please. Hello?
Yes, yes, go ahead.
Okay, I think I can share my screen. I hope everybody can hear me well. Is everything fine on your end? Can you guys hear me?
Yes, we can.
Okay, good. Hello, everyone. My name is Yusuf Yildiz, and after more than 15 years of active field experience, I'm working as a solutions architect in Linbit. And in this presentation, I will try to explain how you can have a resilient infrastructure with Linbit, because this is the way. So before starting the technical part, I would like to briefly tell you about our company and the values that we hold on to. So don't worry, it will be pretty fast, just like the storage infrastructure we have. So Linbit is an open source storage solution provider and founded 20 years ago. And since its establishment, Linbit has adopted the motto of producing software beneficial to the community. And the word Linbit represents not only a company, but also an idea, a free thought that represents open source for everyone. And that's why we are happy to have millions of installations with thousands of users to this day. And basically, we have two softwares. The first one is DRBD, the open source distributed replicated block device, which I will explain in this presentation. And the second one is LinStore. And we have large and small support software around these two software, and I will explain them in the next slide. And yeah, let me switch into the next slide. Okay, so what is LinStore and how it works? So what are we talking about here, right, for resiliency? So in my previous presentations, I often felt that this topic was not very clear. That's why I would like to explain this to you with this visualization. So the LinStore is like a stack. And if you think of it like a car, the DRBD, the replication part, is our engine for the data and responsible for all I/O operations, including the real-time replication. And the LinStore LinStore controller manages the storage stack and split itself from the data path, and giving you like tons of advantages. And the LinStore satellites are installed on all nodes and manage the storage space and provision DRBD resources. I know that in the first hearing it might sound a little bit complicated, but actually it's not. And there is a DRBD reactor. DRBD reactor is when you need some kind of clustering mechanism for iSCSI or NFS targets and everything. And I hope this gives you a better understanding of our STS solution. So let's talk in a little bit more deep detail on technical part, right? So I want to show you a little more detail here in this box in the middle. So it doesn't matter to LinStore what your hardware is actually. It can be SSD, HDD, NVMe, Pmem, or whatever. You can choose the solution that suits your performance expectations. And LinStore can create a software RAID for you or consume these disks without any RAID layer. So let's say you have a lot of disks in here, the hardware part. The LinStore can create a RAID layer on top of them, or you can use your RAID card to have a single disk drive to use in LinStore. It's up to you. It has some advantages and disadvantages. It depends on the use case, obviously. And you might want, let's say you handled the hardware part. As you can see here, we also support Pmems, NVMEs, SSDs, HDDs, all kinds of hardware. And the Pmems are significantly increases our I saw that I didn't open my video. I'm sorry. Let me open it. Oops, I forgot that. Sorry about that. I hope you can see me now. The LinStore can leverage and use the Pmems very effectively, and that it will increase your performance up to 2 times when you put your metadata into Pmems, for example, in LinStore. So after you manage the hardware part, you have to go one level above. It's LVM or ZFS. We are using LVM or ZFS. It's up to you. You can choose any of them. We are using LVM or ZFS because you might want to expand the disks that you will create, or you might want to shrink your disks when you want to do it. And in that matter, you need something, some like volume management on top of your physical drives. So that's why we are adding this layer to have. But by the way, you don't have to use it. I mean, you can use like a plain, but it might be a good idea if you want to use it. And then let's say you created an LVM layer on top of your physical drives. Then you jump into the block storage feature side. And this is where everything becomes important. So the first part is the RBD. The RBD is the replication technology that we built since 20 years now, and it's embedded in the Linux kernel already. And you can have it by just loading this DRBD kernel into your kernel, like loading this module into your kernel. And the most updated version will be always in the GitHub page, so you can get it and compile it, or some PPAs and some repositories on the internet. And DRBD basically creates a RAID 1 array between machines. So it's not a distribution technology. It's not like erasure coding and everything. It just creates one-to-one replication within your machines. And the RBD is really performant, and there will be, and even we have the World IOPS record with the RBD replication in that matter. And then it comes another feature, which is encryption. So encryption is really important because, as we all know, the encryption is needed on most cases. So you might want to add the encryption into your drives and protect it from attacks. And the third feature is the deduplication. The LinStore also leverages the VDO, the technology currently offered by Red Hat. And that means that you can only use the VDO on Red Hat-based Linux distributions right now, but I heard that they are preparing for Linux upstreaming. And the caching mechanism you might want to add, because if you have HDDs, then maybe you might want to have some caching mechanism on top of that. Then it might be a good idea to use DMCache or Bcache for caching mechanism. So let's say you created a block device with using these features. After that, you need some kind of transportation systems to put these block devices into your orchestrators, right? You replicated your block device, so you have highly available block device with the RBD. You encrypt it with LUKS. It will consume a good amount of CPU, by the way. It comes with a cost. And then the video, obviously, it will again cost you some CPU. Not too much, but it is. And then you use cache or not use cache, I don't know. So you have a block device, let's say called the RBD 1000. Then you want to use this block device in Kubernetes for persistent storage, for example, or in OpenNebula or OpenShift, OpenStack, Nomad, Apache Cloud Stack, you name it. I'm sorry. So you need a transportation systems on between these two levels, and this is where the DRBD diskless comes into the picture. So DRBD diskless is, you can imagine something like iSCSI, but far more powerful than that. So it basically puts your DRBD block device under your computational power like it's a local device. So let's say you have you have 2 storage nodes, then 3 compute nodes, right? And these 3 compute nodes connect those 2 storage nodes, but they will see the devices as its local backing devices. So it will shown as like dev/DRBD 1000, but it's actually in another machine, in another Linux. So this is the integration part, and the LinStore handles everything in this box. So you don't have to worry about managing your physical hardware or LVM configuration or block storage features or even transportation systems. All you need to do is create the LinStore, add your features into it, whichever you want, and connect to your orchestrators. This is what LinStore, the open source storage solution that we created till now, is capable of. All right, so what is the problem? I mean, why we create this piece of storage, and why we think it's a good fit for community, right? So far, we have tried to understand what LinStore is, and now let me explain to you why we need it for LinStore for resilience in data storage, because this is our topic, right? The resilience in storage part. So let's think about it. I mean, scalability is a word that every storage vendor, storage creator is adding their feature list, but it is actually true. I mean, scaling with a cost of resources, both money and hardware, is not something we want. I mean, scalability is a term that we need to do it very efficient and clever. And there is resiliency. I mean, can your infrastructure really withstand and adapt to changing conditions and recover from the real failures? I mean, did you really think about that on all cases? Because sometimes when I talk with the members of our community, and we were talking about possible use cases and everything, and so I ask some questions like, hey, did you think about this and that? And most likely they don't, because in theoretically you always think resiliency, but you're not acting actually to fix it. And like I started this presentation, before I started this presentation, I told you that I have been in the field more than 15 years. So I know what happens if something happens when your structure storage fails and you need help. And when that day comes, our open source community is ready for helping all kinds of failures that you have. And the vendor lock-in is also another issue. You might want to fix it with open source software, right? All right, so the solution. The solution is simple, and we have integrated pretty much with everything, like OpenNebula, OpenStack, whatever you have here, right? So the integration is the key part of LinStore. And that means that whatever systems you have, the LinStore will be there to provide you a scalable, a resilient, solid product that will never fail. And it can scale up to thousands of nodes without any issue, and you can have more than thousands of nodes in one single cluster. Because in LinStore, the data and the control plane is separated. This is really important. So remember that I mentioned the RBD. The RBD is the engine of the car, while LinStore is the driver, right? So that means that you can upgrade, downgrade, put maintenance mode into your LinStore nodes, while your DRBD is taking care of the I/O. all I/O operations will continue while you're upgrading your storage infrastructure. And because you don't need to rebuild anything, because the RBD is doing one-to-one replication, that means you will have no downtime at all at any level, And the LinStore and LinBit team is really good at supporting our community and enterprise customers, and we can provide enterprise support if you need it, like 7/24. And obviously, the LinStore is hardware agnostic, so there will be no vendor lock-in for you, so you can mix and match all kinds of hardware in one single cluster. We have a lot of people in the community that does that. So the use cases, it is really important. I mean, what kind of use cases you can have with this stack, the RBD and LinStore. And you can have hyper-converged infrastructures, which is the #1 use case, if you ask me, because the RBD is doing one-to-one replication, so it shines on local reads and writes. And the hyperconverged setups will be the most prominent ones when we see the setups that we have. And then the disaggregated stack, which is also the second, let's say, common use case. So you basically disaggregate, you basically separate the storage node from the compute nodes with a good networking connection, because then your reads and writes will be happening on the networking side. If you use the hyperconverged one, the reads will be hitting local device, while the write is just going to the remote replicas. But on the segregated stack, your reads and writes both will hit the network. That means that you will need a pretty good network for that. And the cloud deployment is also a thing, because what we have here is a software, and then you can install it in any Linux that you want. And the cloud deployment is not an issue for us. Edge computing or hybrid edge computing is another use case, and the LinStore satellites are lightweight, so it's just a small service that runs in the Linux. And then the RBD is also really lightweight kernel module, so they are not consuming any CPU at all. What CPU consuming thing is your encryption or the duplication if you choose. If you didn't choose any of these, the RBD and LinStore will consume really small amount of CPU and memory. And then there comes the hybrid cloud or hybrid stack. So normally, as you all know, people are transitioning from cloud to on-premise or on-premise to cloud, and the LinStore and the RBD can provide you this functionality, because the LinBit itself, the RBD itself is operating system agnostic, and you can even mix and match different kind of operating systems to replicate your drives. And we don't care, the RBD doesn't care if you're replicating from on-premise to cloud or cloud to on-prem. All you need to have is a good bandwidth and a low latency. If you have low bandwidth and low latency, then you can also have asynchronous mode, because the DRBD can run in synchronous or asynchronous mode. And if you even have lower latency, lower bandwidth and higher latency, then you can switch to snapshot shipping. That means that your real-time replication will be gone, but you can replicate your drives with shipping your snapshots. That's also another case. Okay, let's talk about a little bit more about hyperconverged. This is the one single example of hyperconverged. Let's say you have one VM here, a local copy, replicated with the RBD on the second drive here. And the VM is actually working here with a local storage node. And when something happens to this, let's say, hypervisor, the VM will move into another hypervisor. This can be the ideal one, right? And when this VM moves here, And what happens is linstore in the RBD creates a local replica while the VM is reading and writing from the secondary copy here. That means that your VM won't go down while the replication is going to a state that we desire. In this example, it's two-way replicated, but you can create up to 32 replicas per resource. That means that you can go from 2 to 32, but if you ask me, I never seen anyone that wants to replicate more than 3. That's the most that's the only case that I see, not even 4. So this is the hyperconverged case. Your VM will move to another hypervisor while it's running without any issue because the replication is happening real time. There will be no single block that is missing in your setup, right? And this is the disaggregated stack when you separate your hypervisor with storage nodes. And then the VM is running from this storage node without any issue. And if something happens to hypervisor, it just goes, the VMs moves into the second hypervisor, and they will keep on running without any issue. Because the disk that is that you can see it locally is actually running in the storage node, but it's shown as a local device here. And when you move it, it's the same. I mean, this hypervisor is already a secondary to this primary driver, DRBD devices. That means that your disk drive here will be available and expecting someone to read and write consistently. And your storage node can also fail. It doesn't matter because we are working as a active and passive. That means that the passive node will take over really, really quickly in matter of seconds, couple of seconds, and then your VMs will keep on running without any issue. So let me explain what is the takeaways for this presentation. So the linstore and RBD can work with VMs, containers, or bare metal workloads. It doesn't matter, and it can provide you no vendor lock-in, so you don't have to worry about looking in a vendor. And it is an open source solution. Whatever we have, whatever we produce, it's open source since 20 years now for any kind of workload, and available for pretty much all Linux distributions out there. That means that you can install whatever flavor you want to have. And our solutions are aimed for high performance and low latency. That means that no issue at all with the performance because the DRBD is always refactored for the best performance use cases. And we have like millions of installations on the internet since 20 years now. So we have the knowledge of having a storage, producing a storage device. And yeah, a multi-hypervisor support is there also. So you can have like different kind of flavors in your cluster. So this was my presentation. I had a small time to prepare myself. I'm really sorry about that. I wish I could talk more about resiliency on technical level and everything, but I couldn't have too much time. I'm sorry about that. And if you have any questions, I would like to answer it here, or maybe if you want to do it after, here is my email, our GitHub link. So if you want to check our solutions. And yeah, thank you for listening. And that's it. Do we have any questions?
Yes, Yusuf. Thanks a lot, Yusuf. Thanks a lot for your insightful presentation. So in the start of the slide, you mentioned about upgrades to the underlying hypervisors or storage without interruption to I/O. Could you share some more insight on it? How is it because of the replication that linstore does that we are able to seamlessly move between the nodes?
Okay, let me show you from. Give me a second. I will open another one, right?
Sure, please.
Second, please. I will show you a okay. Let me share my screen again. Where is it? Okay. Okay, hope you can see. So this is what LinStore's structure is looking like. I mean, hope you can see it. This one. Maybe it's a little bit small, but let me make it a little bit bigger. Okay, now it should be fine. So this is how LinStore looks like. All right. So there is a controller here, and then the satellites. So the controller can be anywhere else. You can even put the controller in Raspberry Pi if you want to, because it's not in the data plane. So everything that controller is responsible is for, let's say, creating a DRBD resource. It just says, okay, I need to create a two-way replicated DRBD resource in my cluster. So where is my resources? Do I have some free space, for example? It checks the cluster and creates your DRBD resource as you requested, and then gets out of the way. That's it. So the controller is only there to control your cluster, and that's it. So it's not sitting in the data plane, just like others. For example, I will not mention, maybe I can, but I don't know if I can. So there are some like other open source SDS solutions out there. When you kill the controller, the IO stops, right? Because the accessing the data is possible with the controller, but in this case, it's not. And that's why the controller is like really lightweight, small software that is just doing the jobs that you gave him. And for second, the satellites are also, again, only responsible for carrying out the controller's orders, right? So the controller says, okay, let's create two-way replicated DRBD on this node and this node, all right? It sends the command to the satellites, and then the satellites creates the DRBD resource, creates the configuration files, starts syncing them, and then gets out of the way again. So that's why the controller and the satellites can be shut down, upgrade, or whatever you want to do, right? Because the IO is happening on the DRBD level. And once you set up the DRBD, you don't need LinStore at all. And the good part is, let's say you don't want to use DRBD LinStore after 2 years, all right? You don't like the software, you don't want to use it, but you want to keep your data going. You can just remove the software of LinStore. Let's say you're using Red Hat or, I don't know, CentOS with DNF or Yum, just Yum, remove LinStore controller, that's it, it's fine. The data will keep running without any issue because what's happening is the RBD is handling the IO. And the LinStore is only leveraging the tools is already in Linux. So we don't use anything else. That's why even if you remove the LinStore, the stack you have, let's think about it. The encryption is looks, the caching mechanism, it's Bcache or DMcache. The application, it's VDO. The replication, it's DRBD. It's also in the Linux kernel. So whatever the LinStore leverages, it's already in Linux, the LVM, the ZFS. So these are the tools that we're already using it, but separately. So what LinStore is doing, like giving you too much time so you can spend with your family, all right? So you just set up your LinStore controller, set up your LinStore satellites, form your cluster with one single command, that's it. Then you just start creating your volumes. And even if you're using some kind of operator, let's say OpenNebula, all right? And my presentation was actually dedicated to OpenNebula, but I tried to change it a little bit. So let's say OpenNebula, right? And when you add LinStore to OpenNebula with the plugin that we already created, and OpenNebula manages everything for you. So you just do everything from the OpenNebula GUI. Open, create a VM, two-way replicated, that's it. nothing else. And everything will be handled by LinStore itself. That's why I was telling you that, yeah.
Great. Thanks a lot. Thanks a lot, Yusuf. This was a great session. And I guess we don't have any more questions from here. Oh, something just popped up right now. So echoing the question from Raja. So the question is LinStore meant for large file workload, or there is a no file level striping?
Can you repeat the question again?
Is
please?
LinStore meant for the large file workloads, or is it meant for some other types of workloads for managing the software?
Okay. Yes, the LinStore is mainly for the VMs and the Kubernetes pods, and it's mostly focused on performance when you need some performance, all right? Like database workloads, like computational things, and so on. But it's not block, it's not object, it's not file, it's just block. So whenever you need a block storage, LinStore is there. I mean, it can be large too, by the way, because one of our customers is managing plus 2 petabytes, I think, plus 2 petabytes with LinStore. Not, I don't remember the exact number, but plus 2 petabytes with LinStore, but it depends on the need. I mean, so I cannot categorize the LinStore with this simple thing, but it's just, let me tell you that, yeah.
Okay, great. Great, thanks a lot. I guess we don't have any more questions. So back to you, Reena.
Thank you, Santosh. Thank you so much. A big hand to Yusuf Yildiz, wherever you are. Please do type applause on the chat box. Thank you, Yusuf. We have received the information that you were in the airport on your way to Vienna, and you made sure that you attend this by taking a room and ensuring that you're here with us. And I think that calls out for a round of applause. We're so grateful to you and to your time. Thank you so much. Thanks a lot, Yusuf.
Anytime. Goodbye.
Such a pleasure having you with us. And I want each of you to type applause on the chat box. I think that definitely calls out for someone making time to be here amongst us and share the information and have such an intuitive session. Thank you so much once again, Yusuf. And we see so many applauses coming in on the chat box. We are delighted. We are happy. And on that happy note, we would like to move ahead to our next session too. Well, on that note, our next speaker is Professor Onur Mutlu, and ETH Zuri is where he's joining us from. And this session is a fireside chat. And as I know, we have Ankit already joined us here, who's going to initiate this particular chat. And then we are waiting for it. Ankit, are you ready?
I hope so. I'm ready. It's an honor actually to get an opportunity to talk to Professor Onur Mutlu. If someone wants to recall the who's and who of computer architecture, and one of them would be Professor Onur Mutlu. Professor, I don't see your video yet. I guess the spotlight thing works, selecting people who are speaking.
Can you see me right now? I was muted. Sorry. Oh, hi, Ankit.
We can see you and we can hear you, Onur. Yeah, over to you.
Great. You can hear me. That's great. Thank you.
Marhaba, Professor Onur.
Marhaba. How are you, Ankit?
I'm good. And also joining me is Professor Manu Avasthi. I'm sure, Professor Onur, you already know him, but let me introduce him. He's from the Ashoka University, and he will be joining us, bringing in the university perspective, the academic perspective to each of the questions and discussions that we are on to.
Okay.
Hi, Professor Manu.
Hi, Ankit. Hi, Onur. Good to see you.
Hi, Manu. Good to see you, yeah.
Yeah, and just a request, Shingappa, if we can have the slide unshared so that we can see each other well. So, yeah, Professor Onur, let me get started right from the beginning, maybe. Beginning in the sense like from your experience. And I'm not sure how it's done in Turkey, but in India, most people, they do the undergraduate in India and then go for higher studies, their MS or PhD abroad. But I see that you're someone who actually did the schooling in Turkey, I guess, if I'm not wrong. But then for your bachelor's and your master's and your PhD, you were at University of Michigan, University of Austin. Maybe you can tell us about how their journey went, and it might be good perspective for the students who are joining in India. Like, how did it go? How did someone become the Professor Onur Mutlu?
Thank you, thank you. You're very humbling. Yeah, it's true. At the time, at least, I did this journey, and I finished my high school in 1996, and at the time, what you said was true for Turkey also. I think it's still true. Most students go to a university in Turkey, and then a fraction of them go for further studies either in Turkey, but many of them go outside Turkey after finishing after finishing university. Sorry. So what I did was I finished high school, and then there's a university entrance exam that you need to take in Turkey that everybody needs to take. This was actually quite a tough exam at the time I took it. Over time, it has changed. We can talk about the current version also, but at the time it was 2 set of exams, and basically you need to do well, quite well, if you wanted to get to a top university. So I took these exams, worked hard during the high school, and I did quite well in the end. I was placed at Bilkent University, which is one of the top universities in Turkey in computer engineering, and I started it. But at the time, there was a opportunity that the government provided, Turkish government provided, which was if you did well in this exam, top 100 or 200 people, then you had a chance, basically, you had an opportunity to go abroad, assuming you get admission from a university in, I think, one of 5 countries, US being one of them. Switzerland was another one, for example. I believe Germany was another one. And it was fully funded by the government with the condition that you would go back and serve the government, hopefully in a nice position. It's not clear that's if that's always true. Basically, you could be a professor, for example, if there's a position, of course, available for you at the time you return back. So I took this opportunity at the time because I wanted to explore, have a, let's say, a different path, understand what I could learn from a foreign, let's say, different culture. And I applied to US universities, and I got into some of them. In the end, I ended up at Michigan. So I started, let's say, my second year of the university at the University of Michigan with support from the Turkish government. So it was a good opportunity in the end. Because otherwise I wouldn't have the means to go on my own or on my family's budget I wouldn't even consider it, basically. But I got a letter saying that you have this opportunity. Do you want to take it? If you want to take it, these are the steps that you need to take. Apply to a university, get in, and then we will support you, assuming it's one of the universities that we approve. So that's how it got started.
That's true for a lot of us in India also.
Yeah.
Yeah.
Yeah, and then that's how I ended up going after high school, basically. Let's say 1 year after high school, because I studied some time at Bilkent also. And I right now I have a lot of friends at Bilkent University who are professors, and we collaborate with them. I get students from Bilkent University to my research group.
Awesome.
So it's certainly good connections with Turkey.
So I think, Professor Manu, you would also agree. I think that was the era when the processors would actually go for very deep pipelining, and that was the mechanism of getting more performance out of the system. And at that point in time, I see that even in your PhD, you took an alternate approach. You wanted to shake the world, and you came up with efficient runaway execution processors. But yeah, Professor Manu, do you want to add some spice to the question? How did you get about doing that? As in, do an alternate.
Okay, sure.
I mean, I'll just sort of try and reframe the question that I guess Ankit is trying to ask is, you went and did your PhD with Yale, Pat. How did you end up with run-ahead execution as your thesis topic?
Okay,
Or,
okay. That's...
I mean, was it a circuitous path to run ahead execution, or was it something that you sort of like, okay, this is what I'm going to do, or did you try out a whole bunch of stuff
Yeah,
before you ended up there?
Yeah, that's a good question. Basically, how did we end up with this topic? So I started my PhD in August 2000, and I started working on Runhead, let's say, in 2002, maybe if I remember correctly, let's say February 2002 or so. So it took some time to get to it, clearly. Let me give you like what I did in the first, let's say, 1.5 years or so. So I was very excited about microarchitecture. Of course, microarchitecture was a big thing at that time. How to speed up the process, how to make them energy efficient, and Yale's group was one of the top groups in the world, clearly, on that topic. So when I went in, I was very interested in the memory part of things at that time also, because memory latencies are long and processors are stalling. They're still stalling for memory. And how do we actually overcome this bottleneck? So basically I worked on several ideas, smaller ideas, like memory disambiguation, which are interesting, but how do you disambiguate between loads and stores so that you can do better scheduling? I worked on prefetching as well, like how do you improve the performance of prefetchers, different prefetching algorithms. And then I spent one summer at Intel in the product group, the Pentium 4 group at the time. They were transitioning to the next processors at that time, of course. And I worked a lot on prefetching and simulation at that time. And we were doing a lot of studies on what kind of a performance improvement prefetcher would provide. How does it compare to large instruction windows, for example? That was one of the studies because these are potentially approaches that you can combine, but they could be alternative also if you look at it. And we were looking at the performance energy curves, for example, for these using simulation, of course. And basically, we did a lot of studies on large instruction windows. And over time, during the discussions, we were thinking, can we somehow not build these large instruction windows? Because large instruction, for those who are on the call who may not know a lot about instruction windows, this is basically how many instructions you can put into the machine and keep processing before you get a stall. How many instructions are decoded but not yet retired from the machine, basically. At the time, the number was around 126, 128. Today, the numbers have increased. But our goal was to, so if the size of this window increases, you get better tolerance to memory latencies, because memory latencies are on the order of hundreds of cycles. And if you're fetching, let's say, 4 instructions per cycle, if your memory latency is 500 cycles, you need really a 2,000 entry instruction window so that you can tolerate every single cycle of that latency without stalling. But if you want to build this very large instruction window, it's expensive in terms of hardware area cost, energy, complexity, verification and design complexity. And our goal was basically to get the benefit of these large windows without actually building them. So that's how we really came about. We want to, I was working on prefetching, I was working on large instruction windows. I didn't like the large instruction window approach because of the downsides that I just mentioned, but I like prefetching. But I didn't like the ability of, let's say, inability of prefetchers to capture complex access patterns. So if you look at a lot of prefetchers that was built at that time, they were very good at streaming, striving access patterns that are easily predictable, and they could prefetch the data into the memory. But they were not very good at, let's say, more random access, complicated patterns, because they're hard to predict, of course, with pattern matching, etc. So basically, at that point, we realized that most of the time was also getting spent on stalling for memory. And we kind of had the idea, can we somehow not stall for memory during that time and use those cycles for prefetching? That was basically the spark of the idea. And once you, I think, get that idea, the Runhead kind of follows. You basically, instead of stalling, you basically keep executing speculatively. I can, of course, go through slides if you want to go through the idea. I don't know how much in depth you want to go through. I recently talked about Runhead and prefetching in my one of my last lectures in the Digital Design and Computer Architecture course, lecture 25, and we covered Runhead idea. So I have slides also if you're interested in it.
Oh, okay, amazing. But actually, we want to hear the whole breadth of things. And
okay, sure.
well, you worked on so many things, and your experience has been like spanning much of the computer architecture has changed over that period of time. So actually, if you could take our audience through that evolution as well, like all of the compute has evolved independently at different speeds compared to the network has evolved, memory has evolved independently. And each of these, whenever they have evolved faster, they have gyrated and made the entire deployment and infra move towards a deployment which benefits from that. For example, when the compute was growing really fast, you had scale up, a lot of scale up, so that single systems could actually run more complex, more heavy processes. But then the CPU, single CPU stopped growing stronger. Then the multi-core systems came in, and then that's also hitting the ceiling somewhere. Then the network guys took over and said, like, why can't you make larger distributed systems and then put things together, right? So just want to hear from your perspective how you have seen and maybe lived through all of these evolution of architecture, like from when you have seen it up close and how is it today? And maybe if you can drop us a few hints, like what are the future subsystems of research and areas where you see that more energy should be put into further the research.
Yeah, that's great. That's a long history, so I could take hours about this, but I'll try to summarize. You know, I mean, if you look at a computing system, as you mentioned, it's you have computing, communication, and storage and memory. These are the three major components, the way I see it, and clearly these components have improved over time. But I will maybe mention one thing over the decades. I think we have focused a lot on the compute part, and we've improved it a lot more than the network and the memory part, in my opinion. As a result, we're having a lot more bottlenecks today in the memory and the network part. This doesn't mean that there have not been improvements, as you mentioned, because of faster interconnects that were developed. Now we have better distributed systems and even disaggregated memories and disaggregated storage so that we can communicate with those disaggregated with a remote memory in, let's say, reasonable latencies, because the network is fast enough for us, right? So clearly there have been improvements on the network, interconnect, and the memory and storage side, but they have not been, in my opinion, on par with the improvements on the CPU or processor side in general. And in my opinion, one of the main reasons is really these other components, interconnect and memory and storage, have not been viewed as computational components. They're communicating data, they're storing data, but they're not able to compute on the data. And in my opinion, this is a very good future direction. Maybe we'll talk about that afterwards. If I have to summarize the improvements, I think computation was a huge bottleneck since, let's say, 1960s, 70s, 80s, 90s, and people pushed on that bottleneck, especially general purpose processors, right, to improve computation capability. Especially Moore's law helped us because you were able to get more transistors on a chip that you could use for more scalable computation on a chip, even in a single core and then later multi-core. And then also each transistor was improving in terms of performance and energy, right, over time until 2000s, let's say early 2000s. So that these two trends enabled, and also architectural improvements that people wanted to put on computation because you needed to improve computation, enabled our compute units to be extremely powerful and efficient. And at some point, single core was not easy to scale because of complexity and power issues. So people moved to multi-core, and multi-core is also not relatively easy to scale. So people are moving into more accelerator-based systems, right, that can specialize to different types of computation. So we're actually pushing a lot on the computation side, as you can see. Now we have specialized compute accelerators, not just general purpose cores or general purpose GPUs. I mean, GPU is an accelerated machine, but that was also used for general purpose workloads. But now we have machine learning accelerators, video accelerators, and other accelerators are coming clearly, encoding, decoding, compression, decompression, etc. So we have a lot of accelerators in our system right now. So that shows, I think, the effort put into computation. On the network side, I think the faster networks enable bigger distributed systems, but also it's enabling better communication with memory and storage, and also communication with accelerators going into the future, because these accelerators can be on different chips. And I think like newer interfaces that are coming up, that people are looking at, cache coherent interfaces like CXL, for example, those interfaces that are enabled by faster communication protocols can be also good at scaling compute as well as scaling memory. And on the memory and storage side, I think there's a lot to talk about over here also. But I think like improvements have been especially driven by technology, just like in the interconnect. Like flash memory was not a big player until, I would argue, even 2000s, right? But after that, flash memory, people figured out how to design reliable flash memories that can scale into very large sizes by ensuring that the controllers can actually ensure reliability of the flash memory. And as a result, it's all in all of our lives. Right? That has enabled the mobile systems that we can carry today. I cannot imagine the system, for example, without flash memory. So I think that sort of new technologies have enabled new things. And on also on the data center side, flash memories have been extremely successful, clearly. So if I look at each individual components, there have been clearly improvements, both on the technology side and architecture side. But I think right now we're running into issues in the sense that compute is very heavily optimized. So we've had what has happened over the course of, let's say, 70 plus years, in my opinion, is technology scaling was on our side. So transistors became extremely fast and extremely efficient. Right now we're having trouble scaling the transistors, but people are still pushing on it. But unfortunately, interconnect did not scale as much, interconnect and memory technologies. I mean, there have been improvements, no question about that, but not at the same rate as transistors. As a result, the data communication between these transistors that are extremely good at doing computation has become a bigger bottleneck. So I think we're having interconnect and memory bottlenecks in all of our systems today because of this reason. And this can certainly be solved potentially by newer technologies, right? Looking into much better interconnects, much better memory, and that should be worked on, no question about that. But also rethinking the architectures that we have today so that this bottleneck is not exacerbated. Today, we're actually exacerbating that bottleneck over and over because everything has to move to the processor or the accelerator so that we can do some processing on the data. But data sits far away, right? Large data sits in large memories, large storage, and it has to come through the interconnect. So we're exercising the memory and storage and interconnect bottleneck to process the data. But if you actually shift the architectural paradigm to be much more data-centric, such that we can have processing units, accelerators, right next to memory, inside storage, inside the interconnect, basically everywhere where the data resides or gets produced. If we can have that capability of processing, we can have a much better, let's say, more balanced distributed system that has less of a bottleneck, let's say. Hopefully that has given a summary.
Yeah, definitely. So the other day I was talking to Professor Manu about near memory and in memory, and there were a lot of acronyms around the same. But then we actually thought like maybe a lot of our audience doesn't really think of them as a different thing. Maybe they are really the same for them. And today we have the guru of such compute that's in memory and near memory with us. So actually it might be a good opportunity. What do you say, Professor Manu, to actually first know about like what is the buzz about the in memory and near memory?
Mm-hmm.
How are they different? Like, and what about them?
Okay, so you would like to see the difference between in memory and near memory. Okay, I think here...
So maybe not just the difference, maybe first for the audience, you may want to introduce to start with what do we mean by each of them?
Huh?
And then like, are they actually pointing to something similar? So actually I was talking about one concept we have in the industry, and Professor Manu said like maybe it's not a very generic term.
Huh?
The inertia around data. That is,
Okay.
if you have lots of data in one place, the tendency is like we may want to dump more data at the same place rather than have another distributed system and start putting data there. So the term that we often end up using, or maybe some journals end up using, is data gravity.
Okay.
So maybe from that point of view, and then about then you can bring in like where would you use which of these technologies.
Okay, I see. So maybe it's a good place to share one slide, or if you don't mind, because I think I can't share content. It says if you allow me to share content, I'm happy to share.
Yes. Chingappa or Asif, can you
Okay.
give the rights to Professor Onu? Yeah, maybe just a moment.
Okay, sure, yeah.
Yeah.
I mean, in the meantime, I can start maybe while I'm getting the rights. Clearly, so I will define the terminology a little bit differently. I think you're talking about two things that make sense. But before we go into it, clearly we have a huge data bottleneck today, right? We have to move the data all over the place so that we can do computation. And in general, I call processing in memory. Processing in memory. Actually, maybe even more generally, processing where it makes sense, in my opinion, because data gets generated at many different places, at sensors, for example. In genomics, for example, you have these sensors also that generate data that sequence your genomes. So there are many, many different places where data gets generated. And if we can do processing as close as possible to where the data gets generated, then fundamentally we move the data less, right? I mean, intuitively, this makes sense, I think. And then the question becomes, how far do you go? Like, do you really do the processing right exactly where the data is generated while it's being generated and stored? When I say generated, you can actually change it to stored also. So data may be stored in a big storage device. Do you do the processing while it's being stored without moving the data at all, right? That's one possibility. And I think I would call this processing using memory. I think this may be the one that you mentioned as processing in memory, right? This is basically you're using the memory device to do some computation in addition to storing the data, for example. Or you're using the sensor device to do some computation on the data in addition to sensing the data at the same time. You're using essentially the same substrate to do this. If I can share, I can show you some.
Sure.
I'm not sure.
Yeah, Mr. Chingappa or Asif, can you help with the rights?
Yeah, maybe not. Maybe my other, yeah, it's not also able to share. I'm logged in into devices, but.
Okay.
Yeah, but that's what I consider as processing, using memory. I call it processing using memory because you're using the same memory device or sensor device to do computation in addition to memory. And this, I think, can be done. So if you look at, for example, memory devices, DRAM, for example, it has a capacitor, an access transistor, and sensing structures, etc. Normally, we think of that as a memory device, right? But this memory device, if you think about it from a computation perspective, it can also do computation, right? And processing using memory. Okay, I think I can share right now. Let me. Yeah, maybe I don't have it. Okay, I already discussed some of this basically, but so basically, maybe I'll put this slide up. Sorry. Processing using memory is the fact that you can use analog computation capability of the device to do bulk data movement and computation by exploiting the internal connectivity that you have inside the device, by exploiting the analog computation capability, but not adding a processor, basically. In emerging memory technologies, for example, a lot of them have this 3D structure or crossbar structure, sorry, where you can actually do matrix vector multiplication based on pure analog computation capability. So that's one example over here. And I believe all memory technologies have this. All memory technologies are memory devices, but they can also do some computation because of the way they operate. In DRAM, based on chart sharing principles, you can do triple row activation that enables you to get a majority function, bitwise majority function, for example. And you also have a bitwise complement because of the way you sense the data in DRAM, because you need sense amplifiers to sense the data. So you can basically do very basic bitwise operations in DRAM. I'm not going to say for free, but without adding adders, without adding and or not logic. It already can do it based on the analog operational principles. So I think of this as processing using memory. I'm not sure if this was the one you mentioned as processing in memory from your perspective. Is that correct?
Yes,
Okay.
I think because it's not the near memory one.
Exactly. Okay.
That's
Okay, that's great. Yeah. Yeah. I like using memory because processing in memory is kind of a very broad term that's been used a lot, and people refer to many different things when they say in memory processing, in memory computing. But I think processing using memory kind of clarifies it by saying, okay, you have this memory device, you use it for processing as well. Processing near memory, I would argue it's almost everything else, basically. You have processor here and memory here today. Processor can be CPU, GPU, FPGA, accelerator, anything, basically, any compute unit. you basically push that closer to memory. At some point, you can push it in the same subarray as memory, in the same bank, in the same memory chip, but it doesn't have to be in the same memory chip. It could be, as long as it's closer than the current processor, it could be in the memory controller, for example. It could be in the logic layer or 3D stack layer. So processor is similar to what we think of today, some sort of logic that can do computation, that's designed to do logic, not designed to do memory. And then you get it near memory, as near as possible, ideally, right, to minimize the data moment. So I think
But Professor Onur, like for a layperson, like if we go back 20 or 30 years, right? So when you say near memory, we are just saying that the latency between the processor and the memory is being reduced. Basically, principles of physics, be it because of distance or improvement of the bandwidth or interconnect. So can we say that even the general purpose CPU today is nearer memory compared to it was like 20 or 30 years back?
Well, okay, that's a great question, basically. I mean, in a sense, it's near. Well, it depends on the latency, right? How you define the latency. If the latency is defined in terms of, let's say, maybe raw latency, it's reducing, yes, over time, slowly. But if the latency is defined in terms of how many computation can you do in the time frame you can access memory, then the processor is far away, I would argue, compared to a CPU 20, 30 years ago. So in that sense, I think basically, I would argue maybe a better definition of latency is how much opportunity cost you have. You're waiting and you cannot do computation. You're basically wasting the opportunity to do computation for waiting memory. So I would say it's not closer to memory.
Okay, all right.
Yeah, that's a good question. But I think, for example, there are some examples like where GPUs are getting very close to memory today. You have high bandwidth memory systems, and GPUs are getting connected to high bandwidth memory system to 2.5D stacking, and maybe over time 3D stacking, we will see. I think those are definitely reducing the latency and improving the bandwidth significantly. So I think GPUs today are much closer to memory compared to, let's say, past GPUs 10, 20 years ago. Yeah.
I think maybe because they didn't have the same legacy to carry forward, like how the CPU and the DRAM interconnect had to deal with. Yeah, Professor Manu, do you want to put in an additional question along and let Professor Onur take it from that?
So, I mean, this is very interesting. Thanks, Onur. One thing that I'll sort of add on to this, and that sort of ties into your previous comment about, you know, how a lot of the performance improvement that we've gotten is because technology has been improving, right? And you certainly have done a lot of work in terms of bridging the chasm that sort of exists between, you know, technology that comes out and the architectural application of that technology. I mean, especially, for example, the work that you've done now, maybe a decade back on PCM, right? So, so how do you sort of go about doing this? So let's say I was a newish researcher and I wanted to sort of be at this nice interface where I want to, on one side of things, look at, you know, where technology is evolving, and get ideas about how to use that technology to solve architectural issues. Right? If I was somebody who wanted to do something like that, and it could be anything. It could be memory, it could be storage, it could be, you know, processing near memory, or any other kind of architectural innovation. How would I go about doing that? What would your suggestion be?
Okay, that's a great question. I think I guess depends on when you start, right? If you're an undergraduate student, then I would basically let me stop sharing so that I can see everyone also. If you're an undergraduate student, I would suggest getting into research basically right away, as early as possible in your career, so that you can start understanding what's going on in the field, right? Because I don't think it immediately comes to everyone. You really need to have some understanding of what's going on in the field so that you can bridge the gap between a new technology and put some new way of using it, for example, in architecture. So I think having some understanding of the research in the field, trends in the field, certainly helps that. For that, I think studying trends in terms of technology is good. But maybe from my experience, since you mentioned the phase change memory paper that we have done a while ago, the way we came about with that one was we were looking into DRAM. We were looking into memory basically, and we were basically thinking very fundamentally. Okay, DRAM is good. Maybe it'll last for some time, but it's having a lot of scaling issues. And we read a lot of papers. Like there's a paper from IBM in 2002 that talks about DRAM scaling. It's a beautiful paper. I would recommend to people. And we read a lot of scaling papers on DRAM, and it was clear to us that at some point the scaling will become very problematic because you cannot make a DRAM capacitor smaller than some amount and keep it operating reliably, right? And then the question, of course, becomes, okay, once scaling stops, how do you improve the system? And then there are two directions. I think if you, I like the first principles thinking. Maybe I would, that's what I would recommend perhaps to people. Once you start to build some understanding of the field, it's good to have some first principles thinking. Try to identify what's the fundamental problem. Okay, the scaling of memory, DRAM technology is the fundamental problem, according to us. Then the question is, how do you solve this problem, right? And I think fundamentally there are at least two directions, two major ones, let me say. One major one is keep DRAM as much as possible and improve the system, right? Okay, DRAM will not scale very well, but it's good, let's say. How do you improve the system? And that brings us, I think, to issues like better controllers, processing in DRAM, so that you can basically add other values to the DRAM as opposed to the intrinsic technology scaling value, architectural values, let's say. So that's one option. I think that's a direction we pursued also a little bit later, not immediately. But the other direction that was also quite interesting to us is, are there technologies that can potentially be candidates that can replace DRAM or augment DRAM and have properties that are at least some properties that are better than DRAM? And that's sort of first principles thinking enabled us to look at, okay, what are the technologies that may be coming up? And we studied a lot of papers that were in conferences that we don't normally publish at. For example, IEDM, International Electron Devices Meeting. ISSCC had some papers also, solid state circuit conferences, etc. So that we can basically do some, let's say, scouting on the technology that people have been looking at. And we talk to people in industry, of course, although they don't necessarily talk to you if they're working on a very emerging technology. That's very, I think industry academia cooperation is very nice, but sometimes it's harder to do, especially in the emerging technologies domain. If someone is working on emerging technology, it's a bit harder to get data out of that. That's not published, let's say. But we did a lot of scouting of the papers, and we found out, for example, phase change memory is a very nice potential candidate with nice scaling properties. It's not perfect, but it's closer to DRAM, for example, than many other technologies, especially flash memory. And that's how we got into looking into phase change memory. And then we studied its properties as much as possible, given the limited amount of data that we had, and understood what we could do with it. And then we basically decided, okay, this is a good candidate. How do we now design the architecture to take advantage of it? And that was the paper, for example, that you mentioned. And I think in the end, maybe there's no single formula. You need to do a lot of reading. You need to go into research. You need to think about the field in a first, let's say, first principles manner, and try to take a step back from what people are doing, and let's say think a bit differently. Maybe I don't know if this helps, but it does require effort. Let's say I don't think it comes, let's say, right away.
No, absolutely. I agree, right? I mean, to your point about sort of scouting other fields, I definitely personally believe in that as well, right? I mean, with existing things that are out there, there's only so much that you can do. And given how fast technology is changing and how much, physicists and material scientists are creating new things every day, I definitely think that there is, like you mentioned, potential in sort of going to what you might even call sister fields of architecture, and sort of getting enough information from there so that you can, actually get that data out to solve architecture problems. No, I think that absolutely helps.
Yeah, absolutely. I agree. And it also happens. So this, I think I agree with you. The materials and all of that. It's good to look even forward, right? To see what's coming out. It also happens on the higher end of the stack as well, in my opinion. The higher end essentially is you have applications. That's again maybe sister field of architecture, right? You have applications and workloads, algorithms. How can you? What are the really? What are going to be the algorithms of the future? Let's say, thinking about the future and how can we basically build better architectures for those algorithms of the future? And that's a completely different way of enhancing systems overall. But again, it's looking out into the future and looking out into some areas that maybe you're not originally comfortable with, right? And if I have to point out something from my experience, sorry, I think that's how we started the genomics research, for example, that we've been doing genome analysis in 2007 or so. Now we're doing a lot of work in that area because we built the critical mass and understanding. But initially, it was not very easy for us to really understand what are the applications in genome analysis. We scouted the application. It's going to be an important application, clearly. And I think COVID-19, if nothing else, has proven that was true. I hope that's not the only reason. I don't think that is actually. But understanding the applications takes time also, and building architectures that can execute these applications, let's say, extremely efficiently, takes time. And I'm excited about these directions still.
So that came as a proof of concept, like whatever technology you have developed till now. Now, why don't you try it out with COVID-19 and see if it works or not? Like a POC.
yeah, sure.
So maybe I'll just ask one more question since you've brought up applications, and that's sort of that's a top-down approach as opposed to a bottom-up one, which is essentially trying out new technologies to solve architecture problems. Now, how do you go about doing it the other way? So let's say when you started working in genomics, right? I mean, was it something that you identified as an application area that is going to be extremely important in the future? And if let's say I was a first or a second year PhD student who wants to do a top-down kind of a dive into architectural innovation, how do I go about kind of selecting what turned out to be genomics for you, let's say, an application class?
Yeah, that's a very great question also. Thanks, Mona. Yeah, how did we identify genomics? So I think this also depends on your personal interest, perhaps, right? It's clearly there's so many domains, right? You cannot work on all of them. In the end, machine learning was clearly another important one to look into, but a lot of people are working on machine learning clearly today. So it sounds a little bit less exciting from that perspective. But I think it's good to read as much as possible in other areas where people are working on new algorithms, new applications to understand. But it's also good to think about what are the overall problems. Again, maybe I go back to first principles, right? And maybe I don't want to make a huge deal of it, but I think it's so important. Like, what are the really big problems that humanity is facing? And I think if I have to count several, climate a big one, for example. So climate applications are clearly going to be important into the future. I think health was what we were interested in at that time, and that's going to be always important. And what really prompted us towards genomics at the time was there were these sequencing technologies that were developed, that were basically very hot, in the sense that high throughput sequencing technologies were being developed in the 2004, 2005 timeframe, and they were able to sequence lots of data. So people were actually generating a lot of data at that time. And we were actually interested in analyzing that data so for for health and medical and scientific purposes. And that's what made us think, okay, this technology is only going to get better. So in the end, there's a technology perspective also at this, basically a very low level perspective, because the application is enabled by another technology, the sequencing, genome sequencer, essentially, that has been extremely capable because of very low level advances. And we basically said, okay, this technology is going to be much better in the future. And it did become much better with nanopore sequencing devices, for example. It's a very specialized technology. So clearly our computing infrastructure is not going to keep up. So we're going to have a huge mismatch between the amount of data that we can generate and amount of genomic data that we can generate an amount of and the capability of the computation to process it. So we should really do something about it. And when we first started, we basically started looking into read mapping. How do you actually reconstruct the genome from chopped sequences that you get from a genomic sequencer? And we basically tried to develop faster read mappers because software was always an important problem. And then we tried to accelerate them in software. And then at some point we hit the software bottleneck. Let's say you have to go through hardware because what's happening in genomics is you have a very, very specialized sequencer that's extremely good at what it does. If you actually try to match its speed and bandwidth with a general purpose machine is not specialized for any purpose, right? That's why it's called a general purpose machine. So it cannot match the speed of the sequencer. And it was clear to us that you needed to do algorithm hardware co-design at that point. And we basically pushed toward that direction. So maybe I actually have a nice picture of this if people are interested, since we're jumping through a lot of topics, I think, which is good, but it may be sometimes good to have pictures. This is based on a presentation that I delivered recently. I'll try to find it.
No, actually, besides the papers that you have already published and we already know how you suggest to solve it, it's good to know from you, like, how did you go about solving it? Like, what was there going on in your mind?
Yeah.
How did you pick up the right problem?
Yeah.
And I think it's very good to hear from you on those aspects, which don't make it to the paper, right?
Yeah, sure. Yeah, sure. I think maybe I'm getting at that here, kind of. But if you want any more specifics, as far as I can tell, of course, because some of this is really introspection in the end, and it's not a perfect process, right? Because I was also lucky that I had a friend who was working on genomics at the University of Washington at that time. And I was at Microsoft Research at that time. So we kind of connected. We went on some hikes and we basically kind of said, this is going to be the future. Let's work on it together. So there's some, it's not just, I think I would probably be lying if I said it was just, okay, I just sat and thought about it. It's also a lot of luck, right? I think you need to do, I think Pasteur said, for example, luck prepares the, luck favor, no. I'm not getting it correctly at this time, but yeah, I think chance favors the prepared mind. Yeah, chance favors the prepared mind. I would say that, yes. So basically, there was some preparation that we did in terms of, okay, these are some interesting applications, but there was also a lot of luck. For example, if I didn't have that friend who was working on genomics, who's actually a very good collaborator right now, he's at Bill Kent University, John Al-Khan, then probably maybe I wouldn't really go into this, right? Or maybe I would, and I would take a different path. I don't know. Basically, it's a bit hard to tell. But I think in general, it requires, I think selecting a research topic requires preparation. You need to have some sort of thinking that you need to do reading, a lot of reading to do it. Again, following the trends. In genomics, it was again following the trends, in my opinion. Trends, at least at that time, in terms of the sequencing machines. And let me actually show you a more recent sequencing machine. This is a more recent sequencing machine. You can see that it's scaled a lot over the course of decades. And believing in the technology also, but we believed in the technology. We believed that people would actually come up with better technologies to produce even more genomic data. Yeah. And then I think, how do you go about addressing it? I think you have to get in somewhere, basically. You have to figure out like what is the state of the art in that area. And at that time, the state of the art was read mappers, for example. These machines produce data. You need to map them to a reference genome. And then you question basically, what are the bottlenecks of the read mappers, right? And then you can design a better read mapper if you understand the bottlenecks. Or what are the downsides? What are the issues with the read mappers at that time? And that's what we did, actually. I don't have that paper over here. That was 2009. And we wrote it with John Al-Khan at that time. And then the question becomes basically, is this read mapper good? What is the next step, basically? What are the bottlenecks that it has? And then it turns out there's a lot of useless computation. And how do you eliminate that useless computation with algorithmic approaches? And then what is the next bottleneck, basically? That's kind of how we proceeded in this direction. And I think that's if I have to put a method retrospectively into what we did, that was kind of the method. Of course, part of this was, again, luck and preparation and instinct at the time. And part of it was method also, because Okay. And this was, for example, what is being shown on screen was a paper that we did with one of my very recent PhD graduates, Damla, on nanopore sequencing devices. So this technology came about in 2014 or so, at least publicly. And this was a very fast sequencing device. As you can see, it's an edge device also. You can put it, hold it in your hand. And we wanted to really understand the computational bottlenecks associated with it. And we followed the method, basically. And this paper is all about that method. You can see even in the title, right? We have these tools for genome assembly. What is the current state of computation, these tools? What are the bottlenecks, and what can we do in the future to accelerate them? And later works that we did basically built on the insights that we uncovered in these prior works, I would say. I don't know if that answers your question, Ankit, but
Sure.
Okay.
So actually, yeah, let me take some time to quickly remind the audience that we have Professor Onur and also Professor Manu Avasti with me on the fireside chat. So if you have any specific questions that you would like to put across, use the chat window, and we will try our best to take those questions to Professor Onur and Professor Manu and see their views and what they think about it. So yeah, so Professor Onur, actually, I wanted to go back to the idea that you talked about, the near memory and processing using memory. So wanted your views on which kind of applications does it actually become more suitable for? Just like how a general purpose system can do pretty much all things, and if you specially built this nanopore device, but then it can't do many other things. It's very custom designed for a specific thing. So what are those specific things where I can actually think of this application, or maybe a part of this application, maybe a certain function I can do much better with near memory? And also, if you could help with an answer for where can I use the using memory? Let me use that term. So where does each one of them fit best?
Okay.
Where can I use those hammers?
Yeah. So that's a great question. That's a great research question also, actually, I would say. I think if people are interested in doing research, this is a good area, like understanding which parts of applications or which applications are a good fit for different types of processing in memory, near memory, using memory, and different flavors of each of them, clearly for different technologies potentially. And coming up with an automated method for identifying these these functions or applications that can benefit from different types of processing in memory technologies. So I'm not going to claim that I have answers to all of these questions, but we're doing research in this area also. But maybe I'll give some examples. Again, I think your slides can be helpful. So I'll start with processing using memory. And these are usually, it depends on the technology. And in my opinion, it depends on what you can do inside the memory, right? This is a slide from one of my PhD students also, Vivek Seshadri, who is at Microsoft Research India right now. I think Manu knows him well. But basically, the type of operations that you can do in the architecture processing using memory kind of, I don't want to say dictates, but immediately helps some applications more easily than other applications, right? And here we can do bitwise operations, bulk bitwise operations. As a result, applications that have a lot of bitwise operations can benefit, right? That's the idea. So bitweaving, so basically a lot of databases can benefit. Some web search engines can benefit, and you can see some other applications. And we've actually shown that these applications benefit significantly from processing using memory with this type of processing using memory in DRAM. Now, this substrate actually is a little bit more general purpose, which is interesting. So I didn't talk about some research because I don't want to talk a lot about future research here. I want to answer your questions more, but okay, sorry about this. But basically, it's not, once you start understanding the substrate, you can also potentially start making more general purpose, right? Okay, bitwise operations are great, and some applications are a good fit because they already naturally do bitwise operations, but can we do more general purpose operations in this processing using DRAM substrate? And that was our goal basically over some time. And this is a paper where we discussed how to make things a little bit more general purpose. Okay, we have this bit serial processing inside DRAM. It has a lot of parallelism. can we do maybe more sophisticated computations inside the bit serial processing? And again, I don't want to go into the details of it, but it turns out you can. It's still bit serial, so it still limits the domain, but you have to basically rethink your algorithms so that you can express them in a bit serial manner, bulk bitwise bit serial manner. This requires more effort, no question about that. Not all applications are designed this way. So if you can fit your algorithm to the substrate that's fundamentally bit serial and bulk bitwise, then I think you can gain a lot of performance. So hopefully that answers your question. Initially, an architecture may not be a great fit for some applications, but over time, you may realize that you can fit the application to the architecture. And I think with GPUs, that has happened a lot, right? GPUs, for example, were very customized graphics processors. Over time, people realize that, okay, there's a lot of computation capability. How can I fit my application to this customized system? And also at the same time, how can I make the GPU a little bit more general purpose so that I can actually get more applications on there? And GPUs have been very successful because of this reason, in my opinion. And I think I see a similar evolution in processing in memory in general. Processing using memory is clearly specific bit serial right now. But over time, if we start rethinking our applications and also modifying our architecture, we can execute more applications. Now, this is one type of processing using memory. There's also emerging memory technologies type, which is, as I mentioned earlier, you can do matrix vector multiplication, for example, right, in the crossbar arrays. And I think that's also great because some applications do a lot of matrix vector multiplication. And machine learning inference tasks, especially training tasks, also are a possibility. It can be good fit for those, right? So again, I think from the processing using memory perspective, the operations that you can do in the intrinsic to the device determine what type of applications are easier to incorporate. Processing near memory, let's go back to that one, is a bit more general, right? Because now you have a processor that's closer to memory. Fundamentally, it could be any application, right? Fundamentally, you could execute anything near memory. But of course, now technology also potentially dictates what kind of processor you can put near memory, right? If you cannot put a very compute intensive, a very computation heavy processor in a logic layer like this in 3D stacking, or inside the DRAM chip, if you have some, or inside the flash chip. Again, pick your favorite memory technology. Inside a chip that's designed for memory, you cannot put an extremely complex computation engine because of the mismatch in the fabrication capabilities. You won't get a very good processor over there, basically, and overall you would explode your energy because of the leakage problems that you have. So
Professor, would that mean? Would that mean that you will have a customized ISA as well, or a subset of the ISA? You can't have like all the compute functions, right? But then you are restricted with what can actually run here.
Yeah, potentially. I think potentially, yes. You may not be able to have very compute-intensive functions, right, on the memory side. Yes, maybe you have a subset of the ISA or a customized ISA. Yeah, I agree with that. Or some, yeah, exactly. Some instructions can be offloadable. Some instructions cannot be offloadable from the main processor. It depends on how you design the system. But yes, I think the design requirements, implementation requirements may dictate what you can have. But over time, perhaps you could keep adding, right? Initially, you may not be able to add a lot, but over time, you may start adding as the technology, let's say, becomes better over time, right? Today, for example, people are working on 3D stacking technologies where you can stack logic and memory layers. And the hope is that logic layers are going to be, let's say, as good as logic layers you can have in today's processing technologies. Of course, the downside is you're 3D stacking, so you have thermal issues, right? So there's no, let's say, free lunch. You have to consider all of these different issues. And in the end, yes, I think what is beneficial for offloading, let's say, to near memory is determined by what you can execute over there efficiently. Usually, in our experience, very memory intensive functions that do not have huge computation requirements benefit a lot from offloading. Or communication requirements, right, with different functions. So they actually benefit a lot. And we've done, for example, studies in graph processing. Again, I'm not going to bore you with all of these, but there's a lot of applications that we have studied. But maybe I'll mention one of these works where we try to at least automate this process as much as possible. So you can, for example, I think this answers, this is the question I ask is very similar to what you mentioned here. When do you employ near data processing? How do you figure out which functions should go? clearly there are a lot of studies that show benefit, but there are a lot of applications that can potentially benefit. And in this study, we looked at more than 300 applications from different domains. And again, we tried to develop a methodology to classify functions. We call it the MOVE methodology, data movement bottleneck methodology. And again, you can look at the paper for more detail, but you can come up with methodologies that classify different functions based on some characteristics like temporal locality, how much caches are effective, what is the miss rate that you're having in the entire application, what's the arithmetic intensity. And based on that, you come up with a classification of what's your main bottleneck, right? And once you know your main bottleneck, these main bottlenecks behave differently if you execute on the processor, execute on the a near data processor with different characteristics. So you really need to understand how these different bottlenecks behave on different execution units. Let's say some of them may be near memory, some of them may be using memory. In this particular example, we used near memory. We did not look at using memory. And then basically you can decide, okay, if this bottleneck executes well near memory, if it's not compute bound, for example, if it's compute bound, basically you'd better execute on the processor. You don't want to ship it to the memory. But if it's, for example, DRAM bandwidth bound, it benefits a lot from near data processing with high bandwidth. And yeah, that's the idea basically. And this is all open source, so I don't want to go into more detail here. But as I said, this is still an area of research. If people, we did not really solve the problem fully. I think there's a lot of area of exploration over here. Like automation of this is important. But people can build on our work, for example, if they're interested, or they can come up with something completely different that can benefit the field.
So Rina is already online, and I think that means that we are running out of time here. So, but I have so many questions that I would like to get your views on. Rina, can I borrow like for one more question?
Yes, you can. We've slightly overshot the time, but you can certainly go with another question.
Sure. So just one final question, Professor Onur, and I think this benefits both us in the industry and maybe the research in the university. So what are the roadblocks in research that you see from the industry standpoint and from a university or lab research point of view?
Okay, that's a very broad question. Let me stop sharing over here. Okay, so I think let me try to understand. So if roadblocks in terms of things that will like bottleneck the research that you're doing in industry versus academia.
Actually, in both,
okay.
Not really a comparison, but
okay.
So some of the earlier sessions, what we realized is the university people said like all the data today resides with the hyperscalers. It's there with maybe with Google or Azure or others. So we don't have this data in the industry, sorry, or in the academia. And then from an industry point of view, the people who can take the risk and really do the research are sitting in the university, but then we have some data governance issues. We really can't share data across and things like that. Lines. From your viewpoint, like if you wanted, if you had a free hand, like this is how the research can happen better. Like what are maybe just top 2 or 3 of points from your end?
I see. Okay.
Let's not go the entire list, but top 2, 3.
Yeah, sure. I understand. Okay. Yeah. I mean, if I had a free hand, that would be a different world, of course, right? But yeah, I mean, I agree. Overall research today is like bottlenecked by, let's say, access to some data that could be useful for doing, let's say, free research on it. It could be models, for example, of machine learning, for example, right? Or it could be the technology parameters that I just mentioned earlier of an emerging technology. I mean, if I had a free hand, I think open sharing of data is very useful, in my opinion. But that's a bit unrealistic. But we push for it. I mean, as much as possible, right? And at least in academia, you can do that better than you can in industry, in my opinion, because industry, in the end, your goal is to make money for your product, and it cannot openly share everything. Otherwise, you may lose the competitive edge. But I would say if I had a free hand, open sharing of everything would accelerate like overall progress, in my opinion. That said, I think it's still good to have competition in the sense that people should really start try to compete for, let's say, better ideas, right? You should have some incentive on coming up like with big solutions to like next memory technology, right? And I think that can still benefit from open sharing, frankly, of data. But that may also require people to invest a lot, right? Into so that brings me to the next point, basically, which is really investment in research. Open sharing is great, but you also need to, if you want to, let's say, carry out a big research that can change the world, that requires a lot of investment, right? If you're doing, for example, an emerging technology research and trying to develop this technology, fabrication of this technology takes a lot of investment, money, as well as people investment, right? You need to educate the people so that they actually get to a point where they can develop this technology and fabricate the technology. And also you need to provide the money so that that can be manufactured. So I think investment in fundamental research is really critical. And that, in my opinion, that has to be done by everyone who has money. that's governments, that's certainly industry, and also people who are, let's say, wealthy. I think they should probably be putting more investment into the fundamental research, because like this ties back to my first principles approach early on, right? I think first principle is really fundamental, and a lot of the advances that we have realized are based on very fundamental research that people have done. Like flash memory is a great example. Emerging technologies, I think, are going to be great examples also. Yeah, maybe I have two. And also, I think the third one, I will mention the third one, is really, it's kind of related to what I said, investment in people, which is really having a stronger education system that pushes, not necessarily pushes, but that encourages people to become more creative and solve these big problems. So if they are early on exposed to issues that we may be having, let's say 10 years down the road, 20 years down the road, as opposed to just learning what's happening today, right? If they have this perspective, broader perspective, and they're encouraged to think out of the box, come up with creative solutions, I think that's actually very, very important. So I see that as a, not necessarily a roadblock, but something we should really do in the education of future generations, because education is evolving clearly, and there's a lot of access to a lot of interesting content today, but we should maybe guide that education so that people become more creative and more aware of future problems, and so that when they really need to solve it, they have all the tools that they need to solve it. So maybe open sharing, open sharing investment, and education focused on future problems and creativity.
So some great set of suggestions as well, and it was nice hearing your views, Professor Onur. And thank you so much, Professor Manu, for adding your views and the questions. And thanks, Rina, for being generous and sparing additional time. Thank you so much.
Wasn't. The session was so interesting and so intriguing. Thank you, Ankit, for driving the entire session. I think we need to type applause on the chat box and thank Professor Onur and Professor Manu for taking time out and joining us. Thank you so much to both of you for joining us along, and thank you, Ankit, for driving the entire session. On that note, we've almost come to the end of the event, but we've got someone special who would tell us something more and how the day went by, what else is in store when future is concerned. And that's why I'd like to request Dr. Prashant Misra, who is the chair of IEEE Computer Society Bangalore chapter and vice chair industry engagement of IEEE Bangalore section. Please join us along and speak to us. Over to you, Dr. Prashant.
Hello, good evening, and thanks, Rina.
Good evening.
Yes. Hope I'm audible clearly, because I have issues with the microphone. Is it fine? Yeah,
it's clear. It's clear. Yes,
great.
We can hear you clearly. Over to you.
Sure, thank you. Now, I think we had a wonderful day today. If you look at right from the onset, from 8:30 in the morning till now, I think it has been a full rock-on session. I think every talk was very well presented, conducted. Questions were absolutely bang on, and I think it and the amount of participation we have got is stellar. So maybe on the current bridge, you are seeing around 60 to 70 participants. On a proxy bridge, we have again close to 100 participants. So to give you some numbers, I think we had close to like 200 participants throughout the day, and it has only tapered towards the end of the day, but consistently it has been 200 plus. So that says a lot about the quality of the event and the interest that participants saw and the value they got out of actually attending the entire day. I think we had talks all around the board in storage and data. So we had talks on building new storage systems and new hardware for it. We had talks in persistent storage systems, persistent memory systems. We had talks on accelerators and design accelerators. We had talks on data caching. We had talks on coming up with different new ways of computing and how storage and data plays an important role in it. So I think we had a fantastic breadth and depth of talks, and that is what I think the US participants really like today, and that's why you have stuck on for the entire day and shown your support to this entire event. Now, I think this entire program wouldn't have been possible without the speakers who came and spent time speaking to us today. Right from the word go, we had Dr. Dejan, who was there in the morning, right? I think it was US time. It was very early morning for him, but he made time for it and gave the keynote, followed by Professor Vijay Chidambaram from UT Austin. Then we had Xian Li from University of Virginia. We had Andre from Intel. Sorry, we had some glitch here. Give me a moment, 1 second. I think. Yeah, sorry. So, and then we had Dr. Kiran from Western Digital who spoke about accelerators. Then we had a panel. The panel was moderated by Ankit, but the panelists were Alex from Ondart. We had Professor Umesh Belur from IIT Bombay. We had Rashkumar Kannan from HPE. Then post lunch, we had Kishore, who is an independent storage expert. We had Mr. Sundara Ramalingam from NVIDIA. We had Professor Jian Lee from NUS, followed by Yusuf from Linbit, and now you are listening to Professor Onlur Mutlu from ETS Zurich. I think it's a stellar line of speakers, and this is something we started preparing like around 3 months back. I think we as a team, Desh, Ankit, Santosh, Chengappa, and myself, along with support from other colleagues like Amit and Divya ma'am, we came together to actually start preparing for this program, and we're very happy that it has really turned out well. So as it was said, this is like the 4th edition of this particular symposium. Even though this is the 3rd year, this is the 4th edition, and we plan to have another edition, which we call the winter edition, towards the end of the year, mostly around the month of December, maybe at the beginning of December. And this is a pattern that we have been following for the last 2 years. We have a summer edition in the month of June, July. We have a winter edition around the month of November, December. And I think for both these editions, we try to get the top-notch speakers and researchers and academicians and industry experts who would love to share their ideas on data and storage, and we still follow the same pattern. I think I was very happy to see Reena be the entire day and really be the torchbearer for it. I think it was wonderfully coordinated. Reena, thanks to you. I think you were spot on with actually keeping the time, making sure the audience were really excited about it. And I think I think you kept our interest levels really high. So really thank you for spending the day with us and really taking up this job to the best possible extent. Actually, we really enjoyed it. Actually, being you, really staying there and keeping us active throughout the entire day. And apart from that, I think let me also thank our IT handling people. Of course, they are part of the XCOM. It's just that they take up the additional volunteering role of trying to manage the WebEx and other IT channels. That's Mr. Chengappa from HPE. And then we had a student volunteer from BMSC, Mr. Asif. So I think both of them were stellar again. We also had Ketan also join us in between. So I think we had a well-rounded team who also took care of the WebEx and the other IT infrastructure that was running behind the system. So overall, I think I did not say anything more. I think you guys being here till the end of the day really says a lot. And we wish that you join us for the future edition of the symposium for the end of the year once again. So with that, let me close the stage. And a final round, I think again, on behalf of IEEE Computer Society and IEEE Bangalore section, I thank all of you. And we'd love you to become part of other such events that we do going forward. We also like to thank Huawei, who has been especially represented by Ankit and Desh, who have been really supportive of the entire event from the first edition till now. And we wish that wish to have the continued collaboration for many such future successful events. So thank you all. Thank you. It was a great team effort. And with that, let me close and over to you, Reena.
Thank you so much, Dr. Prashant. Hope all of you had a good time today, and thank you for putting all of it together and thanking on behalf of the entire event. And I truly hope all of you had a great time. If that's a yes for one last time, I want to see yeses coming on the chat box. And I hope all of you had insightful sessions today. We had so many sessions, panel discussions, we had a fire chat, we had a productive day. And I'm sure all of this information is going to help all of you. I see yeses coming in. With that, we would like to conclude today's event. And thank you once again to all of you for taking time out and joining us here. Thank you. Thank you so much. See you in the winter edition.